In this video, I'll discuss supervised machine learning. In machine learning, we generally talk about three different kinds of learning. One kind, supervised learning, is learning a model based on a set of labeled examples. The technical description of a labeled example might be expressed as a vector containing parameters paired with the desired output value. But a friendlier way of saying that is that supervised learning models are given previous examples of what worked or what didn't, so they have some experience and use that experience to make current and future decisions. There are plenty of examples of problems that machine learning models have to deal with. Spam detection in email is a common one where the input is an email message or email metadata, and the output is the determination that a message is spam or not, or the probability that email is spam, so somewhere in between. In the medical field, an input could be a patient's medical information and the output would be diagnoses. Another example might be the prediction of a home's selling price, with the input being the home's details, how big, how new, how many rooms, how many bathrooms, and so on. The output would be the estimated selling price of the home. Classification is used to assign a meaningful placement of an element, that is, a categorization. So, given an input, an agent could assign a class to an element. The output is usually categorical, and numerical data can be transformed into categorical data for classification. To use a spam detection example, an agent could classify an email message to determine that it's spam or not spam, so a binary classification. Common models used for classification include decision trees, logistic regression, and support vector machines. Regression means that given an input, an estimation of a parameter is provided. It can be seen as a function of the input, and output is typically numerical data. Some regression models map to categorical data, for example, logistic regression. An example might be home price detection, where the output is a function of the input mapping to a number. Common models used in regression are the linear regression model, the multiple regression model, and decision trees. In this video, I'll discuss the fundamentals of building machine learning models to solve problems. In machine learning terminology, model refers to the structure that maps from an input to an output. So how is a model defined? First, by what needs to be predicted, so classification, regression patterns, and groupings need to be determined. Next, what attributes must be defined. This is important because often we don't need all attributes of a thing in order to make a determination for a specific task. For example, if we're deciding whether or not to turn on the television, the color of the television or how far away it is in relation to us is irrelevant. And then what data set is used. Whether we go with labeled or unlabeled, in other words, is it a supervised or unsupervised model? And then we have to determine how big or small the data set should be. Models typically require many examples for each predictable element. And models need to be tested. A common method for testing is to split example data set into a training set and a testing set. You test the percentage of accurate outputs with the testing set, and repeat the test with different splits of the data set, a process known as cross-validation. And there are important considerations for a model's quality. Is it consistent? How many examples can it correctly predict over and over again? What's the size of the data set? Small data sets can cause overfitting, statistical phenomenon that occurs when a model contains too much noise and loses predictive power. Precision and recall is an important quality consideration, and statistical methods like F1 score can be used to determine a model's quality. Feature engineering is the creation of features for data sets, and it's used to optimize results, that is, provide a better environment for machine learning agents to learn and make decisions. Examples include combining attributes, for example, determining area by multiplying height and width, decomposing attributes, say taking a system's date-time function and breaking it out into year, month, day, and time of day. And transforming data is a method of feature engineering where you change units or normalize data, for example. There are benefits of feature engineering. It can make models yield better results, and it can make algorithms perform better. Finally, when selecting features, features can be scored by running different combinations of features with training algorithms. By scoring them, agents can better determine which ones are more preferable in making future decisions. In this video, I'll discuss overfitting, what causes it, and how we deal with it. Overfitting is a term in statistical analysis that refers to learned models that are too good. Now, you may think that there's no such thing as too good a thing, but overfitting can be problematic. In machine learning, we want to make the data as good as possible, fit it using feature engineering so that a machine learning algorithm has the best possible chance to make the right decisions. A signal is the target pattern that you want to learn. Noise refers to random error in the data that doesn't follow the pattern. And the machine learning goal is to learn the signal while not learning the noise. Overfitting occurs when we learn the noise. So what causes overfitting? Well, primarily complexity, where overly complex models exist. Remember, complicated models require large data sets, and this can obviously lead to complexity. On the other hand, small data sets need to be large enough to show clear patterns, and if they aren't large enough, then an agent can't detect trends. So how do we deal with overfitting? Well, first, we gather more data, take more samples and label more examples, and combine data sets. You can simplify models using models with fewer parameters when possible, minimizing attributes and features when possible, and use models that punish complexity, regularization methods. There are also ensemble learning methods where you can train multiple models and combine the results. In this video, I'll describe how to evaluate machine learning models and how to compare them. The confusion matrix is a visual method used to represent what kind of errors a model is making. For example, in binary classification, you can determine the possible outcomes of a simple yes or no answer with a table like this. You begin with a prediction made by a machine learning algorithm, the possible answer being either yes or no, and map that choice against the correct answer, again, yes or no. Here you're left with 4 possible outcomes. True positive, meaning it was detected as spam and it was spam. False negative, meaning it was detected not to be spam and it was spam. False positive, meaning it was detected as spam and it wasn't spam. Or true negative, meaning it was detected not to be spam and it wasn't. Now, this is just a binary representation, but in the real world, choices often include more than 2 possible outcomes, and non-binary problems can have multiple confusion matrices. Precision refers to the ratio of correct answers, so in the binary example, we would determine precision by dividing true positives by true positives plus false positives. And recall refers to the ratio of true examples that are correctly identified. So we define recall by dividing true positives by true positives plus false negatives. Here's an example using a spam detection metaphor. The model for spam detection, which is a binary choice, either spam or not spam, yields this matrix. So 20 spam emails were correctly identified as spam, true positives. 5 spam emails were labeled incorrectly, identified as not spam, false negatives. 10 non-spam emails were incorrectly identified as spam, false positives. And 50 non-spam emails were correctly identified as not spam, true negatives. Here's an example of how the spam detection ratio would be calculated with precision, which divides true positives by true positives plus false positives, resulting in a precision of 67%. And here's the result for recall, which divides true positives by true positives plus false negatives and results in a recall value of 80%. In this video, I'll discuss the linear regression model. In statistics, the linear regression model is used to model relationships. In the linear regression model, inputs are directly mapped to a numerical output. For example, given an input of the parameters of a house, the output would be the house's perceived value. In the linear regression model, for input vector x with p parameters, the output is given. This is the common single variable linear regression model. So what does the model represent? Weights parameters are provided representing the contribution to output, the relationship between input attributes, scale, and so on. In this first example, given rooms and bathrooms, rooms has a greater impact because bathrooms are part of a house, and typically a house will have far more rooms than bathrooms. In this second example, rooms and area have a similar impact on the model because they're roughly analogous, as you can add up the number of rooms and it will be roughly equivalent to the area of a house. Bias, or intercept, is the error not represented by the rest of the model. In this video, I'll discuss the linear regression model and the gradient descent algorithm. In statistics, the linear regression model is used to model relationships and estimate value. Inputs are directly mapped to a numerical output. For example, given an input of the total number of retail sales in a day, the output would be the value of the day's sales. But there's a cost to the model, and that's how much error a model has. The cost function is described as the cost of a model given the parameters for that model. This is the least squares cost function used in linear regression analysis to increase accuracy by estimating unknown parameters. Gradient descent is an iterative algorithm that, given an example set, determines the minimum. The method works by initializing parameters, calculating cost, calculating gradients, and updating weights. Steps 2 to 4 are repeated until convergence, a term in probability theory that refers to the point when the difference between variables becomes statistically irrelevant, occurs. In this video, I'll discuss the k-nearest neighbor model. The k-nearest neighbor, or KNN model, is a supervised learning pattern recognition model that classifies data for regression analysis. The basic algorithm works like this. First, find the k-nearest neighbors in an example data, and then classify the input to the most frequent category in the k-nearest neighbors. Distance is calculated using Euclidean distance, a straight line distance between example and input, and Hamming distance, that is, how many values overlap. For example, the Hamming distance of test and rest is 3 because there are 3 overlapping values, the letters E, S, and T. There are advantages and disadvantages to using the k-nearest neighbor method. It's advantageous because it requires no prior training of an agent, and the implementation is relatively simple. On the other hand, predictions are costly because they're resource-intensive and conflicts can occur. A majority vote can cause issue with skewed data. For example, if you had a disease data set and only 10% of the patients were ill, k-neighbors would be likely to contain many healthy patients. Finally, different feature ranges can affect the distance calculation negatively. For example, competing features like the number of rooms in a house will be statistically different than the area of the house. One would be a relatively small number like 6, while the other would be a relatively large number like 3,000. In the weighted KNN model, each k-neighbor is weighted with total weights equivalent to 1. A vote occurs by neighbors picking the class that has the most weight. Unweighted KNN weights are applied by giving each k-neighbor 1 over k weight and giving the remainder 0 weight. In this video, I'll discuss decision tree models and the C4.5 algorithm. Decision trees are a key component in supervised learning to determine output by splitting the data based on attributes values. They're used to make decisions based on parameters, that is, values provided in a tree's leaf nodes. Decision trees are typically used for classification being when there's a finite set of attributes that can be assigned to a node. And decisions fall under the same class as the data. If an agent was using a decision tree to decide whether to activate a thermostat based on the ambient temperature of a room, for example, it's only going to use the data provided by that room, the class, and not any other room in the house, which represent other classes. Generally, higher nodes on a decision tree indicate more important attributes, as in this example tree where traffic is the highest priority, early meetings and gas tanks ranking next in the decision process, and so on. The C4.5 algorithm is commonly used to generate decision trees for machine learning. And here are the recursive steps to build a decision tree. First, choose the attribute that characterizes the most amount of data. This is accomplished by calculating the information gain and picking the attribute with the best gain. Then the dataset on that attribute is split. This is repeated recursively with split datasets until a base case is reached. Base cases mean that every example in a sub-dataset is in the same category and that there are no more features or no more useful features. Guesses are performed using the expected value. So what does a decision tree represent? Well, learned patterns are arranged in a series of decisions that can be used to make future decisions. Typically, earlier decisions are the most important features because they represent the learning behavior of an agent. They can be used to make future decisions. In this video, I'll demonstrate how to set up scikit-learn for Python. Now, the first step to getting scikit-learn is to understand what you need. In order to use scikit-learn, you need Python 2.7 or later, or 3.3 or later. You need NumPy 1.82 or later. And you also need SciPy, this version. Now, you can install these individually, but Scikit's site here actually allows you to install a package down at the bottom called WinPython. I'll go ahead and click that. And this is an open source aggregate package which includes everything you need plus a ton of scripts, several different Python interfaces, and even some IDEs, some GUI IDEs. Go ahead and close that. Now, I've already downloaded the latest package and installed it. It's a straightforward installation, but it does take a while to unpack the files. Now, the only thing you should do when installing is to pick a friendly name for the target directory. The installer will default to the location of the installer executable, and that should be changed. So I put this in the C WinPython directory. I like to keep it simple because it's easier to type and remember if you don't have to deal with the versioning information. Now, I've also created a shortcut for that folder on the desktop to make it easily accessible. Now, there's a bunch of different applications in here that you'll probably want to try out, particularly command line Python interpreters and GUI Python interpreters. Next, you'll want to install GraphViz, a graphing package that can be leveraged in Python. It's open source and can be downloaded from the GraphViz website. Neither of these packages creates Windows environment paths, so this has to be done manually, and if done incorrectly, it's going to cause you some grief later on, so I'm going to show you how to set this up. First, you'll probably want to grab the installation directory for GraphViz, so let's take a look. It's in C program files x86, GraphViz, and whatever the version is, in this case 2.38. And you actually need the bin folder. So I'll go ahead and click here, right click and copy that to the clipboard. And let's go to environment variables. Now I've already set these up, but I'm just showing a quick way to actually do this if you're setting it up from scratch. So in environment variables, you want the path system variable. And there it is right there, the GraphViz directory. So that's great. Now next, we want to create a new variable, a system variable for Python. Now, this is entirely up to you if you want to do this, but now this is optional, but you have to create two paths in the system path variable for Python, so it's a bit easier this way. You can call it whatever you want, but I named it WinPy workdir because it appears that's what the included WinPython scripts look for. So what you do is you actually create take the Python path from here, WinPython. Let's go back and take a look. And I've got two versions here, but this is the one I want, 3.62.amd64. And again, you can just copy that into the clipboard and go and create your WinPy workdir variable and then add the path. Now, once that's done, back in the Windows system path variable right here, you can see that we've added the WinPy workdir as well as the WinPy workdir scripts. You're going to need both of those in order to properly work with Python in Windows. Okay, I'll go ahead and cancel those. Close that. Now, once you've changed those system variables, you should restart the system to ensure that the environment variable changes are registered. So next, I'm going to go ahead and open a command prompt. Now, before we enter the Python shell, we need to perform a one-time step of setting up GraphViz for Python. We set it up as a Windows application, but you actually have to set it up in Python as well. And to do that, we need pip, a Python package installer. It will search the internet for the package, so the command is pretty simple. Now, what I want to do is try this. It should work from here. Install GraphViz. If it doesn't, we'll have to change to the working directory. No, it's fine. Okay. Now I've already installed it, so we should get a response here saying, yeah, it's already satisfied. We've already got it installed. But if it wasn't installed, you'd see a prompt here telling you that the installation is going ahead. So there you have it. Now let's check the paths. Now let's check that the paths for Python are working, and you can do that simply by typing the Python command. Okay, no errors, and the triple bracket prompt tells us that we're in Python, so that's it. Now you can start working with Python, scikit-learn, and GraphViz. In this video, I'll demonstrate how to import data and perform basic tasks with scikit-learn for Python. The WinPython kit comes with sample datasets called iris and digits, and here's how to load the samples and begin to work with them. Now, this tutorial can be found on this page, and I urge you to try it out, but I'll demonstrate it here. I'm going to use the WinPython interpreter, which is a nice command line Python interpreter that includes a command history, autofill, and color hinting. Now I'll start by importing the iris and digits datasets. So it looks like this from sklearn for scikit-learn. Now this has a great autofill feature, and to use this, don't use the tab or the space bar. You might be tempted to, because that's how other autofills work. This actually uses the arrow keys. So if you just arrow down, then go ahead and hit the space bar, and there you go. And then once again, I'll do it for data sets. Now, once I've got that up, I'll go ahead and press enter. Okay, we've got our data sets functions in there, so now we can load up iris. So iris equals datasets dot load underscore iris, and opening and closing parentheses. Same with digits. So we'll load up digits equals datasets dot load underscore digits, and again opening and closing parentheses. Now, datasets contain data and metadata in the form of an array. The dataset is referenced by .data, so we can view this array using the Python print command like this. So print digits dot data. And again, if you want that autofill to work, remember to use the arrow key in order to bring up the entire word. Otherwise, you'll do what I almost just did. Okay, so there you go. Now we've got the digits.data. Now we can use the digits.target to provide ground truth. I'll show you this and explain that. Digits.target. Okay, in machine learning, ground truth speaks to the accuracy of a training set and its classification in supervised learning. As you can see here, the information is returned as an array, and what you're looking at is the corresponding number for each digit we're learning. In this video, I'll use scikit-learn to fit a linear regression model to a dataset. In statistics, the linear regression model is used to model relationships. In the linear regression model, inputs are directly mapped to a numerical output. For example, given an input of the parameters of a house, the output would be the house's perceived value. Linear regression reduces the excess sum of squares between observations and predictions. Now, this tutorial can be found on this page, and I do urge you to try it out, but I'll demonstrate it here. So I'll go ahead and start by importing the linear model module from sklearn. Import linear model. Now I'll create a variable object reg that contains the linear regression model. So it looks like this: linear model dot linear regression, opening and closing parentheses, and press enter. Then I'll use linear regression to fit three arrays. So reg.fit, and the syntax here is a little bit tricky. You got to pay attention to the opening and closing parentheses and brackets. So 0, 0, close bracket, 1, 1, close bracket, comma, another open bracket here, 2, 2. There we go. And here actually we have to put in another closing bracket because those are the three arrays. But now what we're going to do is this. So 0, 1, 2. And then close the parenthesis. And I think that looks okay. All right, go ahead and press enter. Okay, now we got some feedback here. Now note the syntax where we've got three arrays followed by the arrays to be fit. That is 0, 1, and 2. And the feedback just lets us know that the fit operation worked. And now we can apply the coefficients from this linear model. And it looks like this: reg.coef with an underscore after it. Go ahead and press enter. And there's the feedback in the form of an array. In this video, I'll demonstrate how to use scikit-learn's k-nearest-neighbor model. The k-nearest-neighbor, or KNN model, is a supervised learning pattern recognition method that classifies data for regression analysis. The basic algorithm works like this. First, the k-nearest-neighbor is found in training data, and then it's classified, and then the input is classified to the most frequent category in the k-nearest-neighbors. Now, this tutorial can be found on this page, and I urge you to try it out, but I'm going to demonstrate it here. So I'll go ahead and bring up my shell, and I'm going to start by creating some training data in a variable called x. So x equals, and here we go, 0, 1, oops, 2, and one more. We'll put in 3. Okay, and press enter. Now next, I'm going to create an array called y that represents target values. So y equals 0, 0, 1, 1. And then I'm going to go ahead and import the k-neighbors classifier from scikit-neighbors. So it looks like this: from sklearn neighbors, import k-neighbors classifier, just like that. Now, k-neighbors locates the k-neighbors of a point, and now I'm going to create a variable object, and I'll call this neigh, just like the tutorial. K-neighbors classifier, and then in parentheses, n-neighbors equals 3. Okay, now fit xy fits the model. X is the training data, and y represents target values, and it looks like this. So neigh.fit x, y. All right, so let's display the neighbor prediction, and we'll do that with the Python print command, neigh.predict. This one's a bit tricky. So it's this 1.1. It's double opening and closing brackets, and then you're going to have two closing parentheses, just like that. Now, predict provides a prediction of the class labels for the data, and you can see there it's 0, and here's the prediction probability. It looks like this: print neigh.predict probability. Oops. Double brackets, 0.9, double brackets, double closing parentheses. Okay, so predict proba returns the probability prediction for our training data. In this video, I'll demonstrate how to use scikit-learn to fit a decision tree model to a data set. Now, this tutorial can be found on this page, and I urge you to try it out, but I'm going to demonstrate it here. I'll start by importing a tree function. So from sklearn, import tree. Next, we're going to create our input, which is comprised of two arrays. So an array called x, looks like that, I think, yeah, and y, 0, 1. Now, array x contains the samples and features, and array y contains the class labels for our sample. Next, I'm going to create the decision tree classifier, which is used to apply multi-class classifications to data sets. I'll just create an object, variable object called CLF equals, and it's tree dot decision tree classifier, opening closing parenthesis, and press enter. Now we're going to use that to fit x and y. So CLF equals CLF dot fit, and then in parentheses x comma y. Okay, now that we've fit the data, we can fitted the data, we can predict the class. So it looks like this. CLF dot predict 2 point comma 2 point and that. Okay, so we've got array 1, and we can also predict the probability of the classes using another command. So it's CLF dot predict proba for probability. Okay, the result here is the percentage of the number of training samples that share a class in a leaf node. In this video, I'll demonstrate how to use scikit-learn and GraphViz to generate a decision tree model from a dataset. With scikit-learn and GraphViz, you can generate a decision tree from a dataset. Now, this tutorial can be found on this page, and I urge you to try it out, but I'm going to demonstrate it here for you. So let's bring up our interpreter. Now, we'll build the tree using the iris dataset included with scikit-learn. So I'm going to type in a few lines here, sklearn datasets import load underscore iris. Okay, from sklearn import tree. So we have to import tree module iris equals load underscore iris, opening closing parentheses. Okay, so I'll create a variable called CLF equals tree dot decision tree classifier, and then take that and fit it. So CLF dot fit with iris dot data comma iris. We have the data and the target, so iris dot target. Okay, now that the data has been trained, we can generate a tree based on the data set. So here's where GraphViz comes in. Import graph, there it is. And then we use dot underscore data equals tree export underscore GraphViz. Okay, now remember we have that fitted data CLF, comma, and then out file equals none. Okay, graph equals GraphViz dot source. I think that's supposed to be a capital letter. I don't think it matters though. Underscore dot data, or dot underscore data rather. Okay, so we have an issue here. Graph, that's what I did wrong. Bring it back up with the arrow key. GraphViz dots. Okay, there we go. And then finally, graph dot render. Here's where the graph is actually created from the data we just created. Okay, now here's where we actually render it with graph dot render. We use iris, which is the data set that we had. and it'll render it from that iris data set, and I'll show you that momentarily. Might take a second. Okay, now we get a little bit of feedback here saying iris.pdf, so that's somewhat helpful, but the thing is we don't really know where it is. Now we want to find that PDF, and it would be created in the current working directory, and we need to determine that. We can use this code in Python, import os, and then print open parenthesis os dot get cwd for current working directory, opening closing parenthesis, close parenthesis there. Okay, so the current working directory is CWinPython notebooks. So let's look in that directory. Okay, now there's an iris file right there with no extension, as well as the PDF. Let's take a look at the iris file first. Open with Notepad. Okay, so what's happened here is our tree data has been created in plain text format, and we can view the learning tree created from the data. Go ahead and close that by double-clicking on the PDF file. Okay, now this is really interesting. As you explore the function, okay, this is really interesting. Now, the tree has been created for us, and it's just that easy when you're working with GraphViz in Python and scikit-learn. Now, keep in mind that export GraphViz can also be trained so you can customize the look of your tree. So if you want to explore its options, you can modify coloring and naming, and that might be helpful, but this is our learning tree generated by that data. In this video, I'll demonstrate how to use scikit-learn to calculate the precision and the recall of different machine learning models in Python. Precision refers to the ratio of correct answers. So in the binary example, we would determine precision by dividing true positives by true positives plus false positives. And recall refers to the ratio of true examples that are correctly identified. So we define recall by dividing true positives by true positives plus false negatives. Now, this tutorial can be found on this page, and I do urge you to try it out, but I'm going to demonstrate it for you here. So I'm going to use the Spyder IDE for Python because we can save this as a script or several scripts once we're done. Now, this example is of the precision recall metric that evaluates classifier output quality, and the scikit site provides the code. I've broken it into 3 separate Python scripts that perform different operations here. First, a data series of simple data is created with noisy features, and then a limit created here, and then a simple classifier is created here. Next, the average precision score is calculated. And finally, the precision recall curve is plotted. So I urge you to review this code and also go take a look at the tutorial on the scikit site for a little bit more information on how everything works together. So the first script creates the data using the iris dataset, and then adds the noisy features and limits to the first 2 classes, and then splits the set into training and test sets. Finally, it creates a simple classifier. So I'll go ahead and run this. Now, notice that no feedback has been provided in the console window, and that's great because we don't expect any feedback. Now, I'm going to switch to the next script, which is a very short script, and run the compute precision, which imports the average precision score function and applies it to y, test, and score, and then displays the average precision recall score using the Python print command. Now, it gives us a score of 88% right there. Now, finally, we want to plot precision recall. I'll go ahead and bring that up. Now, the script imports precision recall curve and matplotlib for plotting the information. And if I go ahead and run this, we get a graph showing a 2-class precision recall curve with an average precision recall score of 88%. Now that you've learned about machine learning and supervised learning, it's time to put some of that knowledge to work. In this exercise, you'll create code to fit a linear regression model to a data set with scikit and Python. You'll import the linear model function, create a variable object that contains the linear regression model, fit 3 arrays, and apply the coefficients from the linear model. At this point, you can pause this video and perform the exercise. Once you're finished, resume the video and see how I would do it. So let's perform these tasks. It's alright if you didn't do it exactly the same way. Now, you can do this in a Python shell or one of the various GUIs, but I've recreated the 4 lines of code here for easy reference. So here's the code to fit a linear regression model to a data set. First, you import the linear model function using this. So from sklearn import linear_model. Then create a variable object that contains the linear regression model, and it looks like this. Now, this is called reg. You can call it whatever you want, but it basically looks like this: linear_model.linear regression with opening and closing parentheses. Then fit 3 arrays. Now, we use regfit and provide 3 arrays plus 3 array references right here. Now, we use regfit and provide 3 arrays plus references here. Okay, finally, this is the code for applying the coefficients from the linear model, reg.coef_. I hope you found this exercise helpful. In this video, I'll discuss how decision trees can be applied to regression problems. In machine learning, predictive models are used to solve problems, with the 2 kinds of models being classification and regression. Regression is a method for providing quantitative values, and regression trees can be used to predict numerical variables. The tree model uses partitioned data based on a tree's rules, and once data is partitioned enough, a simple model is applied. So let's look at regression trees versus the linear regression model. A regression tree applies models locally, that is, partitions that are too small. And they can easily consider interactions. For example, a room count for a house pricing model might be more relevant depending on the city where the house resides. With linear regression, a model is applied globally, and unlike a regression tree, it can't easily consider interactions. In the piecewise constant model, the simplest regression tree is used, where leaf nodes return a constant, and the constant is the average of the training example's values in that partition. If data is missing, the average of the values that the branches lead to is returned. With learning regression trees, the sum of squared errors to split data is used. The algorithm works this way. S is calculated for the current data set. The split that decreases S the most is chosen. The data set is split, and the process repeats recursively until you either have no remaining nodes to split or until the splits aren't changing S by a significant amount. In this video, I'll discuss the CART decision tree learning algorithm and how it's different from C 4.5. Classification and regression trees, or CART, is a standard tree model used for binary splits, whereas C 4.5 and other models are used for special data. For example, C 4.5 is used for non-binary splits. But the CART algorithm is similar to C 4.5 and works this way. It chooses the best node to split and then splits the data set. This is repeated recursively until a base case is reached, and the tree is pruned to reduce overfitting. Decision trees are created from top-down algorithms, and in each state they select a variable using metrics for identifying which variable is best for splitting the set. The metrics method varies, and here are the 3 common methods for splitting. Information gain, or C 4.5, uses entropy to determine how much information is gained after a split. Gini impurity is used by CART and determines the probability of getting a misclassification. The sum of squared error, used in regression trees, determines the cost of a tree. In decision tree learning, pruning is a method for removing leaves and branches from a tree without significantly decreasing the accuracy of the decision. The point of pruning is to reduce the computational complexity of the decision process, And selective pruning can reduce overfitting. In the reduced error pruning process, a leaf is replaced with the most common value of branch decisions made by that leaf. Change repeatedly occurs as long as accuracy isn't affected. If it is, then the value reverts to the prior value. This is repeated over the entire tree from the bottom up. In this video, I'll discuss bootstrapping, bagging, and random forests. In the learning tree process, splitting a candidate and randomly selecting a set of subsamples is referred to as bootstrapping, and bootstrap aggregation is called bagging for short. When bagging for estimates, the process takes several random subsamples of a sample and they're allowed to overlap. Then an estimate is calculated for each sample, and that could be the mean, the variance, and so on. Then the estimates from step 2 are averaged, and that's used as the estimate. In the bagging method for machine learning, subsamples are taken, and a machine learning model is fitted to each subsample. For predictions, an average of all the models is taken. A democratic process, if you will, a voting system, can be used for classifiers. And the bagging method for decision trees uses CART to build each submodel. But here's the problem. Subtrees are too common to make bagging a useful method for decision trees. For example, if K is a strong predictor, many of the subtrees will have K as a root node. In random forests, a random subset of features for each subtree is used. This is known as feature bagging. Here's the random forest's algorithm. N random subsamples of the dataset are taken and a subset of features is chosen. Then a subtree is trained with subset of features using C4.5, CART, or another method, and to make a prediction, the average result of each subtree is taken. In this video, I'll demonstrate how to build a random forest model in Python using scikit-learn. With scikit-learn, you can generate a random forest from a data set. Now, this tutorial can be found on this page, and I urge you to try it out, but I'm going to demonstrate it here. Let me go ahead and minimize that. And I'm going to use the Spyder IDE for Python because we can save this as a script. Now, in the learning tree process, splitting a candidate and randomly selecting a set of subsamples is referred to as bootstrapping. And bootstrap aggregation is called bagging for short. When bagging for estimates, the process takes as many random subsamples of a sample, and they're not allowed to overlap. Then an estimate is calculated for each sample, and that could be the mean, the variance, and so on. And then the estimates from step 2 are averaged, and that's used as the estimate. You can create bagging with scikit-learn and a model called bagging classifier, and random decision trees are created using random forest classifier. So let's take a look. Now, it starts here, so everything up here just sets everything up in the sample data, but down here we start with our bagging, and the first line right here imports the decision tree classifier. Now the next line imports the bagging classifier module. And then we create a decision tree classifier here, and we'll call it tree. Now here's where we create the bagging classifier. And with max samples, we're going to fit estimators, 100 in this example, with a random subsample from the training points of 80%. So that's what those numbers represent. And next you fit the bag with X and Y. Now, groups of random decision trees are referred to as random forests. In random forests, a random subset of features for each subtree is used. This is known as feature bagging. In the random forest's algorithm, n random subsamples of the data are taken and a subset of features is chosen. Then a subtree is trained with a subset of features using C4.5, CART, or another method, and to make a prediction, the average result of each subtree is taken. Now, this line imports scikit-learn's random forest classifier module. Now, next we're going to define the model for random forest classifier. We define the number of estimators for random forest classifier to fit the group of trees. And finally, we visualize it here. Now, if I run this, what we have is a representation of the forest, and notice the colors which indicate the fitting. If we modify the number of estimators and run it again, we can see a change in distribution of colors. So I'll go with something, say, really low, like 10. And if you do a comparison, you can see around the edges here that we do see a variance, a change. They get more granular and chunky. And so this is a way of generating random forest models in Python using bagging and the random forest classifier. In this video, I'll discuss the logistic regression model. In machine learning, logistic regression is widely used for binary classification problems. It's popular in large part because it's a fairly simple algorithm that always returns a number between 0 and 1. The logistic function is used to represent a probability. As I said, the logistic regression model is a regression model used for classification. It estimates the probability of an input belonging to a class, and it outputs a binary answer. And here's how the model is represented. When you're working with multiple classes with logistic regression, classes can be compared with each other. For example, you have 3 brands. You'd pit brand A against B, brand A against brand C, and so on, and choose the one the most. And classes can be grouped, for example, something versus everything else. For example, again, you have 3 brands, and you'd have brand A versus brand B and C, and assign a value, for instance 0.6, and then pick the brand that got the best score against other brands. Softmax regression is a generalized logistic regression for multiple classes. Here's the softmax function. Z is the weighted input, and the model returns a ranked list of probabilities for each class J. For example, brand A has a probability of 70%. Brand B has a probability of 20%, and brand C has a probability of 10%. Gradient descent, an iterative algorithm used for optimization, can also be used for logistic regression. Models can be learned with gradient descent, and the update rule is similar to linear regression. In this video, I'll demonstrate how to use scikit-learn to fit a logistic regression model. In machine learning, logistic regression is widely used for binary classification problems. It's popular in part because of the Bayes algorithm. Because the Bayes algorithm is fairly simple and it always returns a number between 0 and 1. The logistic function is used to represent a probability. With scikit-learn, you can fit logistic regression models. This scikit-learn page contains some great examples of the module sklearn linear model logistic regression. And I urge you to try them all, but I'm going to show you a few right here. So I'll just maybe pick these 3. First, there's pipelining, chaining a PCA, principal component analysis, and a logistic regression. The PCA performs an unsupervised reduction in dimensionality and logistic regression is responsible for generating the prediction. Now here's the code. It's fairly short. You can copy and paste that. I've already done that right here in Spyder, so let's go ahead and take a look at the code. Now, the code creates a variable called logistic on line 14, which is the logistic regression object, and uses it to create a pipeline on line 17. Now, let's go ahead and run this. And there's our generated graph. Okay, let's go back here. Now, the next example utilizes probability calibration curves. This example shows you how you can predict both the class label as well as probability, and it uses several algorithms, including Gaussian, naive Bayes, and logistic regression. Here's the code. Let's go ahead and take a look at it here. So let's run it. Now, we'll see some feedback output from the various methods being used, and here at the bottom we get 2 graphs. The first, right here, shows reliability curves generated with these algorithms. The second graph demonstrates the calibration curve of a linear support vector classifier, linear SVC, using logistic regression, naive Bayes plus isotonic, and naive Bayes a naive Bayes plus sigmoid. Now in example 3, right here, comparison of calibration of classifiers, predict proba is used to generate a level of confidence. Logistic regression is used to provide calibrated predictions. So let's go back here. Here's the code. Let's go ahead and run it. Now, the output is similar to the previous example, demonstrating reliability curves and the result of the various methods: logistic, naive Bayes, SVC, and random forest. In this video, I'll discuss support vector machine models. Support vector machines, or SVMs, classify data into binary classes. An SVM tries to build a hyperplane to separate data, and a hyperplane is a function, a plane with one dimension fewer than the number of attributes. For example, with two attributes, that is a 2D space, the hyperplane is a line. The optimal hyperplane has largest margin, the margin being the distance between the hyperplane and the close points, indicated on this diagram by the dotted lines. When defining hyperplanes and the margin, you use support vectors, input vectors that are closest to the hyperplane. Hyperplanes are built with a vector, and the margins can be defined with other planes surrounding the hyperplane. The margins planes have conditions, and in this example, no example can be inside the margin. Planes can be built using an example point. Points can be picked to be one of the margin planes. These will become hyperplanes. The hyperplane can be derived from the margin plane, and to optimize it, adjustments are made to minimize the margin while following the conditions. In this video, I'll discuss kernel methods with support vector machines and how they're used to model more complex data. Support vector machines, or SVM, classify data into binary classes, and a hyperplane is a function, a plane with one dimension fewer than the number of input attributes. A soft margin hyperplane uses cost instead of a hard condition on the margin, using a hinge loss function for a hyperplane. Hinge loss refers to a function that trains maximum margin classifiers for SVMs. It works by counting how many points don't meet the condition and generating cost based on the sum of the distances for incorrect points to the margin. Then we find the SVM with the smallest hinge loss. In the kernel method for SVMs, the SVM deals with this data by adding dimensions to the data, and this is accomplished by adding features. Common types of kernels for SVMs include the kernel function, a function that transforms an input vector's attributes; the linear kernel, which transforms the data using a linear function; the polynomial kernel, which transforms the data using a polynomial function like squaring numbers; and the radial basis function, or RBF kernel, a Gaussian function and one of the more popular functions for support vector machine classification. In this video, I'll demonstrate how to use scikit-learn to train a support vector machine in Python. Support vector machines, or SVMs, classify data into binary classes, and a hyperplane is a function, a plane with one dimension fewer than the number of input attributes. A soft margin hyperplane uses cost instead of a hard condition on the margin, using a hinge loss function for a hyperplane. And hinge loss refers to a function that trains maximum margin classifiers for SVMs. It works by counting how many points don't meet the condition and generating cost based on the sum of the distances for incorrect points to the margin. Then we find the SVM with the smallest hinge loss. Now, this scikit tutorial contains examples of SVM implementation in Python, and I encourage you to explore it further, but I'll just demonstrate some of the code here. So I'll bring up the console. Now first, we'll start by importing two arrays. X is our training set of size n samples and n features, and array Y is class labels of size and samples. So I'll start by doing the import first from sklearn, import svm, and then our array x, 0, 0. Just do a simple one here, 1, 1. Y equals 0, 1. So again, x is our training set of size and samples and features, and array y is the class labels of size and samples. Okay, so I'll create a variable object here for this, the svm dot svc, and then this clf.fit. Now here what we're going to do is fit x and y, our two arrays, and we'll get some feedback there about that. Now next what we're going to do is predict new values. So we use clf, that object that we created, predict, and 2 point, 2 point, there we go. Okay, and we get our feedback there, array 1. Now we're going to get the support vectors. So clf.support underscore vectors. Okay, there you go. Everything's laid out for us. Now you can use support underscore to obtain index values of support vectors like this, clf.support. Okay, those are the index values of our support vectors. And end support obtains the amount of support vectors for classes. So like this. Nope. N underscore. There we go. Okay, so I did something wrong there. Oh, right. Bring that back. Didn't need that twice. Okay, there you go. In this video, I'll discuss naive Bayes classifiers. Bayes' theorem is a popular method in probability theory that tries to define the probability of events by using a previously established understanding about factors relating to those events. If thunder and lightning are directly linked to rain, for example, then Bayes' theorem can be used to better and more accurately predict the probability of thunder and lightning by determining if it will rain. In this example, the theorem is used to predict the probability that an email message is spam. The naive Bayes uses a naive assumption, that is, the naive Bayes classifier assumes that all features are independent of each other. For example, in message classifying, the word order doesn't matter, so naive Bayes would treat David buys a potato the same way as potato buys a David. In text or document classification, we classify items that make them easier to recognize and parse, and the naive Bayes classification is a common method for classifying text by assuming that all features are independent of each other. Document refers to the piece of text that acts as input, and it can be anything, a plain text file, an email, a tweet, whatever. The naive Bayes classification acts on the probability P that a document is of class C. The naive Bayes calculates the conditional probability P, C given D for each class and picks the highest, given a maximum a posteriori estimation, that is, an estimate based on previous knowledge or experience, and an estimated probability. P, C given D can be thought of as evidence, and you always go with the class with the most evidence. Computationally, multiplying many small numbers can lead to floating point errors. So a log probability is used with the identity log AB equals log A plus log B. And estimating class probability is relatively simple using this equation. Estimating term probability can be achieved using this other equation. If a term never occurs in a class, 0 will be returned, and log 0 doesn't compute. A solution is to add 1 to every term count, as demonstrated by this equation. In this video, I'll demonstrate how to use scikit-learn to fit a naive Bayes classifier in Python. Bayes' theorem is a popular method in probability theory that tries to define the probability of events by using a previously established understanding about factors relating to those events. If thunder and lightning are directly linked to rain, for example, then Bayes' theorem can be used to better and more accurately predict the probability of thunder and lightning by determining if it's going to rain. In this example, the naive Bayes uses a naive assumption. That is, the naive Bayes classifier assumes that all features are independent of each other. For example, in message classifying, the word order doesn't matter, so naive Bayes would treat Bill eats a hot dog the same way it would treat hot dog eats the bill. So you get the idea. Now, this scikit tutorial contains the examples of naive Bayes implementation in Python, and I encourage you to explore it further, but I'll just demonstrate some of the code here, and I'll start by bringing up the console. Okay, I'll start by importing the Python NumPy library, which contains a number of processing functions for arrays. Import NumPy as NP, that's the object we're going to call it. Now I'm going to create NumPy objects x and y. I'll start with x. So x equals np.random.randint 5 size equals, and in parentheses 6 comma 100. Close those parentheses. All right. Now random.randint is a random number generation method, so we're going to create a matrix of 6 arrays of random integers between 0 and 4. Let's take a look. Okay, there are our arrays. Next, I'll create the array y, which contains 6 values from 1 to 6. So y equals np array 1, 2, 3, 4, 5, and 6. That looks pretty good. All right. Now we're going to use scikit-learn's naive Bayes function and import multinomial NB, which is scikit-learn's naive Bayes algorithm for multinomial data. So it looks like this: sklearn dot naive Bayes import multinomial NB. And then we'll create a variable object from the multinomial function. So we'll call the object CLF equals multinomial NB with opening and closing parentheses afterward. Now let's fit the naive Bayes classifier. So CLF.fit x comma y in parentheses. Okay, great. So we get some feedback there, and now we can display our naive Bayes classifier using the print command. So print clf.predict x 2 to 3. Close these. Okay, so there you go. We get our final value. That's our naive Bayes classifier. Now that you've learned about supervised learning models, it's time to put some of that knowledge to work. In this exercise, you'll describe supervised learning models in Python. You'll describe classification versus regression, describe the logistic regression model, and describe SVMs and hyperplanes. At this point, you can pause this video and perform the exercise. Once you're finished, resume the video and see how I would do it. So let's perform these tasks. It's okay if you didn't do it exactly the same way. First, describe classification versus regression. Well, classification maps input into a finite set of classes, and to drill down a bit, binary classification refers to mapping input for 2 classes, i.e. yes or no questions, and multi-class classification refers to mapping input for more than 2 classes. As for regression, it refers to mapping input to a numerical value. Next, describe the logistic regression model. Well, first, it's the regression model used for classification. The logistic regression model estimates the probability of an input belonging to a class and outputs a binary answer. And this is how the model is represented. Finally, describe support vector machines and hyperplanes. Well, first, SVMs try to build a hyperplane to separate data. And hyperplanes are planes with one dimension fewer than the number of input attributes. I hope you found this exercise helpful. In this video, I'll discuss rule association and the a priori algorithm. Association rules are correlations and relationships between variables in a dataset. Rule association is a method used in machine learning that detects association rules. For example, given the problem, what items are usually bought together at a grocery store, possible rules could be hummus and carrots, steak and potatoes, or bread and butter. A priori knowledge is knowledge of prior conditions relating to a problem. An item set is how many items are associated together. For example, a 2-item set might be carrots and hummus, and a 3-item set might be flour, eggs, and milk. Required components for a priori knowledge relies on several things. Item set size, that is, what size item sets we are looking for. Support, how frequent an item has to occur in order to be significant, including item set occurrences or transaction count. And confidence, which is the probability of getting an item if there is another item from the item set. In an a priori algorithm, there are 3 main steps. First, a join process that finds all 1-item sets. Then, pruning occurs, removing all 1-item sets that don't satisfy support and confidence. And then steps 1 and 2 are repeated for 2-item sets, 3-item sets, and so on until the predefined size is reached. In this video, I'll demonstrate how to use the a priori algorithm for rule association in Python. A priori knowledge is knowledge of prior conditions relating to a problem. An item set is how many items are associated together. For example, a 2-item set might be bacon and eggs, and a 3-item set might be flour, eggs, and baking soda. Required components for a priori knowledge rely on several things. Item set size, that is, what size item sets are we looking for. Support, how frequent an item set has to occur in order to be significant, including item set occurrences or transaction count. And confidence, which is the probability of getting an item if there is another item from an item set. In an a priori algorithm, there are 3 main steps. First, a join process that finds all 1-item sets. And then pruning occurs, removing all 1-item sets that don't satisfy support and confidence. And then steps 1 and 2 are repeated for 2-item sets, 3-item sets, 4-item sets, and so on until the predefined size is reached. So let's see that in action. The a priori module can be found on this website, and there's some useful information here about the implementation. You can download the module here as well. You just go ahead and click that, and that will download the module. You extract it, and then you place the files. Now, I'll discuss briefly how to install it and then demonstrate its basic usage. To install a priori, either run the Python setup script that's included or put a priori PI in your project folder. So you can place the entire folder, which comes with samples, in the Python lib folder and run the install, or simply place the a priori.py file in the lib folder. So here's a simple example, and you can find this and others on the Python site. I'll start by importing it, a priori. Import a priori. Transactions equals, and I'm going to do some enters here just like the example on the site does, just to make this easier to read. Use their example of beer and nuts because I like beer and nuts, comma, and then beer again, and this time cheese, comma, and then close that bracket. Oh, there we go. Okay. Now, results. We'll just create a variable here equals list a priori transactions, And let's take a look at the process data based on the algorithm. So we'll just print results. Print results. Okay, so this is the a priori algorithm in play, and you can see the data generated there. In this video, I'll discuss clustering algorithms. Clustering algorithms group data into clusters. Clusters help identify patterns and potential classes. There are several types of clustering, primarily hierarchical clustering, which builds a hierarchy of clusters. This process is similar to decision trees, which also use hierarchies. Centroid clusters build clusters based on centroids, a centroid being the point at the center of a cluster. Classification happens by finding the nearest centroid. Distribution clustering builds clusters based on probability distributions. For example, each cluster is a normal distribution. Classification is performed by finding the most probable cluster. And density clustering is where clusters are regions with a high density of points, and points outside of regions are just regarded as noise. Here are some example problems for clustering. First, grouping images and other sensory data. Clustering is often used for facial recognition. For example, if a picture looks like person X's other pictures, it might be a picture of person X. In biology, where clustering can describe genetic data, and in recommendation systems, for example, movies can be clustered for similarities, maybe a similar genre, common actor, or some other linkage, and a system can recommend other members of that cluster to users. In this video, I'll discuss the k-means clustering algorithm. In k-means clustering, k-means is a centroid-based clustering algorithm, with k-means finding k-centroids or k-clusters, and centroids being the center or mean of a cluster. A major benefit of k-means is that it's fast and simple, meaning it can be used for rapid prototyping. It can try different values of k quickly, it can try different initial centroids quickly, and it can be used as pre-processing for a more complex clustering algorithm. In the k-means algorithm, k-centroids are initialized either with random or user-defined positions. Then each example is classified using the centroids by finding the closest cluster. All the centroids are moved by taking the average of a cluster's members. All memberships are updated with the new centroids. And steps 3 to 4 are repeated until convergence, a term referring to the state where variables have a statistically insignificant difference, occurs. When centroids stop moving, stabilization has occurred. Inertia refers to the sum of squares inside a cluster. K-means tries to minimize inertia. This limits the patterns k-means can detect. For example, if ideal clusters are long lines of data, k-means won't return them. K-means suffers from other issues too. It's sensitive to outliers, and initial clusters can greatly affect the end results. In this video, I'll discuss how to use scikit-learn to build clusters in Python. In k-means clustering, k-means is a centroid-based clustering algorithm. K-means finding k-centroids or k-clusters, centroids being the center or mean of a cluster. A major benefit of k-means is that it's fast and simple, meaning it can be used for rapid prototyping. It can try different values of k quickly, it can try different initial centroids quickly, and it can be used as pre-processing for a more complex clustering algorithm. Now, this scikit-learn example demonstrates k-means clustering on handwritten digits, and there's some useful information here about the implementation. I urge you to explore this page and the included code, but I'm going to demonstrate it right here. Okay, so here's the code. There's a lot here, and the site gets into a bit of detail about it, but the example compares the various strategies for k-means that affect quality or runtime. I'm going to go ahead and run it. Okay, so there you have it. The generated tables provide us with performance on k-means. On k-means, ++, random, and PCA based, and the graph shows the k-means clustering on the data set with centroids identified by the white X's. In this video, I'll discuss anomaly detection. In data analysis, anomaly detection is a method for detecting irregular items and patterns in datasets. For example, it can be used in fraud detection or network breaches. Similar problems include novelty detection, the detection of new patterns that weren't previously observed. For example, an e-commerce site might detect interest in a certain product because the product is particularly popular during a certain holiday. And noise reduction refers to the identification of noise in a data set and removing it. There are some simple statistics methods that can be used in the training of data. If the occurrence of a point is unlikely according to a distribution, it can be flagged as an anomaly. For example, if the data has a normal Gaussian distribution, 99.7% of the data is within 3 standard deviations. If a point is farther than that, it's flagged. The central limit theorem, CLT, makes this useful because big samples of random independent variables will be distributed normally. And time series data can use a sliding window. Time series can have different normal states at different times. For example, a network update that occurs every second, and the mean of the data can be used from the past hour to detect anomalies. In the local outlier factor, an object's local density is found by using k nearest neighbor to find neighbors. An object's local density is the distance to neighbors. It can calculate the local density of neighbors and compare the local density of all objects and group objects with similar densities. Objects that have lower local densities are said to be anomalies. Other methods include clustering because most points fall inside of clusters, and points that are too far from clusters are marked as anomalies. And support vector machine learns the boundary between normal and outlier data, and objects outside the boundary are said to be anomalies. In this video, I'll discuss how to use scikit-learn to perform anomaly detection. In data analysis, anomaly detection is a method for detecting irregular items and patterns in data sets. For example, it can be used in fraud detection or network breaches. Similar problems include novelty detection, the detection of new patterns that weren't previously observed. For example, an e-commerce site might detect interest in a certain product because the product is popular during the holidays. And noise reduction refers to the identification of noise in a data set and removing it. Now, there are some simple statistics methods that can be used in the training of data. If the occurrence of a point is unlikely according to a distribution, it can be flagged as an anomaly. For example, if the data has a normal Gaussian distribution, 99.7% of the data is within 3 standard deviations. If a point is farther than that, it's flagged. The central limit theorem, or CLT, makes this useful because big samples of random independent variables will be distributed normally. And time series data can use a sliding window. Time series can have different normal states at different times. For example, a network update that occurs every second, and the mean of the data can be used from the past hour to detect anomalies. Now, this scikit-learn example demonstrates the local outlier factor, or LOF estimator. I urge you to explore this page and the included code. Now, in order to use it, you'll need to install the local outlier factor module, which is found here. So you go ahead and click source, and that'll give you the source code, which you can copy and install into your Python instance, and all the various syntax for the module is found on this page. In this video, I'll discuss the problems with dimensionality and why it's important to reduce dimensionality. The curse of dimensionality refers to problems caused from data with many attributes. It involves longer processing time, and it's more difficult to explore variables manually. There's also a higher chance of having collinear attributes, collinear being when an attribute can predict another, for example, width, height, and area. Collinearity can affect model learning performance. Dimensionality reduction refers to a set of techniques to eliminate the number of dimensions in a data set. It's considered as an unsupervised learning technique where algorithms must learn what attributes to remove or transform. This method reduces storage needs, and it reduces collinearity, which increases performance. Dimensionality reduction can also make data easier to visualize. Dimensionality reduction methods include missing values in a dataset, which typically has two solutions. First, a small proportion of missing values can be artificially filled in or predicted, and a large proportion of missing values have attributes that can be removed. In low variance attributes have less predictive power. For example, an attribute that has the same value for each example has no predictive value, and the attribute can be removed. Other dimensionality reduction methods include decision trees. Decision tree learning algorithms rank the most important attributes and prune useless attributes, and they can be used to decide what attributes to remove. Then there's high correlation attributes, which cause collinearity. In such situations, a correlation matrix can be used to evaluate the correlation between attributes. In this video, I'll discuss principal component analysis and how it's used for dimensionality reduction. In statistical analysis, principal component analysis, or PCA, is a dimensionality reduction method. It transforms correlated data into principal components, which are variables that may be correlated and are transformed to be uncorrelated. This helps emphasize the predictive patterns of a dataset. PCA returns the principal components in order of their variance. So, for example, the first component has the highest variance, and this can be used to eliminate even more dimensions. At a high level, PCA takes the raw input data and reduces the dimensionality for X and for Y. By doing so, a similar variance can be detected for the datasets. Linearity can also be accomplished with PCA by mapping the data to a different axis. So here the axes PC1 and PC2 are introduced. Then the data can be normalized on a linear scale to remove the correlation. By eliminating dimensions, the data's variance can be analyzed. Here the data points on axis PC1 indicates a high variance, and the data points on axis PC2 indicate a low variance, which can be eliminated. In this video, I'll discuss how to use scikit-learn to perform dimensionality reduction. In statistical analysis, principal component analysis, or PCA, is a dimensionality reduction technique. It transforms correlated data into principal components, which are variables that may be correlated and are transformed to be uncorrelated. It helps emphasize the predictive patterns of a dataset. PCA returns the principal components in order of their variance, so the first component has the highest variance, and this can be used to eliminate even more dimensions. Now, at a high level, PCA takes the raw input data and reduces the dimensionality for X and Y. By doing so, a similar variance can be detected for the dataset. Linearity can also be accomplished with PCA by mapping the data to a different axis. Then the data can be normalized on a linear scale to remove the correlation. By eliminating dimensions, the data's variance can be analyzed. Now, this scikit-learn page explains PCA in detail, and there's some useful information here about the implementation. I urge you to explore this page in the included code, but I'll just demonstrate one of the examples here. So I'll bring up the console. Okay, so we start by importing NumPy as NP. We'll call it NP. And then from sklearn dot decomposition import PCA. Capital letters, that's kind of important. X equals np dot array. So we'll create an array here. -1, comma, -1. Use the same values as the example. -2, comma, -1. -3, comma, -2. And our positive values 1, comma, 1. 2, comma, 1. and 3, 2. Okay, now we're going to create a variable object called PCA lowercase equals PCA uppercase. N underscore components equals, and we'll set that at 2 per the example. And now we're going to fit it. So PCA.fit, and then in parenthesis X. Okay, so we get some feedback there for PCA, and now let's go ahead and print this PCA explained variance ratio. And there you go. Now that you learned about unsupervised learning, it's time to put some of that knowledge to work. In this exercise, you'll describe unsupervised learning. First, you'll describe the 3 steps of the a priori algorithm. Then describe clusters and the clustering algorithm. And then explain k-means clustering. At this point, you can pause this video and perform the exercise. Once you're finished, resume the video and see how I would do it. So let's perform these tasks. It's all right if you didn't do it exactly the same way. First, describe the 3 steps of the a priori algorithm. Okay, the first step is to join by finding all 1 item sets. The second step is to prune by removing all 1 item sets that don't satisfy the support and confidence. And the third step is recursive, repeating steps 1 and 2 for 2 item sets, 3 item sets, and so on until you reach the predefined size. Next, describe clusters and the clustering algorithm. Well, clusters help identify patterns and potential classes, and the clustering algorithm groups data into clusters. Finally, explain k-means clustering. Well, k-means is a centroid-based clustering algorithm. It finds k-centroids, k-clusters, and centroids are the center mean of a cluster. And k-means is fast and simple, meaning it allows for rapid prototyping. It can try different values of k quickly. It can try different initial centroids quickly, and it can be used as pre-processing for a more complex clustering algorithm. I hope you found this exercise helpful. In this video, I'll discuss how neural networks are structured. Neural networks are machine learning models inspired by the biological layout of human brains. They contain many connected units which mimic the way neurons are laid out in the brain, and data is fed through units. Each unit performs a task on the data. For example, it could round, decide if something is positive or negative, and so on. This is a graphical representation of what a single unit, a neuron if you will, of a neural network looks like. They're known as perceptrons. Perceptrons are units in neural networks that can be trained through supervised learning. The unit has an input on the left and output on the right, and in between there are computational processes occurring that use attributes, bias, weights, and other computations used in the decision-making process. For computational efficiency and ease of understanding, neural network units are usually represented as vectors and matrices. There is a single unit representation with 3 inputs and 1 output, a vector representation, and a simple representation. And this diagram illustrates the relationship between multiple units. Remember, a unit is essentially analogous to a neuron. And neural networks are many connected units, just like neurons are connected in the human brain. And they mimic the way neurons interact, with data fed through units and each unit performing a task on the data being inputted. Each unit provides a single output. Because neurons aren't laid out in a 2D space, neural networks are created in layers. This is a basic representation of a multi-layered neural network where units are separated by layers, typically starting with a neural network layer, a group of unconnected units that are connected to units in other layers. The input layer takes the neural network's input in multiple input units, typically in the form of a vector. Each input unit deals with a different attribute. The output layer is the final layer of the network and is responsible for providing the answer to a question. Often there are multiple output units which require some sort of transformation before giving an answer. Hidden layers are any layer between the input and output layers. Hidden layers don't receive outputs from the network, but are used to prepare information from the preceding layer and massage it into a format that the next layer can use. In this video, I'll discuss how cost functions are used to train neural networks. In neural network design, cost functions determine costs, or grades if you will, for how well a network performed in its decision process. Simply put, it's a way of incentivizing a neural network to make better and ultimately the correct decisions. Now, correct is entirely subjective, and in the real world, decisions aren't always based on absolute inputs. It would be nice if everything in life was a binary choice, but that's not the way things work, and so neural networks use cost functions. So a neural network cost for a single example would look like this. Remember, examples or training examples are prior data based on good decisions. So in a chess match, moving your king into an area that's protected by pieces that can't be taken by the opponent would be a good example. There's also a cost function for all examples, that is, the entire group of examples a neural network has to work with. There are conditions for neural network cost functions. They must be some form of average, taking all inputs into account, and this yields better gradients when running the gradient descent algorithm. And they should only depend on the output and not any hidden activation. Backpropagation, which is used to make neural network weight updates, wouldn't work otherwise. Mean squared error, or MSE, is represented by these functions and calculates how much error a model has. That is, how many classifications are wrong. Cross-entropy function is used to compute the amount of error based on activation to show how far you are from being correct. It not only counts the number of misclassifications, but it also indicates if the distance of error is close or far, and it's generally an improvement on mean squared error, which doesn't indicate how far a model is from being correct. Mean squared error with weight decay uses regularization, that is, methods to punish potential overfitting. The weight decay term is a regularization term, and the weight decay value is how strong a case is to use weight decay compared to mean squared error for cost. In this video, I'll discuss activation functions and common types of activation functions. In computing, activation functions are used to determine the output based on inputs. A simple example would be the true or false paradigm of Boolean logic. In neural networks, perceptrons are algorithms that represent a single true or false decision, and they are known as linear classifiers forming a chain of true or false determinations. So after calculating a value, the activation transforms that value for output. Why are the activation functions needed? Well, the function is a linear relationship, and if you only consider linear relationships, a model won't explore potentially better relationships. Therefore, activation functions give a model the potential to learn complex relationships. Here we can compare identity and binary functions. The identity function always returns the value used in its arguments and results in no activation. You can see how this is plotted as a linear relationship on a graph. Likewise, binary functions, which accept two arguments, represent a similar problem. These issues can be rectified with activation functions like sigmoid functions, which map a probability and employ logistic regression, and tanh functions, which, if transformed, are similar to sigmoid functions. Rectified linear unit, or ReLU, is a popular activation model for convolutional networks. It's commonly used for computer vision implementations, and it allows for fast training. In this video, I'll discuss feed-forward neural networks and the intuition behind calculating gradients in neural networks. Feed-forward neural networks have information traveling in one direction only, so fed-forward, and single-layered feed-forward neural networks, also known as perceptron networks, process information in from the front and spit out information at the back. So input and output, which is no surprise. And in this network paradigm, all inputs are directly connected to its outputs. Perceptrons have two input units and one output unit, and just like computer processing technology, this layout can be mapped to the logic gate paradigm. Each set of units can be thought of as a gate. It's called a single-layer network because often neural networks are multi-layered and this one isn't. It's a simple single-layered paradigm. Feed-forward neural networks are trained using supervised learning, so information is fed to them by providing pairs of data input for each cell and letting them develop solutions. Single-layer models are not computationally complex enough to solve anything more than simple problems, and the single-layer model is the earliest neural network design, dating back to the 1950s. Feed-forward networks are typically arranged in layers because neural networks model after the human brain, and brains are three-dimensional. Layers allow neural networks to compute more complex problems. In layered models, units receive their input as output from the layer directly before it. So here we have a feed-forward pass example with two inputs coming in on layer 1 and two outputs on layer 5. In multi-layered neural networks, each unit in a layer has a connection to units in the preceding layer. Layers containing hidden units are employed as demonstrated by the light blue nodes here. The hidden units sit between layers and don't receive outputs from the network, but are used to prepare the information from the preceding layer and put it in a format that the next layer can use. Deep feed-forward neural networks are very popular because of their deep learning capabilities, and they're widely used in a number of commercial applications. Gradient descent is an algorithm that determines a function's minimum. It's called gradient descent because it steps down like gradients, with steps being proportionate. In gradient descent with neural networks, the mean squared error cost function is recalled with weight decay. During updates, gradients need to be determined using these functions. And gradients can be computed using these formulas. In this video, I'll discuss backpropagation and how it can be used for more efficient neural network training. Backpropagation for neural network training determines the amount of error that each node adds to data using gradient descent. In backpropagation, all weights are initialized first. They should be initialized using small random values, and if all weights are the same, they remain the same when updating occurs. Then a feed-forward pass is performed, and all the activations are saved. Error terms are calculated. Error term is an estimation of how much a node participates in overall error. Next, the error term for the output layer is calculated using this algorithm. Then, going from layer NL minus 1 down to layer 2, all the error terms are calculated using this method. Then, gradients are updated. This can easily be calculated using error terms. And steps 2 to 5 occur until convergence, a term that refers to the point when distance between data becomes statistically small, occurs. Derivatives also need to be implemented. This is required for backpropagation. These can be implemented beforehand using sigmoid and rectified linear unit or ReLU functions. In this video, I'll discuss batch learning and why it's desirable. In machine learning, iterating with a full data set is often impossible. There's either not enough memory, unreasonable amounts of time required for processing, or both. This is where batch learning comes in. A mini-batch is a small subset of a data set. In batch learning, each iteration uses a mini-batch to update gradients. The resulting performance is similar to using a full data set, and it's a lot faster than using a full data set. The stochastic gradient descent method is used in batch learning to estimate the expected cost of using a small subset of a training set. Weights are then updated using the estimated cost. When employing stochastic gradient descent, there are some important considerations. First, the learning rate should be much smaller. Mini-batches can have a great amount of variance, which leads to more drastic updates. And the order of the data should be randomized. Think of it as shuffling. The reason for this is that if mini-batches always arrive in the same order, then the model would be biased for the learning process. In this video, I'll discuss TensorFlow and provide a high-level overview of its architecture. TensorFlow is a flexible machine learning library developed by Google Brain. It can easily be configured and scaled to different hardware configurations. For example, you can use CPUs, or if you really want to amp up processing power, you can introduce GPUs. TensorFlow's numerical operations are executed on a data flow graph, with each node representing an operation and edges representing values. Tensors are TensorFlow's base object. They are an n-dimensional array, for example, scalar, vector, matrix, or cube. Rank refers to the number of dimensions. Tensor shape is represented by elements per dimension, like this example, which illustrates how a 2x2 matrix is represented. Variables in TensorFlow are tensors that can be modified when a session is running, for example, weights, which influence how decisions are made. In TensorFlow, computations run on data flow graphs. Graphs are defined by operations and edges, operations meaning graph nodes and tensors meaning graph edges. And programs interact with graphs by creating sessions. In this video, I'll discuss how to set up TensorFlow for use on a CPU. There are two kinds of TensorFlow installations, and you should be aware of which one you need before you install it. Choose TensorFlow for CPUs if you plan on just using CPUs. The two installations, this one is a simpler install that takes about 10 minutes. Now, the other version is TensorFlow for GPUs, and if you have a CUDA-enabled NVIDIA GPU in your system, you can choose this one. TensorFlow is going to perform much faster with the GPU, and if you need some serious machine learning power, this is the one to choose. If you plan on using a GPU but don't need that support right away, you can go ahead and install the CPU-only version first, and then migrate to the GPU version later. Now, you can find out more on this page, and once you've determined which version you need, you can install it using either pip or Anaconda. I'll use pip, but the Anaconda install is similar. Now, you can do it from a DOS prompt or PowerShell. I want to run this in the scripts directory of my Python because I've discovered some issues when trying to do this from other locations, even though the path has been set in environment variables. Okay, I'll start by holding down Shift, right-click on the scripts directory, and select Open PowerShell window here. Now, the first thing I want to do is make sure that I have Python setup tools installed. This will protect you from potential errors when you're installing TensorFlow. You may need easy setup as well, but let's just go ahead and do this. I think I already have easy setup. Install, upgrade, setup tools. Okay, now we can install TensorFlow. So you use pip install and then -- upgrade TensorFlow. Now this is going to require a live internet connection, so just be aware of that. And the install can take a while, and the install can take about 10 minutes, depending on how fast your connection is and how fast your system is. So it'll just go ahead and run, and once it's finished, you're ready to work with TensorFlow. Yeah, I don't think we need to take them through the entire install here. It's just some verbiage here. I may pause it. Oh, wait a second. Okay. Let me just pause this and come back when it's done. In this video, I'll demonstrate how to import TensorFlow and demonstrate a few basic TensorFlow commands. Tensors are TensorFlow's base objects, and they're represented as n-dimensional arrays. Now, this Getting Started guide is a really useful site that has a bunch of information about TensorFlow, and it offers some helpful ways to begin working with TensorFlow. I'll demonstrate a bit of it here, but you really should go through the various tutorials and the information here because it's a good jumping point for working with TensorFlow. Now, there's a brief overview of the fundamentals of TensorFlow, 3 guides for training a MNIST, or Modified National Institute of Standards and Technology database model. There are guides for working with the TensorFlow high-level API and guides for TensorBoard, which is a utility for machine learning visualization. So let's go ahead and take a look at the Getting Started guide. Now what I want to do is just open my Python instance, and Now this lays it out for you, but what I'm going to do is just demonstrate a bit of the initial code here. So I'll bring up my Python instance. And we'll start by importing TensorFlow as TF. So we're going to call it TF. Now we'll create a computational graph, which is a collection of TensorFlow operations laid out in graphs. In those graphs, nodes are plotted, and every node takes as inputs 0 or more tensors. We'll create constants which receive no inputs and output internal stored values. So I'll start with node 1 equals, and remember we called TensorFlow TF, so TF.constant 3.0 dtype equals TF, and again this is a constant. It's going to be a 32-bit integer. It's going to be a 32-bit floating point number. And then node 2 equals TF.constant. Make this 4.0. Now, all I'm going to do is just display node 1 and node 2. So print node 1 and then node 2. Okay. Now in this output you may notice that displaying the nodes doesn't provide the values 3.0 and 4.0, and that's because they're nodes that would result in 3.0 and 4.0 when evaluated by creating a computational graph inside a session. So let's go ahead and do that. So I'll create a variable called SESS, or for session, equals TF dot, and there it is, session with a capital S, open closing parenthesis. Now this is okay. These lines of feedback can be ignored. TensorFlow is merely letting you know that TensorFlow can be faster if you build it from source. So you can disable this feedback if it's irritating you, but we're not going to care about it. We're just going to let it go. Now I'll show you one more command. This is just printing the session.run, and we want to see node 1 and node 2. And I missed a parenthesis there, so let's put the closing parenthesis. And what am I missing here? Let me just get out of that. Okay. Let me just bring this back. I obviously mistyped there, so ses.run. And then, okay, I see what I did. There we go. Node 1, node 2, closing bracket, and then 2 closing parentheses like that. And there we go. Okay, and there's the output we expected. In this video, I'll demonstrate the implementation and training of a single layer neural network in TensorFlow. Now, when you're getting started with Python and machine learning and working with TensorFlow, there's plenty of great resources out there, tons of tutorials, tons of sample codes, and GitHub, of course, is always going to be a great resource for that. So, here's an example of the implementation and training of a single layer neural network in TensorFlow. It's a logistic regression example, and I highly recommend you go and check this out. The author has created this code, and you can see it there. Now, it's not very long, but the idea is that this example is going to use the MNIST database of handwritten digits. So if I go ahead and click this link, okay, this will give us some more information on the MNIST database of handwritten digits. And this just provides a way of taking actual handwritten digits, an image, and then analyzing them and turning them into characters. Now, the logistic regression example is going to provide us with some feedback after it's done. It's going to create random weights and calculate. It's going to create random weights and optimize the database in preparation for recognizing the characters. So let's go ahead and take a look. Now I've taken that code and placed it in a Python script in Spyder, and the author has provided some helpful information in the form of comments throughout the code, so I recommend that you go to the author's site on GitHub and check that out. But basically it begins by importing MNIST. It begins by importing MNIST data. That's the actual character recognition data in the form of an image file. It establishes parameters, sets TensorFlow's graph input, sets model weights, constructs a model, minimizes error using cross entropy, and initializes variables. Then a training cycle is implemented, and when optimization is complete, the accuracy for 3,000 examples is calculated. So let's go ahead and just run it and see what the output looks like. Now, as you can see, it's estimating the costs. And this will take a few seconds. And there we go. The optimization is finished with an accuracy of approximately 89%. In this video, I'll demonstrate code that implements and trains a multiple layer neural network in TensorFlow. Now, here's an example of a connected neural network using 2 layers with TensorFlow. This is some code that's been placed on GitHub. It's a great resource for finding code that you can work with when you're starting to work with Python, machine learning, and TensorFlow. Now, this is known as a multi-layer perceptron. The example uses MNIST handwriting digits with a data set that has 60,000 examples for training and 10,000 examples for testing. You can see it right there, the image for the handwriting sample. And digits have been sized, normalized, and centered in a 28 by 28 pixel image with values between 0 and 1. So you can check out the entire code here, but I'll just go ahead and demonstrate this in Python. I've actually taken the code and placed it here. Once again, you can find more information about the code on the GitHub site. And the author has put in some useful comments in here that help. And the author has put some useful comments in here that helps us understand what's being done. It imports the MNIST data, sets parameters and graph input, stores weight and bias for layers, creates the model and constructs it, and then trains the network. Now, after optimization is complete, the testing accuracy will be displayed. So let's go ahead and just run it to see what the output looks like. Okay, there you go. It ran pretty quickly. The optimization is finished with a testing accuracy of approximately 88%. Now that you've learned about neural networks, it's time to put some of that knowledge to work. In this exercise, you'll describe neural networks. You'll explain the 4 neural network layers. You'll describe conditions for neural network cost functions. You'll explain why activation functions are needed. And you'll list considerations for stochastic gradient descent. At this point, you can pause this video and perform the exercise. Once you're finished, resume the video and see how I would do it. So let's answer these questions. It's okay if you didn't do it exactly the same way. First, explain the 4 neural network layers. Well, first, there's the neural network layer, the input layer, the output layer, and the hidden layer. Next, describe conditions for neural network cost functions. First, they must be some form of average and take all inputs into account. This yields better gradients when running the gradient descent algorithm. Also, they should only depend on the output and not any hidden activation. Backpropagation used to make neural network weight updates wouldn't work otherwise. Next, explain why activation functions are needed. So after calculating this formula, activation transforms that value for output. And this is a linear relationship. So if you only consider linear relationships, the model won't explore potentially better relationships. Also, activation functions give the model the potential to learn complex relationships. Finally, list the considerations for stochastic gradient descent. Well, first, the learning rate should be much smaller. Many batches can have a great amount of variance, and that leads to more drastic updates. In addition, the order of the data should be randomized or shuffled. If many batches always come in the same order, the model would be biased during the learning process. I hope you found this exercise helpful. In this video, I'll discuss the high-level architecture of convolutional neural networks. In the convolutional neural network, there are several layers, beginning with the input layer, and here there are 4 inputs. Then there's the convolutional layer or layers, the rectified linear unit activation layer, pooling layers or layers for downsampling, and the fully connected layer or layers. Then the softmax layer, which normalizes the data, is next. So let's deal with the architecture terminology. The convolutional layer extracts different features from each part of the image. The filter assigns weights to an area of an image. For example, a 5x5 filter would represent a 5 pixel by 5 pixel selection of the image. The feature map is a new image that's created when the filter is applied to the input. Stride occurs when the filter moves across the image. Think of an imaginary box that surrounds a 5x5 section and moves to the left by 1 pixel at a time when processing is complete. By 1 pixel when processing is complete on the 5x5 section. Stride size is how much to move, so a stride of 1 would move the filter by 1 pixel. Pooling combines variables into one, so for example taking the average value of 4 pixels. LeNet-5 was one of the first convolutional neural networks. It was developed to recognize characters from 32 by 32 images, and the neural network has 7 layers, a convolutional layer with 5x5 filters resulting in 6 28 by 28 feature maps, pooling layers which downsample images to a 14 by 14 feature map, 2 more convolutional layers, and 1 more pooling layer, 1 fully connected layer, and 1 output layer. Here's a visualization of LeNet-5. The input is a 32 by 32 image, like the hand-drawn X here. A convolutional layer with 5x5 filters resulting in 6 28 by 28 feature maps. Pooling layers downsample the image to feature maps. 2 convolutional layers, 1 fully connected layer, and 1 output layer. Then, finally, the softmax layer normalizes the data, and the output is the letter X. In this video, I'll describe how convolution layers are set in convolutional neural networks. In convolutional neural networks, a filter is a set of weights applied to a section of an image. Filters can be visualized as small images, so a 5x5 filter is a filter that's 5 pixels high and 5 pixels wide. A third value represents the color depth, so a 5x5 by 3 filter is a 5x5 pixel filter with 3 color channels. To apply a filter, the dot product of the image and the filter is taken. When building feature maps, stride size is how many pixels to move the filter. A stride of 1, the most popular choice, moves the input by 1 pixel. Think of it as having an imaginary square around a 5x5 area, and then once the processing in that area is complete, you move it 1 pixel to the right. To build a feature map, the output of each filter is taken and an image is built. Then there's the stride size. Filters are neural network units described by this image. To implement strides, the same unit is copied multiple times. Each unit shares the same weights, and each unit outputs part of a feature map. In this video, I'll discuss pooling layers and how they're used in convolutional neural networks. In convolutional neural networks, Pooling reduces the number of parameters in a network. For example, downsampled images, which, when reduced in size, need to have information, that is, pixels, removed. In the convolutional neural network topology, pooling layers are inserted between convolutional layers. The advantages of pooling layers include that they reduce the amount of required computations in memory, and they reduce overfitting. In 2x2 max pooling, for every 2x2 square, the max pixel is returned. A returned image will have 25% of the original pixels, so 75% fewer activations to compute. For example, a 32 by 32 pixel image will be reduced to 16 by 16 pixels. And there are other pooling types. In average pooling, the pixels for downsampling are averaged. In global average pooling, the average of multiple feature maps is taken so they can be combined. In a basic use case, you replace a final fully connected layer by building a feature map for each class, passing all the maps in a global average pooling layer, and then performing softmax on the average map to normalize the data. In this video, I'll discuss some training considerations for convolutional neural networks. Convolutional neural networks are a special type of neural network. A convolutional layer is a neural network layer that isn't connected and includes weight-sharing units. Convolutional neural networks are popular for several kinds of practical applications, including image processing, but they require training, so here are several considerations for training. First, in the pre-processing phase, mean subtraction, where the mean is subtracted from each example, is performed. This centers the data on the origin. Then, normalization occurs, where you divide subtracted data by the standard deviation. This puts all the data on the same scale. Next is zero padding, where you add zeros around the data, for example, adding pixels around an image. If a dataset is split in a training and test dataset, pre-processing should be performed after splitting occurs. Pre-processing also has to be performed on objects you want to predict. When initializing weights can't all be initialized to 0, and they'll always have the same values when updating. Weights can be initialized with small random numbers, but this causes high weight variance. So, to decrease variance, you divide each weight by the square root of the number of inputs. And bias initialization may or may not affect performance. It's typically initialized to 0, but it's sometimes initialized to a big enough number to fire all the rectified linear unit, or ReLU, activations. In CNN training, backpropagation, which determines the amount of error that each node adds to data using gradient descent, can be used. Fully connected layers are trained like normal neural networks. Pooling layers contain no weights, so they don't need training. And convolutional layers are trained like normal neural networks. Since weights are shared, gradients are shared among them. In this video, I'll discuss regularization and how it applies to convolutional neural networks. In neural network design, regularization is a method used to reduce overfitting, a statistical anomaly that occurs when data noise obfuscates any relationship that the data might normally indicate. Regularization punishes models with the potential for overfitting. It uses weight decay, which punishes high weights by decaying them over time. If an outlier causes a spike in weight, it will eventually move towards 0. If a weight truly should be high, many examples will outpace the decay. L1 and L2 regularization are two common methods of regularization. In L1 regularization, the weight decay is represented like this. It encourages small weights, that is, weights close to 0, and small weights make noise less relevant. In L2 regularization, the weight decay is represented this way. It discourages the neural network's dependence on a small subset of inputs. For example, it considers more inputs more equally. Generally speaking, L2 regularization performs better. There are other regularization methods too. Max norm constraint limits the magnitude of a unit's weights, magnitude being represented with this formula. And constraint can be enforced when updating. And dropout randomly skips some of the activation when training a dataset. The probability p can be set as a hyperparameter, so p equals 0.5 is common. And dropout should not be applied when making predictions. In this video, I'll describe regularization of convolutional neural networks. In neural network design, regularization is a method used to reduce overfitting, a statistical anomaly that occurs when data noise obfuscates any relationships that the data might normally indicate. Regularization punishes models with the potential for overfitting. There are several common methods for regularizing CNNs. First, you can modify datasets. By providing more training data, overfitting models may experience better performance. And using a dropout layer, nodes are randomly dropped, including the node's inputs and outputs. In dropout layers, overfitting is reduced, and this is an efficient method for averaging models. Nodes become less affected by other nodes' weights. In early stopping, the number of steps for hyperparameters is tweaked. Early stopping is a regularization method that prevents overfitting with iterative methods like gradient descent. Generally, the learning model is updated so better fitting occurs with training data. And weight penalties for L1 and L2 regularization is a popular method for training models. In weight penalties, the assumption is that models with large weights are not preferable and that models with small weights are less complex. Penalties are applied to keep the weights down. Ideally, no weights at all are preferred. The exception would be if there are large gradients. In this video, I'll describe implementing and training convolutional neural networks. A big challenge with typical neural networks is that they consider an entire input all at once. For applications like image processing, for example, 3 different handwriting samples in different locations and angles would be treated as different inputs, even though they're just the same characters represented in different locations or angles. The solution to this involves pre-processing, which is a powerful but limited in its implementation, or convolutional input, which grabs small portions of an image and looks at just those. Convolutional neural networks are a special type of neural network. A convolutional layer is a neural network layer that isn't connected and includes weight-sharing units. Convolutional neural networks are popular for several kinds of practical applications, but they require training, so there are several considerations. This tutorial on GitHub is a good example of how a convolutional neural network in TensorFlow can be implemented and trained. It implements a CNN with an accuracy nearing 100%, and you can tweak the accuracy by using some of the suggested exercises. In the flowchart section, you can see a visual representation of how the data moves through the convolutional network in this tutorial. An input image of 28 by 28 pixels is taken, and filter weights of 5 by 5 pixels are applied on the convolutional layer 1. 14 by 14 pixel images are filtered on convolutional layer 2 with filter weights of 5 by 5 pixels. 7 by 7 pixel images are output to the fully connected layer with 128 neurons, and after processing sent to the output layer with 10 neurons. From that, classifications are generated, effectively the number contained in the input image, which is 7 in this case. Now, I recommend you try this tutorial out. There's a lot of code here and more than 50 steps in the coding process with some helpful feedback from the author. In this video, I'll discuss recurrent neural networks. Recurrent neural networks address the missing link between human understanding and neural network understanding. A recurrent layer is a layer that feeds output into itself sequentially, with the output from the last iteration used in the next iteration, essentially retaining information. It forms a chain of units that are copies, providing information to successive nodes in the network. So why are recurrent neural networks useful? Well, first, traditional neural networks don't have any memory. They forget after every step. This makes it difficult to use neural networks for time-based or sequential data where past events affect present events, for example, time series, video sequencing, or natural language processing. Here's a neural network example for machine translation, in this example using a neural network to translate the English phrase, "the dog runs," into French. Classification is when there's a finite set of attributes that can be assigned to an item. For example, a pencil can have a color, a weight, a length, a diameter, and so on. A finite set of attributes. But the output can't be weighted as a class because there are infinite classes. That is, language translation is not often a straight one-to-one translation. And the output can't easily be mapped as regression. In other words, the model can't easily learn how wrong it is. In this recurrent neural network example for machine translation, we have RNNs operating to map the translation. It's a fairly simple example because the order of the definite article the subject dog, and the object runs appear in the same order in English and French for this example, but that's rarely the case in plain language translation. So with RNNs, the network can learn grammar rules and word associations using finite classes of words. In this video, I'll describe the different types of recurrent neural networks. There are different types of recurrent neural networks. For example, there's one input to many outputs, that is, describing the input as in this graphic example. There's also many inputs to a single output, as in this graphic example. This is commonly used for tasks like sentiment analysis, where a tweet or a Facebook post would be analyzed and a decision would be made whether the person making the post was happy, sad, angry, frustrated, and so on. In that case, perhaps the input is product comments, where a customer is commenting on a company's product, and the output would be how happy the poster is with the product. In many inputs to many outputs, the input and output can be unsynced. For example, in machine translation from one language to another, where the order of the words is not as important as grammatical rules and meaning. Or they can be synced, for example, identifying and tagging frames in a video, which is a sequential process. When using RNNs for non-sequential input can be taken sequentially to use a recurrent neural network. The input can be used fully for input where features have different meanings depending on other features. For example, images, where you need different items to form a face, a nose, a mouth, eyes, ears, and so on. And recurrent neural networks for images are similar in the way they work, to the way convolutional neural networks work. In this video, I'll discuss how to implement a long short-term memory network. Connecting neural network units recurrently offers limited functionality because a recurrent neural network can only use the output from the last iteration, so they have no true memory. Long short-term memory, or LSTM, networks are recurrent neural networks that can learn relationships over time. Dissolution, add a memory cell. LSTM networks manage a memory cell based on inputs. Weights are used to learn what to forget and what to remember, and weights are also used to learn how to use memory. In the LSTM structure, a cell represents memory. X and plus represent multiply and add gates. A sigmoid is a sigmoid or logistic unit. Tan H is a unit. And T is the current time or iteration. In terms of how LSTM remembers, there are three main steps. First, step 1 deals with how much to remember. A sigmoid returns a number between 0 and 1. This is used as a percentage of what to remember using this function. Step 2 deals with what to add to memory. Tan H extracts information to add using this function. A sigmoid decides the percentage of information to add using this function. And the compiled information is added to the cell. Step 3 builds the output. Tan H extracts information from cells using this formula. The sigmoid decides the percentage of the information to add using this formula. And finally, the output is sent to the subsequent input. In this video, I'll discuss an example for using RNNs and LSTM for language modeling. Recurrent neural networks address the missing link between human understanding and neural network understanding. A recurrent layer is a layer that sequentially feeds output into itself, with the output from the last iteration used in the next one, essentially retaining information. But connecting neural network units recurrently offers limited functionality because RNN networks can only utilize the output from the last iteration, so they don't really have memory. Long short-term memory, or LSTM networks, are recurrent neural networks that can learn relationships over time. They add a memory cell, and LSTM networks manage a memory cell based on inputs. Weights are used to learn what to forget and what to remember, and weights are used to learn how to utilize memory. In the LSTM structure, a cell represents memory. X and plus represent multiply and add gates. Sigmoid is a logistic unit. Tan-H is a unit, and T is the current time or iteration. Now, this tutorial demonstrates the training of a recurrent neural network for language modeling. The goal is to fit a probabilistic model and assign probabilities to sentences. This is accomplished through prediction. What are the subsequent words given history of previous words? The model contains an LSTM layer, and it computes a word at a time and determines probabilities that predict each new word in a sentence. Now the tutorial uses files from the TensorFlow models repository. So click that and then download the zip file here. Once you have the zip file, extract it to the home directory, which in Windows is typically C users and whatever your username is. Then download the PTB dataset from Thomas McAuliffe's webpage and extract that to the home directory. The dataset is a pre-processed set of data with 10,000 different words. Now let's go ahead and take a look at the directory. I've already actually downloaded it and unzipped these. So I'm here in this directory. That's my users, my home directory. We have models master and simple examples. Those are the two folders that we need. Now, I highly recommend you try this yourself and read through the excellent information on this page. But I will demonstrate this and tell you that there are a couple of tweaks that have to be made. First, the code was created for Python 2, and in Python 3, the dictionary attribute iteritems has been changed just to items. So you have to open this file. I'll go ahead and show you. Sorry, let's go back here. It's under Models Master, Tutorials, RNN, and PTB. And there's the file right there. It's ptb_word_lm.py. You open that in a text editor and modify 2 lines. I recommend an editor with line numbers because there are more than 500 lines of code, but you can use search to locate the 2 instances of iteritems and change them to items if you like. Now, second, the code provided by this tutorial may kick back an error if you don't have a GPU. Now, you can fix this by adding num GPUs to this command. Go down here. Let me say that again. Now you can fix this by adding num_GPUs to this command. This system doesn't have a CUDA enabled GPU, so I'll have to use this switch. So let's go ahead and run the code. So once you've got the models repository and PTB dataset extracted in the home directory, open a PowerShell session. Okay, now once you're here, we want to change to the home directory. Now I'm already there, C users Jamie, but in case you want to know how to do that, cd $home in PowerShell. And then we want to change to the directory that contains our code, our script, models master, tutorials, RNN, PTB. And finally, we want to run the Python script. Now, it looks like this: Python ptb underscore word underscore lm.py. I'm going to put a space there and a backtick because I want a multi-line command here. Just make it easier to look at. So you use the backtick right next to the 1 to do that. Press enter. Okay, double dash data underscore path equals $ home slash simple examples slash data, and then a space, double dash model equals small rnn underscore mode. Oops. Sorry. Okay. Going back to this, space, double dash rnn underscore mode equals basic. And here's what I was talking about, the GPUs. Double dash num underscore GPUs equals 0. Okay, so go ahead and press enter. Now, it's going to run, and it's going to take a while. As a matter of fact, quite a long while, because I don't have a GPU on this system. So you really should try to use a GPU. And by the way, these comments are not errors. They're just actually information telling you that there are ways to tweak your CPU if you don't have a GPU to make this run a little bit faster. So I recommend you try out this TensorFlow tutorial yourself and have some fun by tweaking the settings. And I'll just sit back and wait for this to finish. It'll take, as I said, a little while. Now that you've learned about convolutional and recurrent neural networks, it's time to put some of that knowledge to work. In this exercise, you'll describe convolutional neural networks. You'll explain convolutional neural networks, explain common uses for CNNs, describe pooling layers and their advantages, and describe long short-term memory, or LSTM. At this point, you can pause this video and perform the exercise. Once you're finished, resume the video and see how I would do it. So let's answer these questions. It's okay if you didn't do it exactly the same way. First, explain convolutional neural networks. Well, a convolutional layer is a neural network layer that isn't fully connected and has weight-sharing units. Next, explain common uses for CNNs. Well, first, they can be used and are commonly used with image processing as well as audio processing. Next, describe pooling layers and their advantages. Well, pooling reduces the number of parameters in the network, for example, downsampled images. Next, pooling layers are inserted between convolutional layers. And advantages of pooling layers include they reduce the amount of computations and memory needed, and they reduce the risk of overfitting. Finally, describe long short-term memory. Well, connecting neural network units recurrently is limited. The network can only use the last iteration's output, so there's no true memory, if you will. The solution: add a memory cell. LSTM networks manage memory cells based on inputs. Weights are used to learn what to forget and what to remember, and weights are used to learn how to use memory. I hope you found this exercise helpful. In this video, I'll describe how cross-validation is used. When using training, testing, and validation sets in neural networks, using the training sets to test a model leads to overfitting, a statistical anomaly that occurs when data noise obfuscates any relationships that the data might normally indicate. A model can simply remember all inputs to make perfect predictions, but it won't be able to predict different examples correctly. In such scenarios, a test set should be extracted for experimenting. The model can still be overfitted to learn how to be good at predicting only the test set, and an extract validation set is used to mitigate overfitting in a test set. So here's the major issue. Splitting a data set into 3 can make it too small for proper training. Cross-validation, on the other hand, can split a dataset k times, train each dataset, calculate the accuracy for each dataset, and average the metrics over each. This method requires a lot more computations than regular splitting, but it returns much stronger evaluation metrics. In this video, I'll discuss how to perform cross-validation in Python to obtain strong evaluation scores. When you're using training, testing, and validation sets in neural networks, using the training sets to test a model leads to overfitting, which is a statistical anomaly that occurs when data noise obfuscates any relationship that the data might normally indicate. A model can simply remember all inputs to make perfect predictions, but it won't be able to predict different examples correctly. And in such scenarios, a test set should be extracted for experimenting. The model can still be overfitted to learn how to be good at predicting only the test set, and an extract validation set is used to mitigate overfitting in a test set. So here's the issue. Splitting a data set into three can make it too small for proper training. Cross-validation, on the other hand, can split a data set k times, train each data set, calculate the accuracy for each data set, and average the metrics over each. This method requires a lot more computations than regular splitting, but it returns much stronger evaluation metrics. Now, this tutorial provides a good introduction to cross-validation with Python using the train, test, split helper function. It loads iris data and fits it to a linear support vector machine, sampling a training set and holding on to 40% of the data for testing. And it does much more. There's several code samples here and some useful information on how cross-validation is implemented. So I recommend you check this out and try some of these examples so you can better understand cross-validation and how it can be implemented. In this video, I'll discuss different metrics that can be used to evaluate binary classification models. There are different metrics that can be used to evaluate binary classification models. The confusion matrix is a visual method used to represent what kind of errors a model is making. For example, in a binary classification, you can determine the possible outcomes of a simple yes or no answer with a table like this. You begin with a prediction made by a machine learning algorithm, the possible answer being either yes or no, and map that choice against the correct answer, again, yes or no. You're left with four possible outcomes: true positive, false negative, false positive, or true negative. Precision refers to the ratio of correct answers. So in a binary example, we would determine precision by dividing true positives by true positives plus false positives. And recall refers to the ratio of true examples that are correctly identified. So we define recall by dividing true positives by true positives plus false negatives. And F1 score is a metric that considers both precision and recall equally using this formula. F1 equals 1 is the best score, and F1 equals 0 is the worst score. There are alternate F measures. F1 can be generalized to weight precision and recall differently using this formula. Beta less than 1 means precision is more important, and beta greater than 1 means recall is more important. The Matthews correlation coefficient is a balanced coefficient that returns a number between -1 and 1. 1 is a perfect prediction, 0 is a completely random prediction, and -1 is a complete inverse prediction. Balanced refers to the fact that it can still be used when class sizes have a large difference. And the Cohen-Kappa score is a score that compares the model to a random selection with the expectation that accuracy will be attained using this formula. P0 is the model's accuracy when tested. PE is the expected accuracy if random choices were made. And the score is interpreted using the following scale. 0.821 is considered a strong score. 0.2 to 0.6 is considered fair or moderate. 0 to 0.2 is a slight score. And anything less than 0 isn't any better than random classification. In this video, I'll describe different metrics that can be used to evaluate non-binary classification models. Different metrics can be used to evaluate non-binary classification models. Multi-class metrics use more than two possible target classes. Binary metrics can be used for each class, for example, class 1 versus everything else, or class 2 versus everything else, and so on. A multi-class F1 score takes the weighted average of the F1 score of each class. In multi-label metrics, each input has one or more target classes. Ranked labels are a return set of values which are ranked, and they can be split like multi-class metrics for each label at each position. For example, class 1 at position 1 versus everything else, class 1 at position 2 versus everything else, and so on. With average metrics, precision, recall, and other metrics are calculated across all possible classes and label sets. Metrics are averaged using different methods. The macro average takes the average over all classes. The weighted average weights classes by how common they are when averaging a metric. And the micro average sums all metrics' dividends and divisors and uses that ratio. In this video, I'll discuss how you can use Python to calculate common evaluation metrics. There are different metrics that can be used to evaluate binary classification models. The confusion matrix is a visual method used to represent what kind of errors a model is making. For example, in binary classifications, you can determine the possible outcomes of a simple yes or no answer using a table. Precision refers to the ratio of correct answers, and recall refers to the ratio of true examples that are correctly identified. An F1 score is a metric that considers both precision and recall equally, and there are alternate F measures. There's also the Matthews correlation coefficient, a balanced coefficient that returns a number between -1 and 1, with 1 being a perfect prediction, 0 a completely random prediction, and -1 a complete inverse prediction. And the Cohen-Kappa score is a score that compares the model to a random selection with the expectation that accuracy will be attained. Now, on the scikit-learn site, you can find out more about classification metrics, and the sklearn.metrics module includes functions that can be used to measure classification performance. Some work only with binary classification, others work with multi-class and multi-label instances, some are used for ranking, and some can be used with binary and multi-class problems, but not multi-class. Now, clicking on any of these metrics will take you to a page where you can find out more about the syntax used, as well as examples. So let's take a look at this one. This is accuracy score. And here's some information about the metric and a brief code example, which I'll demonstrate now. So we start by importing numpy as np, and then from sklearn.metrics import accuracy score. Okay, so we'll create y prediction, or pred for prediction, equals 0, 1, 2, 3. And again, you should check out the example on the scikit-learn page to get more information about this. I'll create one called y_true, and this is actually what's being done on the scikit-learn page. 0, 1, 2, 3. Okay, and now we can use the accuracy score using the two parameters ypred and ytrue. And there you go. In this video, I'll describe different metrics that can be used to evaluate regression models. There are different metrics that can be used to evaluate regression models. Mean squared error, whose formula is shown here, is often used as a cost function. It describes how good a model is at making predictions, with 0 being the best score, and higher scores indicating increasingly error-prone models. Other measures of error include mean absolute error, for example, a non-square mean square error as demonstrated by this formula. MSE is typically preferred. It takes variance into account and it eliminates statistical bias. The mean square log error is good for the exponential growth model. The output becomes linear, and here's the formula. And an R2 score determines how well the model can describe the data. 1 is the best score, and 0 represents a model that always returns average output from a training set. That is, it always returns an expected value. If the score is less than 0, that indicates it's worse than using the expected value. In this video, I'll discuss how you can use Python to calculate common evaluation methods. There are different metrics that can be used to evaluate regression models. For example, mean squared error is often used as a cost function. It describes how good a model is at making predictions, with 0 being the best score and higher scores indicating increasingly error-prone models. Other measures of error include mean absolute error, for example, a non-square mean error. MSE is typically preferred. It takes variance into account and it eliminates statistical bias. The mean square log error is good for the exponential growth model. And an R2 score determines how well the model can describe the data. 1 is the best score, and 0 represents a model that always returns average output from a training set. That is, it always returns an expected value. If the score is less than 0, that indicates it's worse than using the expected value. Now, this scikit-learn site has some useful information on regression metrics using the sklearn.metrics module. You can click on several of the functions here to learn more about the metrics and their implementation, including code samples. For example, I'll click on R2 score, and that takes us to a new page where we can find out more about the parameters that can be used, and it also includes code samples that you can try out. In this video, I'll introduce you to AWS Machine Learning. Amazon Web Services Machine Learning is a cloud-based service that allows you to utilize machine learning. It's useful for beginners and developers alike, and uses a simple and easy-to-use API. There's no need to understand the underlying algorithms behind machine learning, or even machine learning for that matter. With AWS Machine Learning, you can get started right away creating machine learning models, and once the models are ready, you can obtain predictions. There are a few AWS machine learning key concepts you should be familiar with. Data sources refers to the metadata that's associated with data input. Machine language models are the models you set up that generate predictions using patterns that are extracted from your input data. Evaluations determine the quality of machine language models. Batch predictions create predictions for input data, and real-time predictions generate predictions for observations based on the data. There are several ways to access AWS Machine Learning. You can use the web-based Amazon Machine Language Console, the AWS Command Line Interface, the Amazon Machine Language Application Programming Interface, and there are SDKs for integrating AWS Machine Learning with software development. As for regions and pricing, AWS offers 2 real-time prediction endpoint regions for machine learning. US East out of North Virginia, and the EU out of Ireland. To avoid any confusion, regardless of where you're based, you can work with models from any region. As for pricing, if you're familiar with the AWS model already, you know that machine learning follows the pay-per-use model, so you only pay for what you use. Rates are hourly, and there's no commitment, initial cost, or minimum to get started with AWS Machine Learning. In this video, I'll demonstrate how to set up an AWS environment and import a data source. Now, Amazon Web Services Machine Learning is cloud-based, and it allows you to utilize machine learning. It's great for beginners and developers alike, and it uses a pretty easy-to-use API. Now, there's no need to understand the underlying algorithms behind machine learning, and with AWS Machine Learning, you can get started right away creating machine learning models. Now, if you're familiar with the AWS model already, you know that machine learning follows the pay-per-use model. So you'll only pay for what you use. But you do have to have an AWS account. So here I've got a page in AWS called Setting Up Amazon Machine Learning. And the first thing you need to do if you don't have an account is click here to set up an account. It is free. There's no charge associated with it. However, you will have to give some sort of payment information like a credit card in order to use it, because you may choose to use services later on that are billable. The machine learning example that I'm going to show you now doesn't have a cost associated with it. So if you want to just try it out and you don't want to pay anything, at least at this point you can try it without having to pay anything, but you will have to provide that credit card information. Now, once you're set up, you can go to this page. This is the Amazon Machine Learning Get Started page, and click this button. Now you have two options here. You can use the standard setup or the dashboard. Go right to the machine learning dashboard. There's also a tutorial here that provided by Amazon, and I do believe there's a cost associated with this. It's up to you, but you might want to try it out. It's pretty good. But let's just go ahead and use the standard setup and click Launch. Now, there are several steps here, beginning with inputting data. Now, the thing is, you can have your own data, but if you don't have your own data, Amazon has provided you with some data in a CSV, comma separated values format that you can use, banking data. And you can take a look at the file. I'll go ahead and click it to download it. And just double click that. So there's your comma separated banking data. You can import that into Excel if you want to look at it as a spreadsheet, but there's a lot of data there that you can work with. So I'll go ahead and close that. Now, in order to use this, you have two choices here for data access. You provide an S3 location, a path on Amazon S3, or a data source name. The way we're going to do it with this data is just to copy this file. We don't have to copy the beginning here, S3:/ because already provided for us here. Go ahead and paste that in. And once that's done, I can go ahead and click Verify. Now, the validation is successful, and we expect that because the data was provided by Amazon. And at this point, we can do is go to the next step by clicking Continue. In this video, I'll demonstrate how to create a model in Amazon Web Services Machine Learning. So the first step in the process to creating a model is inputting the data. I've chosen the banking comma separated values file that's provided by Amazon because it's a good sample file that we can use. And once you've chosen that and verified that data, the second step is choosing your schema. Now, I'm going to step through this pretty quickly simply because I don't want to mess with any of this. Everything's already set up in the data file. We know it's good and solid because it came right from Amazon. But if you want to, you can review the various categories here that are in the file, change the data type, and select your schema items if you want to. Notice that down here we've got 1 to 10 of 21, so if I click there, we can see there's the one we actually want, and that's Y. It's a binary value, so this is a binary schema we're going to work with. I'll go ahead and click Continue. And we've got a message here. You've selected the binary attribute named Y as the target. Yeah, we're using a logistic regression to train a binary classification model. So we're in the third step now, target, and we're just getting some feedback here that we're using Y, and then, so we'll use logistic regression for training. Now at this point, we can choose the target, and you've got a number of different categories you can choose here. Again, I'm going to leave that blank and just click on Continue. Now, we have the option in step 4 of a row identifier, and that just helps understand how prediction rows correspond to observation rows from the input data. So if you want to, you can choose to select yes. But once again, we're working with the data from Amazon. I don't want to mess with this too much, but that's okay. We're not going to change anything here. We'll just go to step 5, which is reviewing. So we review everything from the input data, the schema. We've got one binary attribute, for example. We've got 10 numeric attributes, 10 categorical attributes. Our target is binary classification, so we're just using a yes/no binary choice. No row identifier, and there we go. So we can go ahead and click on Continue. Now, we go to ML model settings. You can use this to customize if you want to. I'll go ahead and just go down here. What we can do at this point is choose the default, recommended, or custom, where we can modify things. We'll use the default. Again, we're working with the Amazon sample data, and we should be good. So I'll go ahead and click Review. Okay, everything's completed. Now at this point, we can go ahead and click Create Machine Language Model. And we get some feedback that this was successfully created. Now if I go to ML models right here, okay, we'll see there's our banking.csv. It's got an ID number and a status of pending. So right now it's being processed. And once that's finished processing, we're going to change in status and it'll tell us that it's ready to work with. In this video, I'll discuss models and training in AWS. Okay, so I've got a data set that I've actually trained, and I'm at the AWS Services console, and I'm going to click on Machine Learning. Now, this will take me to the Machine Learning console, and you can see that there are several items here generated from banking.csv, a comma-separated values document. And this is just a test document provided by Amazon. 3 of them are actual data sources. We have our machine language model and evaluation right there. And there's some useful information here. For instance, the status of these is all completed. They've all been processed. And we even have the completion time for these various items. So for example, I can click on banking.csv and just get some information on banking.csv and even use this data source to create, train a machine language model, evaluate a machine language model, or generate batch predictions. So I can do that from here. Now if we go back, here's our machine language model, banking.csv. And we can see that it's been completed. It's a binary classification. We get some information on the data source, the training. The evaluations, one has been created. We can perform another if we want to. And then predictions, we can view these in CloudWatch, the metrics, that is. I'll go ahead and click that. Okay, and from here we would actually pick our metrics and generate the CloudWatch graph. Let's go back here. Sorry, this one right here. We can generate batch predictions, try real-time predictions, and enable real-time predictions by creating an endpoint. I'll go ahead and generate batch predictions here, see what happens. Okay, so there's our batch predictions. Now if I go back here and click on the evaluation in the dashboard, okay, now we get our evaluation summary. This tells us what happened with the data and the idea behind this, and gives us an idea of the performance metrics. So in this case, we actually got a really good score, extremely good actually, and of course that's because we're using the data that was provided to us by Amazon. But this gives us an idea of the overall score, the baseline, and the difference. And we can adjust the score threshold here if we want to mess around with this a bit. So if I wanted to say put it here, we can get an idea of which are correct and which are errors. And here we can see that as we move it, we've got an idea of the true positives and the true negatives, and the false positives and the false negatives. So as I move it more toward predicted most likely to be 1, we see that the errors actually goes up. And if I go back toward predicted most likely to be 0, you can see the errors goes up there as well. So it really depends on this middle point is where it originally was is actually the sweet spot. And if I move it up here, you can see the number of errors goes up, the number of correct go down, and then the opposite is true when we go back to the center. And then if I go to the other threshold, then we see the same thing occurring. So we can actually play around with that a bit, which is nice. I can also, where did I put that? I think it was right there. No. Now go, oops, no, that's not it. Now go back and let's explore performance. So I click on explore performance and we get the same thing. So we can actually mess with that as well. So really, it has essentially a similar similar effect. Modifying. Let me say it again. So basically, clicking on either of those allows us to play around with the score threshold and see what the results are for our machine learning model. So there's plenty to do here with Amazon Machine Learning, and the really nice thing about it is that you can get this all set up fairly quickly and easily, use some existing sample data if you want to, and there's no cost to it until you actually start to do more with it. For example, there's a tutorial that you can take for setting it up, and I believe there's a cost associated with that, but most of the front end of this, getting set up with Amazon Web Services machine learning, is free, and it offers you some really powerful processing opportunities when you're training models and making predictions. Now that you've learned about applying machine learning, it's time to put some of that knowledge to work. In this exercise, you'll describe bias and variance. You'll describe bias, describe variance, and describe the trade-offs between bias and variance. At this point, you can pause this video and perform the exercise. Once you're finished, resume the video and see how I would do it. So let's tackle these questions. It's okay if you didn't do it exactly the same way. First, describe bias. Well, bias is error caused by making assumptions. It's defined by taking the difference of the expected, the average, value, estimated, and the actual value. And the expected estimated value is the average of values if a model is trained multiple times. High bias models require many assumptions, that is, linear regression mode, naive Bayes, and so on, and these models can miss certain relationships in the data. Next, describe variance. Well, variance is error caused by fluctuations in the data, and that is often referred to as noise. And that's commonly thought of as noise. High variance can cause models to be prone to overfitting, and training the same model on different data sets will yield different results when the variance is high. Finally, describe the trade-offs between bias and variance. Well, in machine learning, every model has some bias and has some variance. Decreasing variance increases the bias, and decreasing bias increases the variance. Some models are more prone to different types of error, so changing model parameters can help mitigate one type of error, but not both. And hybrid models can be used to mitigate both types of error. I hope you found this exercise helpful.
There are several machine learning algorithms and techniques which require the input data to be scaled in some form. If the features in your dataset are vastly different in scale, then some algorithms will have a bias for the high magnitude features. For example, consider a dataset where you're evaluating students who have applied to a university. Their high school GPAs will be in a range of 0 to 4 approximately, and then their SAT scores will be in a range of 400 to 1600. Many algorithms will tend to downplay the GPA and give a higher weightage to the SAT score simply because the GPA is a much smaller number than the SAT score. This is precisely why it is important for you to know how to scale your input data and the different types of scaling techniques which can be applied. That is precisely what we will cover now, and for this demo, we will be performing some scaling operations in Jupyter Notebooks. Jupyter Notebooks are an interactive web-based development environment. It allows you to define and then execute a few lines of code for your application and then get immediate feedback before you proceed further and then build upon your app. Here, I have brought up a Jupyter Notebook session from my workspace, and then within that, I have a directory called Notebooks, and this is where the Jupyter Notebooks for this particular course will be developed. It is assumed that you have some background using Jupyter Notebooks and you're comfortable with the interface. However, before we begin building our first Jupyter Notebook for the course, let us take a look at the workspace itself. For that, I'll head over to the root workspace directory, and within that there are two subdirectories, datasets and notebooks. The datasets directory contains all the data sets which will be used during the demos in this learning path. And we can quickly take a look at what it contains. So within this, as you can see, are a number of CSV files, and these are the data sets for the demos. We can navigate back up to the workspace root, and then from there, head over to the notebooks directory again. And now we can create our first Jupyter notebook for this course. So for that, just head over to the right and click on New. And then the kernel which I'm going to use for this notebook is the Python 3 kernel. And I'm just going to click on that. And the first thing I'm going to do when this notebook is up is to set it a name. So the topics we will be covering in this demo are data scaling and encoding. And that is the name I'm going to set for this notebook. So once you hit rename, we are now ready to write some code. The first thing I'm going to do here is to simply disable warnings for this notebook. This is something you need not do, but I'm just doing it here because there are some of the dependencies of the libraries we will use, and those can invoke some warnings. These warnings are likely to be addressed in the newer versions of the libraries. However, they will merely be a distraction for this course, which is why I'm simply disabling them. Following that, we will import all the libraries which we require for this demo. And this includes the NumPy library, which will allow us to manipulate data in the form of arrays. The Pandas library allows us to view data in the form of a two-dimensional data frame. And this is what we will use in order to represent our data set. The Matplotlib library is used in order to visualize data. And then the scikit-learn's pre-processing library is the one which includes various scaling operations which we will demonstrate during this course. This includes not just scaling operations, but a lot of other data processing tasks which are required in order to prepare your data to be fed to a machine learning algorithm. With that done, we will now go ahead and import the data set which we will use to demonstrate various scaling operations. The data set includes a lot of information about movies, such as their name, year of release, their revenues, and also includes the ratings for these movies on IMDb and Metascore. The source for this dataset is www.kaggle.com/promptcloudhq/imdb-data. We load this dataset into a Pandas data frame using the Pandas read CSV function. The argument to this particular function include the location of the dataset itself, which is in the datasets directory we saw previously, and then optionally we can specify a separator for the data within this dataset. In our case, because it's a CSV file, the separator is a comma, which is what we set here. This read CSV operation will turn our CSV file data into a Pandas data frame, which we will reference as movie data from here on. So once we have this data frame, the first thing we will do is to drop any rows within it which contain any missing values. Any missing values in a dataset can throw off a number of operations which you wish to perform. There are many different means available to handle missing values. One of these could be to simply fill in the missing values in numeric columns with zeros or some fixed value. However, if the dataset does not contain too many missing values, often the cleanest operation which you can do is to simply drop all the rows which contain even one missing value. And this is exactly what this drop NA function of a Pandas data frame can accomplish. So once we have cleaned this dataset with all missing values and updated our movie_data data frame, we can preview its contents using the head function. This will return by default the first 5 rows in our data frame. And then from the output, you can see the kind of data which is included in our dataset. So we have here the movie title, the different genres which it can be cast into. We have data for the director, the actors, the year of release, the total length of the movie, and the ones we are interested in include 2 rating columns. The one called rating references the IMDb rating for the movie, and then finally the Metascore rating at the extreme right includes the Metascore rating. The IMDb rating aggregates the ratings of users on IMDb, while the Metascore rating represents the ratings given by critics. As you may have deduced from looking at the data, or may already know previously, the IMDb rating is in a scale of 0 to 10, while the Metascore rating is in a scale of 0 to 100. We can then take a look at the length of this data set, that is the number of rows, using Python's len function. To that, we simply pass in our data frame as argument, and this shows us that this data set includes 838 rows of data. Following this, let us examine the contents of the year column. So within our data set, we want to examine how many different movies have been released in each year. So for that, we reference the year column of our pandas data frame and then make use of the function value_counts. And the output shows us that our dataset includes movies released between the years 2006 and 2016, and there is certainly a bias towards the more recently released films. So after previewing our dataset using the head function and then examining the contents of one column over here, we have some idea of what our dataset looks like. However, when you have a large number of numeric values, then there is a pandas data frame function which can give you a much better understanding of the distribution for each of the columns in your data frame. This function is the describe function, and then executing this line will show us exactly what it gives us. So here you can see that for all the numeric columns in our dataset, we have some kind of information about its distribution. So we have here the mean, standard deviation, the minimum and maximum values for the particular columns, and we also have the values for the two quartiles and the median as well. So you can see here, for example, that the rating column has a mean of about 6.8, and then the values range from a minimum of 1.9 to a maximum of 9. The median value for the rating is also about 6.9. If we were to use this IMDb rating value in order to decide whether a movie is a hit or a miss, we can make use of one of the operations available in the scikit-learn preprocessing library. That is exactly what we will explore in just a little bit. So now that we have loaded our movie ratings dataset into a pandas data frame, and then made use of the describe function to examine the contents and the distribution of values in all the numeric columns, we will now perform an operation to split our dataset into movies which are hits or flops. Since we often view the IMDb rating for a movie to make a binary decision, whether we want to watch the movie or not, it'll be helpful for us if we could convert this rating column into a binary value. So any movie which exceeds a certain threshold for IMDb rating will be considered watchable by us. That is exactly where we can use the binarizer of the scikit-learn preprocessing library. This has the effect of converting a continuous column in your data frame into a binary value. Anything above a specified threshold will be assigned a binary value of 1, and anything at or below that threshold will be given a value of 0. So to use it, we import the binarizer class from sklearn.preprocessing and then immediately apply this on our data frame. So we initialize the binarizer over here by setting it a threshold of 7. This means that when this binarizer is applied to a specific range of data, any values exceeding 7 will be converted to a value of 1, and anything equal to or less than 7 will have a value of 0. We will apply this binarizer using its fit function, and the specific range of data to which we apply it is the rating column of our movie_data data frame. So here we pick a value of 7 for our threshold because this exceeds the mean and the median of the rating value. So any movie with an IMDb rating greater than 7 will have a value of 1 over here, and then this will be considered by us as worthy of a watch. Everything else we will decide to skip. So once we run this cell, our binarizer has been created, but at this point, it has not performed any transformation of the dataset yet. However, we can still examine this object, and for that we just take a look at what this binarizer gives us. And here we see that it includes a threshold value of 7, which we had explicitly set, and then there is this copy parameter, which by default has been set to true. This means that this binarizer object is working with a copy of the rating column and will not transform its contents in place. If you would like an in-place transformation, you can simply initialize the binarizer with the copy parameter set to false. So now that we have our binarizer object, we will go ahead and transform the contents of the rating column. And for that, we make use of the transform function of the binarizer. This will binarize the contents of the rating column using our specified threshold, and the transformation will not occur in place within the data frame, but will be output in this binary_x object. So we can simply go ahead and execute this cell in order to get a binary output. And then we examine the first 10 rows of this binary_x variable. And this is just to confirm that this binary transformation has indeed taken place. The type of this binary_x variable is a NumPy array, which is why we can access the top 10 rows using this slicing notation. And from the output, there are clear signs that this binarizer has indeed done its job. So we only have ones and zeros, at least in the top 10 rows. However, in order to make sure that the threshold has been applied correctly, it is best to do a side-by-side comparison of this binarizer output along with the original rating column. In order to do that, we transform this binary_x NumPy array into a pandas data frame, and for that we initialize a new data frame to which we supply this binary_x as the data input. We set a name for this column as binary rating, and then this will create a new data frame with a single column, which we refer to as binary_rating_df. We first examine the top 5 rows of this data frame, and we can once again see here that this contains a bunch of ones and zeros. And now for the side-by-side comparison, we make use of the pandas data frame concat function. Here we concatenate our original movie_data data frame with this binary rating data frame. This concatenation will occur along the columns, which is why we specify the axis is equal to 1 argument. And then we also specify the columns of this updated data frame which we wish to view in the output. So here we are only concerned with the title, year, the original rating, and the binarized rating columns. To view the first 20 rows of the data frame, we specify a value of 20 as the argument for head. From the output though, it does become clear that the binarizer has indeed worked as expected. For example, the rating for the movie The Guardians of Galaxy at the very top is 8.1, and this has a binary rating of 1, while the film Prometheus, with an IMDb rating of 7, has a binary rating of 0. So this is the one which is exactly at our threshold value. With that, let us explore the distribution of the data in our data frame once more using the describe function. And then from the output, we see much the same values as we did previously, but this time the new column is at the extreme right, which is the binary rating. With a mean of 0.42, we can say that about 42% of the movies in this data frame have a binary rating of 1, while the rest have a rating of 0. We have previously seen how the binarizer in scikit-learn's preprocessing library can be used to transform a column containing continuous values into a categorical column with binary values. Another interesting transformation offered by the scikit-learn preprocessing library is the min-max scaler. This transforms a continuous feature by scaling its values to a specified range. So in the IMDb movie dataset, which we have been working with, we saw that the IMDb rating itself is in a range of 0 to 10, whereas the Metascore rating is in a scale of 0 to 100. It'll help if both of these were in exactly the same scale before we fed them as input features to many machine learning algorithms. This is exactly what we will do with the min-max scaler in this demo. To begin though, let us now import the min-max scaler from the sklearn.preprocessing library. And then following that, we preview our dataset once more. So we view the first 5 rows using the head function of our movie_data data frame. And we can confirm over here that the IMDb rating column, which is known simply as rating, and the Metascore rating in the Metascore column are in different scales. The first thing we will do before applying any transformation is to visualize the distribution of the IMDb rating and the Metascore ratings. For that, we make use of the matplotlib data visualization library, and any visualization in matplotlib will be part of a figure whose dimensions we have specified in the top row here. Following that, the specific plot which we will generate here will be a histogram, which we define using the plt.hist function. A histogram, as you may be aware, will show the number of occurrences of a specific value or a range of values within your dataset. That is, it will display a frequency distribution. The data we wish to examine the distribution of includes the IMDb rating and the Metascore rating, and we will split the entire range of values into 10 different bins. There will be 2 sets of bars in our output. This will include one set of bars for the movie data rating column, and then another set of bars representing the distribution of the Metascore ratings. So in the argument to the hist function, we also specify a label for each of these sets of bars. In the next 2 lines, we set a title for our plot and also specify where the legend should be located. In fact, by setting a value of best for the legend location, we are letting matplotlib decide what the optimal placement of the legend is. Matplotlib also allows us to set the labels for the x and y axes for our plots, and this is what we do over here, where the x-axis will represent the rating values, whereas the y-axis represents the counts for the number of data points in a dataset which fall in a particular range of rating values. Right at the bottom, we make use of the plt.show function in order to display the plot inline in our Jupyter notebook. This is not required if you are running matplotlib in interactive mode. However, once we run this cell, our histogram plot has been generated. Now clearly, because the IMDb rating is in a scale of 0 to 10, all the IMDb rating values fall into this first bin. So you see over 800 data points. So our dataset contains a total of 838 rows, and the IMDb rating for all of them is in this first bin. The Metascore rating, on the other hand, is more evenly distributed. So clearly, if we were to do either a like-for-like comparison between the IMDb rating and Metascore values, some scaling of at least one of these columns is necessary. In fact, a lot of machine learning algorithms, including clustering algorithms such as the k-means clustering, will require all the input data to be in the same scale. And this is exactly where we will use the min-max scaler which we have imported. So we initialize a scalar object using this min-max scaler, and we can specify a range for the transform distribution. So if we want all our ratings values to be in the range of 0 to 5, then we set a value for this feature underscore range argument to a tuple containing 0 and 5. If you do not explicitly set a feature range, then the min-max scaler will use a range of 0 to 1. So once we have initialized our min-max scaler, we can quickly take a look at it. And then this shows that once again that this is working on a copy of our input data and will not apply any of the transformations in place on our data frame. And we can once again see the feature range over here. If you'd like to access these parameters at any point, you can make use of the get underscore params function of the scaler, and this will give you the values for the copy and feature underscore range parameters. It is now time for us to apply this min-max scaler in order to transform the contents of the ratings columns in our data frame. So we have previously seen with the binarizer that we first used the fit function in order to fit the binarizer to our input data, and we followed that up by calling the transform functions in order to apply the transformations. To avoid having to make 2 separate function calls, there is also a fit underscore transform method which does both a fit and a transform operation. This is available with the min-max scaler as well as the binarizer and other transformers within the preprocessing library. The argument to this includes the columns of our pandas data frame which we wish to transform to the specified range. So both the IMDb rating and the Metascore columns will be transformed into a range of 0 to 5 this time. And once we apply these transformations, we can view the first 5 rows of these scale ratings to see exactly what they look like. Since the scaled values will include a lot of digits following the decimal point, I'm setting a precision of 3 using the NumPy set print options so that it is easier to visualize the scale data. And then since the scale ratings will be in the form of a NumPy array, we can make use of this slice notation to view the first 5 rows. And from the output, we can see here that the values do seem to be in the range of 0 to 5, and it seems easier for us to compare the IMDb rating with the Metascore rating this time. A better test would be if we can place these two ratings values side by side, which is exactly what we will do by transforming this scale ratings data into a pandas data frame. The two columns within that data we will label as scaled rating and scaled metascore. And then let us preview this data frame by making use of the head function. And this output is much cleaner than what we saw previously with the NumPy array. And generally speaking, you can see here that the IMDb ratings, where the users rate the movies, seem to be higher than the Metascore rating, where the rating is given by critics. Such comparisons can be performed when both the ratings values are in the same scale. We will now go ahead and visualize the distributions of these two ratings values once more. So we make use of matplotlib's hist function to generate histograms, and we will be using the scaled IMDb ratings and the scaled Metascore ratings, and we will split up the range into 10 different bins. So what do the distributions of these scale ratings values tell us? Well, from the output here, we can clearly see that in the case of the Metascore ratings, there is a far wider distribution into the bins. We can observe that the IMDb user ratings seem to fall pretty much into 4 of the bins in this range. So scaling can be applied not just to process your data before it is fed into some machine learning algorithm, but in order to analyze the data you have in order to extract meaningful insights. We have now examined the use of a binarizer in order to transform a continuous value into a binary one. And then we have applied the min-max scalar in order to explicitly specify the range into which a particular distribution should fall into. We will now examine how we can use a standard scalar in scikit-learn in order to standardize a distribution. That is, we adjust the values in a distribution so that it has zero mean and unit variance and standard deviation. The individual values in the distribution will then be expressed as a z-score or a z-score, where they will be expressed in terms of standard deviations from the mean. This standardization of the input features is an essential requirement for many machine learning estimators. This includes support vector machines and also some neural networks. So let us now begin exploring how exactly we can apply a standard scalar on a dataset. We begin by importing the standard scalar from the scikit-learn preprocessing library, and then we will apply the standard scalar to some of the columns in our dataset. This includes the rating, the metascore, and the revenue columns, and we will now take a look at the original values, at least in the first 5 rows of the dataset. So from the output, we can see that they're all in different scales. The ratings column, which includes the IMDb user ratings, takes values between 0 and 10. The Metascore ratings has values between 0 and 100. And in the case of the revenue, well, it'll start from 0 and there is no upper bound. From this preview here, we can guess that they're probably in the range of hundreds. That is, the revenues are typically hundreds of millions of dollars. In fact, the best way to get a brief summary of the distribution of values is to make use of the describe function. And once we apply it, we get a few insights here. The mean values for each of these columns is visible, and you can make some kind of mental note for what the range of these values is. You can also make note of the standard deviations, because it is the mean and standard deviation we need to keep an eye on once we apply our standardization. Before we do so, however, let us examine the distribution of the revenues data. The reason for this is to understand the distribution before we apply our standardization and afterwards. So we once again make use of the matplotlib hist function in order to distribute our revenues across 10 different bins. And the output makes it clear to us that most of the films seem to have low revenues. That is, they seem to be in the $0 to $100 million range. And once we get above $300 million, there are hardly any movies in our dataset. Let's move along now and then initialize our standard scalar. So we do not pass any parameters when we initialize the standard scaler. However, when we apply the fit function, we pass in the 3 columns from our dataset which we wish to standardize. So once again, these are the IMDb rating, the Metascore, and the revenue columns. Once our standard scaler has been fitted to these columns, we can examine its parameters, and we see here that once again, the copy argument is set to true, and the width mean argument, which by default has been set to true, determines whether the data in the columns need to be centered. That is, whether they should be adjusted in order to have a zero mean. In the case of the width std parameter, this is again set to true by default, and this determines whether the data needs to be scaled in order to have a unit variance or standard deviation. So now that our standard scaler has been fitted to the 3 columns which we have defined, we can examine some of its details. If you would like to see the mean for each of the columns, we can make use of the mean underscore field in the standard scaler. And this gives us an array containing 3 values corresponding to the means of the 3 columns. Similarly, we can take a look at the variance for each of these columns by accessing the var underscore field. And we have the 3 variance values over here. Following this, we will transform the data from the columns by making use of the transform function in the standard scaler. So this will mean that each of the individual values in the 3 columns will be expressed as a z-score. That is, in terms of standard deviations from the mean. So once this transformation has taken place, we can examine our scaled values. And on this occasion, we see both positive and negative values, and all of the values seem to be rather small. So the z-score transformation seems to have taken place. We will now view these z-scores in the form of a pandas data frame. So we initialize this data frame using the scaled underscore x values and then set names for each of the columns. So these will be scaled rating, scaled metascore, and scaled revenue. And then we preview this scaled data frame using the head function. So we can see some of these scale values now in the form of a pandas data frame. And once this is done, we can examine the distribution of the data here by making use of the pandas data frame describe function. From the output, you can see that the range of data is now much more narrow, but the interesting points here are the mean for each of these columns. So the standard scaler will set the means for each of the columns to 0, and this is pretty much what has occurred. So though the means are not exactly 0, they nearly are given the scale of these numbers. Similarly, the standard deviation for all of these columns is almost exactly 1. So this is the effect of standardizing your data. This will make it easier for machine learning estimators to make sense of your input features. And in addition, they can also speed up the training process in some cases. Even for your own data analysis purposes, if you were to have values expressed as a z-score, it is easier for you to estimate whether a particular value in your dataset is ordinary or truly exceptional. Now that we have standardized our data, let us examine the distributions for each of them. So here we make use of the histogram function once more in matplotlib in order to plot the scaled values for rating, metascore, and revenues. And the output shows us that after scaling, most of the IMDb and Metascore ratings seem to fall within 2 bins. The data distribution seems to be even more skewed in the case of the revenue, where 2 bins around the mean seem to take up nearly all of the data points. We can now examine the scaled revenue individually, and for that we make use of a similar histogram to what we saw previously when we plotted the absolute revenue values. So this time we plot the scale revenue distribution, and the graph we emerge with is in fact very similar to what we had previously. So standardizing our data seems to have little effect on the actual distribution of the data itself. What is clear from this, however, is that most of the movies in our dataset seem to have revenues slightly less than the mean. This implies that there are a handful of movies which have generated a lot of money, and they're skewing the mean value for the revenue column. The transformations we have applied in the course so far have involved the use of a binarizer, a standard scaler, as well as a min-max scaler. All of these operate on columns of a data frame, and then transform each column independently from the others. We will now explore the use of a normalizer, which does not operate at the level of a column, but in fact treats each row of your dataset independently. When such operations are performed at the row level rather than at the column level, we say that it is a cross-sectional transformation rather than a longitudinal one. The use of a normalizer is required in the case of certain clustering algorithms and also when you wish to perform text classification. In this demo, however, we will be using a dataset which includes health-related metrics for a number of patients and then contains a label of whether they developed heart disease or not. The dataset can be downloaded from www.kaggle.com/ronitf/heart-disease-UCI. This dataset is available in the course materials, and in my case, it is in the datasets directory in my workspace. So I'm reading from that directory using the pandas read_CSV function in order to load the contents of this dataset, which is in the heart.csv file, into a data frame called heart_data. Once this dataset has been loaded, we can preview its contents using the head function. And we can see here that this includes a fair amount of information for each patient. Starting with their age, their gender, CP represents the type of chest pain the patient complained of. The T-rest BPS represents the resting blood pressure. The final target column represents whether the patient was eventually diagnosed with heart disease or not. So if we were to use some of the columns of this dataset in order to perform some clustering operations, then transforming it using a normalizer should give us better results. So before we do that, let us quickly preview the total length of this data frame. And we can see here that this includes 303 rows of data. Following that, we will import the normalizer from the scikit-learn preprocessing library. And then before we apply it, let us extract some of the columns from our data frame, which we will use in order to perform this normalization. These include the patient's age, their resting blood pressure, their cholesterol levels, their maximum heart rate, and we include the old peak column mainly because it contains very low values relative to the others. So these will be our X data, and once we have it, we can quickly preview it using the head function, and we quickly get an idea for the scale of each of these columns. The age is usually a 2-digit number, whereas the test rest BPS is typically in the hundreds. Cholesterol levels seem to be in the 200s to 300s range. However, to get a true picture of what this data distribution is like, we make use of the describe function for the data frame. So here we can see the range for each of these columns, as well as their means and standard deviation and their quartile values. So now we have some idea of what this data looks like. We can go ahead and prepare this data in order to apply normalization. The first thing we will do is to transform the contents of this data frame into a NumPy array. We can do that by making use of the values field of the data frame. And then we have this variable called array. When we view its contents, we see that it has the same data as in the data frame, but this time it does not have the column headers and then associated metadata for the data frame. So with this raw array, we can feed it into the fit function of the normalizer. So when we initialize the normalizer, we do not set any parameters, making use of the default values which the normalizer will set. Following that, we make use of its fit function, to which we pass our NumPy array, and this will fit our normalizer to the input features. Following that, we can take a look at this normalizer which we have initialized, and this shows that once again it is working on a copy of the data, and the type of normalization which will be performed is an L2 norm. We'll discuss that in a little more detail in just a little bit. But before that, we can take a look at the get_params function, which is included as part of the normalizer, in order to retrieve each of the parameters which have been set for it. We won't be accessing those parameters for now. However, what we will do is to transform our input features using the transform function of the normalizer. So this should normalize each of the rows within the array. Following that, we can quickly preview the first 5 rows of this NumPy array which is returned using the slice notation. and the output confirms that some kind of scaling operation has indeed been performed. To make it easier to view this NumPy array, we will transform its contents into a pandas data frame. So we initialize this data frames with a normalized array. And since this data frame will contain no column headers as of now, we will create a list of the column headers which will be applied to it. For this, we make use of this column underscore names list, and this contains the same column headers as in the original dataset. Following this, we apply this column underscore names list to our data frame by setting its columns field to this column underscore names list. And following that, we are now ready to preview this data frame. And now we can see exactly what the transformations which have taken place are. So just to give you an idea of what transformation has taken place, the first cell in this data frame representing the age of a particular patient was 63 in the original data set. The scaled value of this age is the age itself, which is 63, divided by the square root of the sum of the squares of the values for each column in this particular row. So the formula I have displayed on screen shows how this value of 0.197466 was calculated. All the other data points in this particular data frame were also calculated similarly. So you'll remember from the parameters of our normalizer that by default it was set to use the L2 norm when normalizing. This is precisely why the sum of the squares is used in the formula. If it was set to use the L1 norm, it would use the sum of the modulus values rather than the sum of the squares. Now let us use the describe function in order to view the distribution for each of these columns. And the output shows us the range of values over here. Now this is not entirely meaningful because when we perform this normalization, it is each row which is evaluated independently and it's not a column-wise operation. And this output confirms to us that the relative scales for each of the columns has not really changed significantly since the normalization. In our scale data frame, there are a number of digits after the decimal point, which does make it hard to read the values. So I'm simply going to apply the round function here on our data frame. So the values are rounded to 2 digits after the decimal point. We can quickly preview the contents of this transform data frame. And yes, this is far easier to read. Now, one effect of this cross-sectional scaling will mean that the distribution of data within columns should be affected by the transformation. Let us try to visualize that by making use of the matplotlib hist function once more. And first, we will plot the distribution of the test rest BPS column of the original dataset, not the transformed one. And following that, we can see what the distribution looked like before normalization. We will now plot a similar histogram, but on this occasion, it will represent the distribution of the test rest BPS column after normalization. And then from the output, it becomes evident that the scaling has indeed affected the distribution. So this histogram is a little different from the one we saw for the original dataset. There will be instances when you would like a particular value to be expressed as a proportion or a percentage of the maximum value in that series. For example, if you're examining the math scores of some students after a particularly difficult exam, individually, a score of about 70 may not seem particularly impressive. However, if you happen to know that the maximum score obtained by any student in that exam was only about 73, then you know that a score of 70 is in fact really good. So there are benefits to expressing a particular value in terms of the proportion to the maximum value. And this is precisely where the use of the maxapps scaler comes into the picture. So this is one of the scalars which is available in the scikit-learn preprocessing library, and it will express each value as a proportion of the maximum value in the corresponding series. We will soon see exactly how this works. The dataset we will be applying this transformation to is the heart patients dataset we used previously, specifically the trimmed down version whose contents we preview here. So you can see that this includes 5 columns in all: the age of the patients, their resting BPS, and so on. So if you're not in the medical profession, just looking at these numbers in and of themselves may not give you an idea of whether they are high or low. However, if we were to transform this using a max-app scaler, things will become much clearer. However, before we apply the transformation, let us make use of the describe function in order to examine the distribution for each of these columns. And from the output, we now have an idea of the range for each of these columns, but the values which are of interest for the max app scaler are the ones right at the bottom, the maximum values for each of these series. So to apply the max app scaling, we simply initialize the max app scaler and we do not pass in any arguments because we just wanted to use the default values. We then call its fit method on our input x values, and this will initialize our max app scaler in this scalar variable. We can examine it over here, and there is just one parameter associated with the max app scaler, whether it will work on a copy of the input data or whether it will apply the transformations in place. So following that, we examine some of its other fields, and if we take a look at the max underscore abs underscore field, we get the maximum values for each of the columns. This is exactly what we saw in the output of the describe function on our data frame. So now that this max app scaler has been fitted with our data, we can transform it by making use of the transform function. So this will return a numpy array containing all the scaled values, which we will reference as max abs underscore x. If we take a quick look at what it contains, we see a lot of values between 0 and 1. So it looks like all the values are indeed expressed as a proportion of a maximum value. We simplify viewing this data by transforming it into a data frame. So once again, we initialize the data frame with this max abs underscore x array, and we specify the columns argument in order to set the column headers. We'll then preview this new data frame, and we can see the values of our scale data. For example, the first value in this data frame represents the age of 63, which is expressed as a proportion of the maximum age of 77 in that column. It is also easier for us to estimate how high or how low each of the other values in this data frame are. For example, the cholesterol level for the first row shows that this patient had a cholesterol level which was 41% of the maximum value in this data set. We can now examine the distribution of values in our scale dataset, and we get a few interesting insights. For one, as expected, the maximum value for all of the columns is exactly 1. But does this scaling have any influence on the distribution of data in a particular column? Well, there is one way to find out, which is why we will plot this histogram for the test stress BPS column before the transformation was applied. So just as we have done previously, we set a title for the plot and we also label both the axes. Following that, we get a view of the distribution before the transformation. And now we will plot a distribution once more, but this time on the scaled value for the test stress BPS. And then when we generate the plot, we see that the distribution has in fact not been affected by the scaling. All the transformations we have covered so far in this course have involved scaling data in some form. Such scaling of the input data is a requirement for many machine learning estimators. This can help your machine learning models make better predictions, and in many cases, they can also speed up the training process. We will now explore another family of pre-processing tools, and these involve encoding your dataset in some form. In this demo, we will take a look at label encoders, which are often used to transform string data in your dataset to numeric labels. To demonstrate that, we will load one more dataset into a Pandas data frame. This dataset, which is popularly known as the adult income dataset, contains information about various working adults in the United States. And then there is a label which indicates whether the individual happens to make more than 50,000 US dollars a year in income or less than $50,000. The dataset can be downloaded from www.kaggle.com/wenruliu/adult-income-dataset. It is also included as part of the course materials and can be found in the file adult.csv, which is in the datasets directory of my workspace. So I make use of the pandas read_csv function to load this dataset into this income_data data frame. Once the data has been loaded, we preview its contents using the head function. And now we can see exactly what this adult dataset looks like. You can see this includes details such as the age, education, occupation, race, and gender of the individual. And then finally, towards the right, there is their income. And there are just two values for this particular field, whether the income is less than or equal to 50,000 US dollars or greater than 50,000. This dataset is often used to build classification models where you can use all the input features to determine whether a person makes more than 50,000 US dollars a year or not. You will also notice in the bottom row that there are some missing values which are represented by a question mark. In order to handle missing values, it's best for them to be represented as NaNs rather than question marks or any other string value, which is why we are now going to reload this adult.csv file into the data frame, except this time, as an argument to the read_csv function, we will specify that the NA values in the dataset are represented by question marks. So once we load this data and preview the dataset, what we see here in the bottom row is that all the missing values are represented by NaN. However, that is not going to be the focus of this demo, and we will now switch our attention to this marital status column. You can see here that this includes the marital status of all the adults in this dataset, and all their marital statuses are expressed in the form of strings. Now, if we were to build a classification model using this dataset, then we will need to transform this into numeric values. This is because most machine learning algorithms, whether used for classification or for regression problems, cannot work with string data. So we need some way to transform this particular column into numeric values, which is exactly what we can use the label encoder for. Before we do that, however, let us examine the unique values in this particular column. So for that, we access the marital status column from our income data frame and then use the unique function in pandas. So this gives us all the different values which are present in this particular column. And there are a total of 7 distinct values. When we apply label encoding to this column, the strings you see in front of you will be transformed into integers ranging from 0 through 6. We will now go ahead and implement that. And for that, we will import the label encoder class from scikit-learn's preprocessing library. We will follow that up by initializing the label encoder without passing any parameters. And in order to label encode the marital status column, we will simply make use of this label encoder, specifically its fit_transform method, whose argument includes the column of our pandas data frame which needs to be label encoded. So here we are label encoding this marital status column and then overwriting the current marital status column with the label encoded values. Following that, we can preview our data frame once more. So the output gives us the first 5 rows of the data frame, but what we wish to focus on is the fact that the marital status column no longer contains strings, but these numbers. So each of the unique values for marital status has been translated into an integer. And to view what these integers are, we can make use of the unique function once more. And we see here that the 7 different values for marital status, which were previously strings, now contain 7 different numbers from 0 through 6. The labels have been chosen by simply iterating through the original marital status values in alphabetical order and then assigning an integer index. So in alphabetical order, the first value for marital status is divorced, which has been assigned the label 0 in this case. The last value is widowed, which has a value of 6. Now, in case you have performed a label encoding of some column, and you decide that you did not want to perform that encoding in the first place, or you need to reverse the operation for some reason, well, you can simply make use of the inverse transform function. This will convert the label encoded values back to their original form. So once we execute this, we can preview the data frame to ensure that the inverse transform did take place. And then from the results, we can see that the marital status column now includes the original string values. So one thing to note is that label encoding is not meant to transform input features just like we have done in this demo so far. This is because a lot of machine learning algorithms will interpret the numeric labels as numbers rather than the labels which they really are. This could have the effect of the labels being treated as numbers which can be compared to one another. And for example, the machine learning algorithm may treat the value of divorced as less than widowed because the label for divorced, which was 0, is less than the label for widowed, which was 6. This, of course, doesn't really make any sense, which is why label encoding is not meant to be used on input features which contain more than two distinct values. It can, however, be used on the target column of a dataset meant to be used for classification models, irrespective of the number of distinct values in it. In the case of our dataset, this is the income column. So if we were to use this adult income dataset in order to build a classifier which will be able to take in all the input features and then predict whether an individual makes greater or less than 50,000 US dollars a year, then we need the target column to be in the form of numeric labels rather than strings, which is why we will now use the label encoder's fit transform method on the income column of our dataset. And then following that, we can preview its contents. And we see here that all the string values have been replaced by zeros and ones. Once again, alphabetical ordering, or to be more precise, ASCII ordering was applied before assigning the labels. So the string less than or equal to 50k has been replaced by 0, and the string greater than 50k is represented by 1. So now that we have transformed the target column into label encoded values, there still remains the issue that most machine learning algorithms require the input features to be in the form of numbers rather than strings. There are clearly many string variables in our dataset here. So what do we do about them? Well, in the next clip, we will talk about one-hot encoding, which can be applied on the input features. We previously discussed how label encoding should not be applied to input features. This is to prevent machine learning estimators from treating them as numerical values when in fact they are categorical labels. However, there still remains the question of converting the strings in our input features to some numeric value which can be fed into machine learning algorithms. For that purpose, we have something called one-hot encoding. In this case, if the feature column which you wish to encode has n distinct values, then one-hot encoding it will transform it into n different columns, each representing one of its distinct values. For each row, the value present in that column will be represented with a 1 in the corresponding one-hot encoded column, and all the other one-hot encoded columns will be 0. I'm sure this is all a little abstract, so let us begin coding and see exactly what this looks like. So previously, we had label encoded the marital status column of our adult income dataset. Now, in order to perform a one-hot encoding, we can make use of a pandas function rather than a scikit-learn function. The pandas function to use here is called get_dummies, and the argument which is passed to it is the column which needs to be one-hot encoded. In our case, this is the marital status column from our dataset. So once we perform this one-hot encoding, we can view the return data frame, and you may recall that there were 7 distinct values in this particular column. So the output should contain 7 columns. And in fact, that is precisely what we have. The 7 distinct values have been translated to 7 distinct columns, where each value is a new column header in this case. The first row in this particular dataset represents an individual whose marital status was listed as never married. So you can see here that the corresponding column here has a value of 1, while all of the others have a value of 0. The next 3 rows represent individuals who are married with a civilian spouse, and the value of their marital status was married civ spouse, which is why that column is 1 and everything else is 0. So at this point, all of the values in these columns are numeric, and these can be fed into machine learning algorithms. What we have done with this one-hot encoding though is to create a separate data frame containing the one-hot encoded values. So if we preview our original data frame over here, we will see in the result that the marital status column is still in its original form. So if you would like to perform this one-hot encoding in place and alter the contents of your data frame, we can make use of the pandas get underscore dummies function once more, but this time we pass in the arguments a little differently. Using the data argument, we specify the data frame which contains columns which we require to be one-hot encoded. Following that, we use the columns argument to pass a list of columns in this data frame which needs to be one-hot encoded. In our case, we only wish to perform this encoding for the marital status column, which is why we only pass this in our list of columns. The getDummies function will return a data frame which contains our original income data frame, but the marital status column will be replaced with the 7 columns representing its one-hot encoded values. So once we run this cell, we can simply do a preview to see what this looks like. And you see that the original marital status column is no longer here. As for the one-hot encoded columns, well, for that we simply scroll over to the right, and the 7 new columns have been appended over here. So if you were to use the getDummies function in order to one-hot encode all the categorical columns in this particular dataset, then this can be used in order to train and build a machine learning model. So all of these one-hot encoded columns will be treated as numerals. However, when there are only 2 distinct values in a column, 1 and 0 in the case of one-hot encoded columns, then there is no risk of a machine learning algorithm making some kind of spurious comparisons with the values in the column. In this exercise, you'll transform the continuous data in a series into a set of categorical values, specifically binary values. There will be many instances where you need to make a decision based on a particular score. For example, you may take a look at the ratings out of 5 for a restaurant and then decide whether to go there for a meal. If there is a certain threshold for the restaurant rating, below which you will not consider the restaurant at all, then you may want to make use of a tool which will mark all the restaurants above a certain rating value into one category and then cast the remaining restaurants into another. There is such a tool available in scikit-learn, but what exactly is it? Next, you will need to distinguish between normalization and other scaling techniques which were covered during this course, such as standard scaling and min-max scaling. There are subtle variations between each of the scaling techniques. However, there is a significant difference between normalization and the others. But what exactly is it? Next, consider that you have a data set which includes the total quantity of goods sold for a vast array of products. All the sales quantities are present in a single column. However, the numbers here are typically very large, and in order to gauge whether a product has sold well, you want to express its total sales quantity as a proportion of the sales of the most popular product. Which scaler in scikit-learn can you use for this purpose? And finally, you will encode the vehicle type column in a particular dataset which contains 3 values: hatchback, sedan, and SUV. This is a feature column in your dataset, so you can use one of the 2 encoding techniques which were covered during this course. Which one and how exactly will you use it? Each of these topics were covered during this course, so please pause the video and take some time to solve them on your own. For the first task in this exercise, you had to transform a continuous series into a binary one based on a threshold value. The pre-processing tool which is available in scikit-learn to do exactly that is the binarizer. You can initialize a binarizer by setting a threshold value. If you apply the binarizer, for example, to the ratings out of 5 for a restaurant, then you may set a threshold of 3.5, in which case the binarizer will set a value of 1 for all restaurants which have a rating greater than 3.5. And the remaining restaurants with a rating of less than or equal to 3.5 will be marked with a value of 0. So in scikit-learn, you can initialize the binarizer by setting this threshold value, and then in order to transform the contents of a column to a binary value based on that threshold, you can make use of its fit_transform method. For the next task in the exercise, you had to distinguish between normalization and some of the other scaling techniques which were covered during this course. One significant way in which normalization is different from the other techniques is that it operates on each row independently. So a normalizer operates on a cross-sectional basis. The other scalars which we covered during this course operate on each of the columns in the dataset independently. So how exactly does a normalizer work? Well, consider that you have a dataset with 3 columns, and this is one row of data where the values are x, y, and z. When you apply the normalizer using the L2 norm, then the normalized value of x will be calculated using this formula, where you have x in the numerator and in the denominator you have the square root of the sum of the squares of x, y, and z. On the other hand, if you make use of the L1 norm when initializing the normalizer, then the normalized value of x will be calculated using this formula, where in the denominator you have the sum of the modulus of x, y, and z. For the next task, you needed to scale the sales quantities for each of the products in your dataset and express it as a proportion of the sales of the most popular item. So the way to do that using scikit-learn is to make use of the max app scaler, which is available in the pre-processing module. So once you have initialized your max app scaler, then you can make use of its fit_transform method in order to transform the contents of your sales quantities column. In many cases, the raw numbers for the sales quantities for any item may not convey how well that product is doing overall. You need to put it into the context of the most popular selling item in your list. In addition, there are many machine learning algorithms which will tend to attach a higher weight to columns which have very high quantities. In such a case, using a max app scaler will ensure that your sales quantity is always a value between 0 and 1. For the final task, you needed to encode one of the feature columns in your dataset which conveyed the type of vehicle. There were 3 distinct categories for your vehicle type as well. So when one of your feature columns contains string data, this cannot directly be fed into many machine learning algorithms. You will need to convert it to some numeric form. When the number of distinct values in your feature column are greater than 2, then you cannot apply the technique of label encoding, since many algorithms will assume that you can compare the numeric labels just as any other numeric values in your dataset. So the technique to employ in this case is one-hot encoding. So the way to do that using the pandas library is to make use of the get_dummies method, and to this you can pass as argument the column whose contents you want to one-hot encode. Your single column in this case will then be transformed into multiple columns corresponding to the number of distinct values in the column. In our example, we had 3 values in the vehicle type column, which were hatchback, sedan, and SUV. The first row in this particular example here represents a sedan, so the value of the sedan column for that is 1, and the value for the hatchback and SUV columns is 0. The second column here represents a hatchback, so in one-hot encoded form, the hatchback column is 1 and the remaining are 0. In this demo, we will be applying the techniques of scaling input feature data and also encoding them in order to build a linear regression model. The code for this demo will be written in Python 3, and we will be using Jupyter Notebooks as our dev environment. Here I have created a new Jupyter Notebook which is called Linear Regression with Scaling. So let us now begin coding our application. To begin though, I am going to disable warnings for this notebook. This is because some of the dependencies of the libraries we will be using will invoke some warnings, and these are likely to be fixed in future releases of the libraries and will just be an unnecessary distraction during the demo. So once the warnings have been disabled, we will import the first of the libraries which we require, and this is the pandas data frame library. Following that, we can quickly check the version of Pandas which is being used, and the version which I have as of this recording is 0.23.4. So if you run into any issues with Pandas, it could be because of a version mismatch. We move along now and then import the dataset which we will be using for this demo. This is the Kings County house price dataset. So it contains a lot of information about houses which were sold in Kings County, which is in the state of Washington in the United States. The dataset can be downloaded at www.kaggle.com/halfoxem/house-sales-prediction/home. To load this dataset, which is in the form of a CSV file, we make use of the Pandas read_CSV function, and this CSV file is included as part of your course material, and in my case, it is in the datasets directory of my workspace. So once the CSV file has been loaded from there, we can preview the dataset by making use of the head function of the Pandas data frame. And here we get an idea of what this dataset contains. So the second column contains the date of sale for the house, while the third column contains the price at which it was sold. All of the other columns to the right contain details about the house itself, the number of bedrooms, the number of bathrooms, the total living area expressed in square feet, and so on. If we scroll over to the right, we see other details including the zip code for the house, the year it was renovated, if at all, and also the total living area of the house. So there are a lot of details over here, and this particular dataset is often used in order to build a regression model where the features will include most of the details about the house, and then the value to predict is the price at which it was sold. That is precisely what we will do in this demo. But before that, let us explore the dataset which we have. First, we will make use of the len function of Python to check how many rows are present in this dataset. And we see that this includes over 21,000 rows. So there are more than enough data points for us to build a decent model. Following that, let us examine the distribution of each of the numeric fields in this dataset. And for that, we make use of the describe function of a Pandas data frame. And the output does convey this information, including the mean and standard deviation for each of the columns, as well as the min, max, and the values at various quartiles. We can see, for example, that the mean number of bedrooms for the houses in our dataset is about 2.1. The most important column for us, however, is the price, and this is the value we will try to predict using our linear regression model. So you can see here the values at the 25th and 75th percentiles, and that the median house in our dataset is about $450,000. Before one begins building their regression models, it is often good to visualize the data distribution, and for that we can make use of the matplotlib data visualization library. So in this case, in order to visualize the distribution for the house price, we will make use of something called a box plot. This is a very quick way for us to gather how the data for the house price column is distributed. So for this, we make use of the box plot function in matplotlib's pyplot object. The arguments which we pass to it include the series whose distribution needs to be plotted, which in our case is the house price. After the box plot definition, you can run plt.show, and this may be required in order to generate the plot immediately within your Jupyter notebook. This is not needed if you are running matplotlib in interactive mode. So once we execute this cell, we see the box plot which represents the distribution of the house prices. The box which you see includes all the data points within the interquartile range. So these represent the house prices between the 25th and 75th percentiles in our dataset. The horizontal line in the middle of the box represents the median value for the house price. The two vertical lines which extend out of the box are known as whiskers, and they represent a certain fraction of the interquartile range. So the box represents where half of the data points in your distribution are, while the whiskers should cover the range of most of the remaining points. Any points which are outside the whiskers are termed as outliers. So what this box plot tells us is that most of the houses in this dataset are within a price range of $1 million or so. However, there are a few outliers which we cannot see in this box plot. We move along now to the feature selection part of building our machine learning model. So here, we will get rid of some of the columns in our dataset which we deem unnecessary for the purpose of predicting the house price. This includes the ID for the house, as well as the date of sale and the latitude and longitudinal locations. We make use of the drop function of a pandas data frame, and because we wish to drop columns from our data frame, we need to set the axis argument to a value of 1. Following that, we will quickly preview our data frame just to ensure that those 4 columns have indeed been dropped. And then from the result, we can see that those 4 columns are no longer here, and the remaining columns which we see now will make up the feature columns when we build our model. Now that we have the features which we require, we will follow one more best practice, and this is to shuffle the dataset before we use it for training and testing. One way to perform this shuffling is to use the sample function of a pandas data frame, and this is meant to generate a random sample from your dataset. However, by specifying the value of this frac argument as 1, frac here stands for fraction, we are saying that generate a sample from the entire contents of the data frame. This will have the effect of shuffling the entire dataset randomly. Following that, we make use of the reset_index function so that the shuffled data frame will contain index values from 0 to 1 rather than a shuffled order of index values. We set the drop argument to true so that the old index is not included as a column in the newly shuffled data frame. So running this will ensure that we have a shuffled data set to work with. And then following that, we continue examining our data. First, we see the number of unique values in the grade column of our data frame. And for this, we make use of the unique function. So this shows us that the grade for a house ranges from anywhere between 1 and 12. This value represents the condition of the house being sold. Next, we check the number of unique values for the year in which the house was built. And as you might expect, there are many more values in this column. So both of these truly are numeric columns where a comparison can be made between their values. For example, a house with a grade of 12 is actually better than a house with a grade of 7. However, it is clear that the values in each of these columns truly are in a different scale. So there is some justification for scaling this dataset. Moving along though, let us first check whether there are any null values in our dataset. And for that, we make use of the isNull function in a pandas data frame. Here, we wish to flag those rows in our dataset which contain even a single null value in any of its columns. However, the output confirms to us that there are no null values present. So this dataset is something which we can now work with. Previously, we loaded the data for the Kings County house prices dataset into a pandas data frame. We then selected those features which we require in order to build our linear regression model. Following that, we performed a shuffling of the dataset, and then we ensure that there are no null values present which could interfere with the building of our model. So now we are ready to proceed and then begin the training process. But before that, we will need to split our dataset into train and test sets. For this, we can make use of this nifty utility available in the scikit-learn library, which is the train test split. So once we import this into our notebook, we will go ahead and define what our input features are and what the value to be predicted is. So the features, which is our X data, includes all of the columns in our house_data data frame except the price column. So this is exactly how we define the variable X. And then our Y variable, of course, is the price column of the house data data frame. This, of course, is without any pre-processing. That is, we have not performed any encoding or scaling of our input data. Following that, we make use of the train test split function, whose arguments include the X and Y data from our dataset, and we can also specify the size of the test data. In our case, we want to use 20% of our dataset for testing, which is what we specify in the test size argument. One thing to note is that the train test split function will in fact perform a shuffling of your dataset. This shuffling is performed by means of a random number generator, and the seed to be used for this can be specified in the random underscore state argument. And now that we have our train and test data, we are ready to initialize our linear regression model. For this, we import the linear regression class from the scikit-learn library, and then we initialize it by specifying no parameters. That is, we will simply use the default parameters for this model. Following that, we begin our training by fitting this model to our training data. For that, we make use of the fit function of the linear regression model, whose arguments are the input features as well as the y data. So we pass in xtrain and ytrain over here. So with that, we now have our linear regression model which has been fitted to our training data. You can see the default parameters which have been used over here, that it is working on a copy of the data, and then the values of the fit intercept, njobs, and normalized parameters. So now that this model has been built, how good a job does it do in representing the training data? That is, what is the R-square score for our model on the training data? Well, for that, we can make use of the score function of our linear regression model, and we simply pass in the xtrain and ytrain variables. And the output gives us an R-square score of 0.65, which shows that this model does a fairly good job representing the input features. However, 0.65 is still not a great R-square value. Later on, we will perform a one-hot encoding and scaling of our input data and check whether the R-square value improves. But we move along now and check the coefficients for each of the input features of our model. We can do this by accessing the coef underscore field of the linear regression model. And the output generates an array of coefficients, and the length of this array corresponds to the number of input features. The features with high positive coefficients have a positive effect on the house price, whereas those features which have a very high negative coefficient tend to bring down the price of a house. So these numbers are all well and good. However, it only makes sense if we were to match these coefficients with their corresponding columns. We do exactly that now, where we create a pandas series object, and the values in the series will be the coefficients which we just saw, and the index will be the names of the columns in our dataset. We will then sort the series object according to the coefficient values. And the output does give us some interesting insights. Right at the bottom, you can see that having a waterfront seems to be very strongly correlated with a high house price, which certainly makes sense, as is the fact that the grade of a house, that is, the condition of the house, has a positive effect on the house price. However, one interesting point to note in this particular data set is right at the top of this output. The greater the number of bedrooms, the lower the price for the house. This suggests that the more expensive properties in our dataset are probably the smaller condos, and these are all likely to be in the city of Seattle, where property prices are rather high. The larger houses in the dataset are likely to be in other parts of Kings County, where the house prices are lower. So we now have an understanding of what our model looks like. It is now time for us to put it to the test. Specifically, we will make use of the linear regression model's predict function in order to make predictions on our test data. So once we pass in the features of our test data and we get the predicted y values, we can take a look at these predictions. And from the output, we can say that these do indeed look like house prices. So the model is at least not wildly off with its predictions. However, in order to evaluate its performance, we will now go ahead and plot the actual values of the house prices against the predicted values. For that, we make use of the matplotlib plot function. And in order to make our plot easier to visualize and reduce the amount of noise, we will only be considering the first 150 values for both the actual and predicted house prices. We can also configure the plot, for example, by setting a label for the y-axis. And then following that, the plot is generated, and in fact, the predicted values for the house price do seem to correspond reasonably well with the actual values. The legend in the top right does show us that the blue line represents the predicted house prices, whereas the orange line represents the actual values. So while this is visual confirmation that a linear regression model does make predictions reasonably well, it'll be best for us to quantify its performance by calculating the R-square against the test data. So once again, we make use of the score function of the linear regression model, and we get an R-square of 0.64, which is in fact not that far off from the R-square on the training data. So clearly, this model does perform reasonably well on the test data as well. We can now move along to some of the other metrics in order to evaluate a model, and this is where we make use of the mean square error metric available in scikit-learn. We make use of this metric in order to see how far off the predicted y values are from the actual values, and this is the number which we get. This of course is a mean square value, which means that it is not in the same scale as the actual house prices. So in order to get that value in the same scale, we need to calculate the root of this mean square error. For that, we simply employ the square root function available in the Python math library, and we calculate the root of this mean square error, and we get a value of 210,000. So this is in the same scale as the house prices, and a root mean square error of 210,000, given that the average house price in our dataset is about 540,000, suggests that our model is actually doing reasonably well. However, further improvements can be made if we employ one-hot encoding and scaling of the input features, which is exactly what we will do next. We previously built a linear regression model using the Kings County house prices dataset. We did not perform any scaling or encoding of the input features, and we were still able to get an R-square value of about 0.64 on our training and test data. The root mean square error for that model was about 210,000 versus an average house price of about 540,000 in the dataset. In this demo, we will scale the input features and also perform a one-hot encoding of the zip code column, following which we will rebuild the linear regression model and then compare its performance versus the older model. So to begin, we will import the min-max scaler, which is what we will use in order to scale all the input features which are continuous in nature. Before we apply it, however, let us preview our dataset so that we have an idea of the kind of data we're working with. And yes, as you can see, there are plenty of features here which are continuous. However, there are also a couple of categorical features, such as the waterfront and view columns, and these columns we will leave out from scaling. We will now go ahead and then create our X variables, and for that we will separate out the continuous from the categorical data. We first create a separate data frame containing only the continuous values in our dataset, and this includes all of these columns which you see here in the house data frame. So once we have all the continuous features, we will go ahead and define one more data frame, and this contains the two categorical columns, waterfront and view. There is one more column to consider over here, and this is that of the zip code. So even though the zip code is numeric in nature, it is in fact a categorical value. This is because zip codes cannot be compared with each other like numbers can. For example, a zip code of 07302, which is in the state of New Jersey in the United States, is numerically less than a zip code of 1001, which is in the state of New York. And despite what many people might say, this does not mean that the zip code in New Jersey is in any way less than the zip code in New York. So zip codes are clearly categorical values, and the way to encode categorical features is to use the technique of one-hot encoding. In this case, we make use of the pandas get_dummies function in order to one-hot encode the zip code column of the data frame. Once we have this encoded set of columns in the x_zip code data frame, we can preview its contents. And we see here that this in fact contains 70 columns corresponding to the 70 different values of zip code present in our dataset. So now we have all the continuous values, the categorical values, and the one-hot encoded zip code values in separate data frames. It is now time for us to perform a scaling of the continuous data for which we will initialize our min-max scaler. Here, we explicitly set the range in which the scale values should be present. So all the continuous values in our dataset will now take values between 0 and 1. So once we run this cell, we have initialized our min-max scaler, and we can quickly confirm its parameters. And this confirms that it will be working with a copy of the data, so the transformation will not happen in place, and that the feature range will be between 0 and 1. Following that, we can take a look at the getParam function, and this confirms the value of the parameters for the scalar. We will now make use of the scalar in order to transform the continuous data in our dataset, and for that we make use of the fit transform method. So all the continuous data in our data frame will now be scaled to a value between 0 and 1. The value returned by fit transform will be a NumPy array, and before we create a data frame from it, we will define the column headers for the scaled values of the continuous data. So here we make use of the same columns as in the original dataset. Following that, we will create the data frame from our scaled X values, and then we make use of the columns list which we just defined in order to set the headers for this data frame. We can then quickly preview the contents of this scaled data frame, and what we have now is a scaled version of all the continuous data in our original dataset. So you can see here that just as we defined, all the values here are between 0 and 1. So with that, we have performed the two transformations which were necessary in order to prepare our data for training. We performed a one-hot encoding of the zip code column, and now we have scaled all the continuous features in our dataset. All of our input features, however, are now split across 3 different data frames. We will now concatenate these 3 data frames in order to have a single unified data frame with all of our X data. So here we make use of the pandas concat function, where we concat the scale data frame which we just created, and then to that we add the categorical data frame containing the waterfront and view columns, and also the one-hot encoded columns for the zip code. The argument of axis is equal to 1 for this concat function suggests that the concatenation should happen along columns. We then make use of the head function once more to preview the contents of our concatenated data frame. And we see here that all of the columns have indeed been concatenated together. So here we have all our continuous data, our one-hot encoded columns, as well as the 2 categorical columns, all in one data frame. Previously, we created a data frame which included all the scaled values for the continuous data in our dataset. We also included 2 of the categorical columns, and then we also concatenated to it the one-hot encoded values for the zip code. So with that complete, we are now ready to go ahead and then split our dataset into training and test sets. For that, we once again make use of the train test split function. And on this occasion, our X data is going to be the scale DF which we just created with all the concatenated columns. And then our Y data is going to be the price column from our original house data frame. Just as we did previously, we pass in both the X and Y variables over here to the train test split function, and we specify that 80% of the dataset will be used for training and 20% for testing. Following that, we are now ready to rebuild our linear regression model. If you're using the same Jupyter notebook as you did previously, then you do not need to include this import statement, as the linear regression model should already be present. This time, however, we will be redefining this linear regression model, and with one notable difference from the last time. Here we will specify a value for this fit intercept argument and set it to false. This is because when we include a one-hot encoding of any column in our input features, if the linear regression model tries to fit an intercept, this could lead to multiple problems related to collinearity. In order to avoid this, we need to set this value to false when we're using one-hot encoding. So we have now redefined our linear regression model, and then we can fit this to the training data. So for that, we make use of the fit function once more to which we feed in the X-train and Y-train variables which were created from the train test split. So with that, our trained model has now been created. It is now time for us to score this model, that is, to calculate the R-square value and see how good a job this model does in representing the training data. So remember that in the case of our previous model where we did not perform any scaling or one-hot encoding, the R-square value was about 0.65. So we now calculate the R-square value for our newly created model, and we will first do this using the training data. So once we have that, we see from the output that this R-square value is 0.8, which is significantly higher than the 0.65 we saw previously. So clearly, our scaling and encoding has greatly improved this model. One more way to view this model is to examine its coefficients, and this time we get a much larger array, given that the one-hot encoding alone created 70 columns from a single column. So now, if you would like to match these coefficients to the corresponding columns, we can create a pandas series object once more, where we have the coefficients along with the column headers, which will be the index for the series. We will once again sort the contents of the series according to the value of the coefficients. And viewing these coefficients with the column headers gives us some interesting insights. Once more, we see that the number of bedrooms is in fact negatively correlated with the price of the house. And now we can also see which specific zip codes in fact drive down the price of the house in our data set. The zip code of 98023, which you see here in the third row, represents a neighborhood which is close to the Tacoma Airport near Seattle. So intuitively, it makes sense that houses in this particular neighborhood will be lower, and the presence of a house in this particular zip code means that it will drive down the price in our data set. When we move further down, we can see that the zip code of 98039 is associated with a very high house price. And once again, this makes sense because this is a zip code which is very close to the waterfront and is right across the bridge from downtown Seattle. So with these coefficients, we have a good idea of which input features have what kind of effect on the house price predictions. We will now evaluate how well this particular regression model does on predicting house prices on the test data. For that, we once again make use of the predict function of the linear regression model, and the argument to this will be the input features of our test data. This will return a set of predictions for the house prices, which we will capture in this variable called y_predict. Once we have that, we will immediately go ahead and compare the predicted values of the house prices with the actual y values. And for that, we make use of matplotlib once more, and specifically the plot function in order to generate lines for the actual and predicted values for the house price. Once again, we only make use of the first 150 values in each series so that our graph does not contain too many values. So while we got a reasonably high R-square value on the training data, how well does this model do when it comes to making predictions on the test data? And from the graph over here, we can see that it in fact does rather well. If you compare this with the graph of our predictions from the previous model, you will notice that the predictions from our new model are much closer to the actual values than in the previous one. So at this point, we have some visual confirmation that our new model, built using scaled and one-hot encoded features, does seem to perform better than the previous one. However, let us now try to quantify this by getting the R-square value for this new model on the test data. So once again, we make use of the score function of the linear regression model, to which we pass in the x and y values from our test set. And the R-square value in this case is a very healthy 0.82. So this is much higher than the 0.64 which we saw previously when we did not perform any scaling or one-hot encoding. So clearly, both of those had a significant effect on improving the performance of our model. We will continue evaluating this model, and just as we did previously, we will calculate the mean square error. So once again, we get a rather large number, and this is because it's not in the same scale as the actual house price. To get that value, we will need to calculate the square root of this mean square error, and the output gives us a value of about 150,000. So this is once again less than the 210,000 we saw previously without scaling and one-hot encoding. So in every metric, both R-square as well as mean square error, our new model does perform significantly better than the previous one. This is precisely why we need to pre-process all our input features before using it to build a machine learning estimator. Previously, we saw how the use of a min-max scaler in conjunction with the technique of one-hot encoding significantly improved the performance of our linear regression model for the Kings County house prices dataset. We will now replace the min-max scaler with a standard scaler and see if this improves the performance of the model even further. So here we import the standard scaler from the sklearn preprocessing module and then initialize it using the default parameters. So we don't explicitly define anything here. Following that, we can view this standard scaler and we can see the 3 default parameters which have been set. We can also check these parameters using the getParams function. However, now we will apply this standard scaler on all the continuous variables in our input features. So here we make use of the fit transform method where we pass in our x_continuous data frame containing all the continuous values in our dataset, and then the output of this will be the scaled values of all the continuous data. These scaled values will be in the form of a NumPy array. So we will load the values into a pandas data frame and we will set the name of the column headers as well using the columns list which we created previously. And with that, we have now applied standard scaling to our continuous data. Just as a reminder, the standard scaler will operate on each of the columns individually and it will make sure that the data is scaled such that each column has a 0 mean and a standard deviation of exactly 1. So the values which you see over here are in fact the z-scores or z-scores of the corresponding actual values. So these values can be negative if they are less than the mean and positive if they are higher than the average for that particular column. So each of these values are represented in the form of standard deviations from the mean. So now that we have applied standard scaling to the continuous data, we will use that in order to create a data frame containing all of our x values. For that, we make use of the concat function once more, and we concatenate the standard scaled values with the categorical values and the one-hot encoded zip codes which were created previously. And with that, we have all of our input features together in one data frame once more. It is now time for us to perform a train test split. And on this occasion, our X data contains all of the standard scale continuous values along with the 2 categorical columns and the one-hot encoded zip codes. And our Y data remains the price of the house. We once again apply the train test split so that we have 20% of the data set which will be our test set and the remaining 80% will be used for training. We will now redefine our linear regression model, and just as we did previously, because we're using one-hot encoded zip codes here, we initialize this linear regression model with the fit intercept argument set to false. We'll then begin the training of our model by using the fit function to which we pass in the xtrain and ytrain variables created from the train test split. So with that, our linear regression model has been recreated. It is now time for us to evaluate this model and see how this compares to the previous model. So here we make use of the linear regression model's score function once more in order to calculate the R-square value on the training data. And we get this value of 0.805, which is almost exactly the same as with the previous model where we applied the technique of min-max scaling. So the use of the standard scaler has had no noticeable impact on the R-square value, at least on the training data. But how does this compare on the test data? Well, for that, we will get all the predicted Y values from the predict function of the linear regression model, and we will use that in just a little bit. But we will also calculate the R-square score on the test data this time. And the R-square value of 0.818 over here is once again very similar to what we saw previously when we applied min-max scaling. So when we evaluate the model using these numbers, there doesn't seem to be any significant impact of the standard scaling as opposed to min-max scaling. How about if we plot the actual and predicted values on a graph as we have done previously? Well, we can see that once more there is a very close match between the actual and predicted values, and visually we can't really tell whether there is a difference by using this standard scaler instead of the min-max scaler. So while we saw a significant improvement in the model's performance when we applied both scaling as well as one-hot encoding, substituting one scaler for another has had no noticeable impact on performance. This will not be the case with all datasets, however, so you must apply different scaling techniques to see what works best with your specific dataset. One thing we will explore a little further now is to see how the actual house prices vary from the predicted values by plotting the distributions using a box plot. Here we make use of the matplotlib box plot function once more, and in order to generate two separate box plots, we pass in both the actual values of y, which is in the y_test variable, and the predicted values of y as well. So how do these distributions compare? Well, you can see that as far as the boxes are concerned, they are in fact reasonably similar. What is different about these two boxes is in the case of the outliers. So the outliers in this box plot are represented by these little black circles, and these are not part of the box or the whiskers which extend from them. So these are houses whose prices truly stand out in this distribution. What these box plots tell us is that our linear regression model has not been able to accurately predict the house prices for these very expensive homes. This in fact should be expected since it is difficult to predict the behavior of outliers in any field. We will now recreate these box plots, but on this occasion, we will limit the range of y values so that our focus is on the box rather than the outliers. So here we set these y_lim values to range from -250,000 to 2 million. And the output here does bring the boxes more into focus. So one thing we can see here from the house price predictions is that some of the predictions were in fact negative. However, the distribution of the predictions very closely resembles the actual distribution of the house prices, and all of this is a confirmation of the reasonably high R-square and low mean square error values. In this exercise, you will identify some of the distinct characteristics of the standard scaler. Each of the scalars available in the scikit-learn preprocessing module have its own set of features. And the standard scaler is meant to scale your data so that it has specific characteristics. What exactly are they? Next, you will encode a column in your dataset which is called mattress size and contains 4 distinct values: full, twin, queen, and king. So this is a feature column in your dataset. So what kind of encoding will you perform and how? For the next task, you will recall 2 of the metrics which were used during this course in order to evaluate a regression model. Once you have finished training your model, you must evaluate it in order to see how well it fits the underlying data and how good a job it does when predicting on the test data. There are some pre-built metrics available in the scikit-learn library, and you'll need to come up with at least 2 of them. For the final task in the exercise, you will list down all of the details which are conveyed in a box plot. A box plot is a very useful visual aid which conveys a lot of information about a specific distribution. So what are the details which we can gather by looking at a box plot? Each of these topics were covered during this course, so please pause this video and take some time to perform each of these tasks on your own. For the first task in the exercise, you needed to recall some of the features of your distribution once you have applied the technique of standard scaling on it? Well, once you have made use of a standard scalar on your distribution, then the scaled values will have a zero mean. So whatever the values in your original distribution, after you perform standardization, the scaled values will have a mean of 0 and will also have a variance of exactly 1. Since the standard deviation is the square root of variance, this will also have a value of 1. All of the values in the series will be expressed as number of standard deviations from the mean. In such a case, the distribution is set to convey the z-scores of a particular column. When you're not sure what to make of a particular value by looking at the raw number, then it is best to put it in the context of the entire distribution, which is where the z-score comes in handy. For example, if someone comes to you and says that they scored about 65 out of 100 in a test, then you may think that is not a particularly great score. However, if they also convey to you that a score of 65 translates to a z-score of 3, then you will know that this is 3 standard deviations above average and is hence a very good score. A lot of machine learning models, including neural networks, require the input features to be scaled, usually using a standard scalar. For the next task, you needed to come up with a way to encode one of the feature columns in your dataset, which contain 4 distinct values. The values represented different matrix sizes: full, king, queen, and twin. So how exactly would you encode this column if you were to feed it to a machine learning algorithm? Well, when you have more than 2 distinct values in a feature column, then you cannot use label encoding, and you must instead use one-hot encoding. The way to do that using the pandas library is to make use of the get_dummies method, and as argument you can pass the column in your dataset which needs to be one-hot encoded. The one-hot encoder will transform the column which you passed as input into a number of columns. This number corresponds to the number of distinct values in the input column. In our example, because we had 4 different matrix sizes, there will be 4 new columns created by the one-hot encoder, each corresponding to a matrix type. The first row in the example you see in front of you represents a king size matrix. So in this case, the value in the king column is 1 and the value in the remaining columns is 0. And similarly, the second row in this example represents a full size matrix. For the next task in the exercise, you needed to recall some of the evaluation metrics which are available in scikit-learn and which were used during this course. One of the metrics which we used was the mean square error, from which we also gathered the root mean square error, or RMSE. This is the most widely used metric for the loss function of a regression model, and generally speaking, the lower the mean square error on your test data, the better your model is. Another very useful metric which evaluates how good a job your model does in explaining the variance in the underlying data is the R-square score. The higher the R-square score for your model, the better it usually is. There are a few drawbacks with the R-square metric though. For example, if you add more features to your dataset, then the R-square value can increase even if the newly added features don't really improve the model. In such cases, you can make use of the adjusted R-square, which calculates a score by taking into account the number of features. So if you add features which don't really improve the model in any way, then the adjusted R-square may actually decrease even if the R-square value increases or stays the same. So while these were the 2 metrics which we covered during this course, there are also other metrics which are available in scikit-learn. One of these is the mean absolute error. So while the mean square error is not on the same scale as the value you're trying to predict in your regression model, the mean absolute error is. And finally, you needed to recall some of the details which we can gather by examining a box plot for a particular distribution. So the box in a box plot is defined by its lower and upper edges. The lower edge conveys the first quartile value. That is, the value at the 25th percentile of the distribution. The upper edge of the box plot conveys the third quartile value, which is the value at the 75th percentile. Within the box, there is a horizontal line which represents the median value for the distribution. And then outside the boxes themselves, there are whiskers. The whiskers are vertical lines which extend from either side of the box, and their range is determined by the interquartile range. For example, the upper whisker extends to 1.5 times the interquartile range beyond the third quartile value. And similarly, the lower whisker extends to 1.5 times the IQR below the first quartile value. So this is the default range for the whiskers, and it is something which can be configured in Matplotlib and other data visualization libraries. Any of the values in your distribution which do not fit within the range of the whiskers and the box itself are the outliers in your distribution. So all of this data can be obtained simply by looking at a box plot. In this demo, we will build a classification model using the scikit-learn library. The development work will be done using the Python 3 language, and we will be using Jupyter Notebooks as our dev environment. Here, I have brought up a new Jupyter notebook, which I have named Classification with PCA. This is because once we have built the classification model, we will later go on to apply the technique of Principal Components Analysis, or PCA, in order to reduce the number of features which are considered by the model. So let us begin coding. And first, I'm going to disable warnings. Some warnings may pop up due to the libraries we will be using in this course, which in turn have dependencies on other libraries which may be getting deprecated. These warnings will merely distract us during the demo, so I'm simply going to disable them. However, they will have no bearing on the actual execution of the code. So following this, we will import the first library we require. This is the pandas data frame library. And once we have that, we will use pandas in order to load the data from a CSV file into a pandas data frame. So this will be the dataset we will be using during this course. And this dataset can be downloaded from https://archive.ics.uci.edu/ml/datasets/statlog plus %28 vehicle plus silhouettes %29. This dataset is available as part of your course materials, and in my case, it is present in a datasets directory in my workspace. So I am loading this vehicle.csv file into a data frame, and this is done using the read_csv function in pandas. So once we have populated this data frame, we can preview its contents using the head function. And what this dataset contains is the information about the silhouettes of a lot of different vehicles. The idea is to predict what type of vehicle it is by examining the details of the silhouettes. The input features over here include numerical representations for various details of the silhouette. This includes the compactness, circularity, the scatter ratio, elongatedness, and so on. The label for this dataset includes the class of vehicle, which could be a bus, a van, or even a sedan. So if you want to view the entire dataset, we can scroll over to the right here, and you see the class column right at the end. So there are clearly a lot of features over here, and we certainly don't need all of them in order to build a good classification model. Before we do that, however, we can examine our dataset, beginning with the total number of records. For this, we make use of the len function, and we see that we have a little more than 800 records to work with. Following that, we will go ahead and trim some of the features from this dataset, for which we will make use of the pandas data frame drop function. So as argument, we specify all the columns from the data frame which needs to be dropped, and we specify these 9 columns over here. In order to ensure that it is the columns which are dropped, we specify the argument for axis is equal to 1, and by setting the in-place argument to true, the original data frame will be modified with the columns dropped. So following this, we examine the first 5 rows of the data frame using the head function once more. And what we are left with are 10 columns in all. These include the 9 feature columns, and then there is the label at the end, which is the column named class. You can already see 3 of the different classes over here, which are van, bus, and Saab. You will notice that all of the columns in this particular dataset are numeric, but the class values are all in the form of strings. Machine learning algorithms cannot work with such string data directly, so we will need to transform this class column into some numeric form. This is exactly what we will do now by label encoding the class column. For that, we will import the label encoder class from the scikit-learn preprocessing library, and will then initialize this label encoder with all the default values, so we don't explicitly define any parameters here. Following that, in order to label encode the class column of our data frame, we will simply pass it as an argument to the fit transform method of the label encoder. Note here that we are casting the original labels as type string by making use of the asType function. This is because in the original dataset, the class column will be of type object, and the label encoder needs to work with string types in order to perform an encoding. So once we have label encoded the class column of our vehicle data frame, we simply preview its contents once more. And at the right, we can see that the class column now contains numbers or labels instead of the original string values. We will now examine the number of unique values in this class column. And this output shows us that there are 4 different classes of vehicles in the dataset. This in fact gives us a benchmark for the classification model. If we were to make random guesses for the type of vehicle, we should expect to come up with a 25% accuracy given that there are 4 different options. So our model needs to do significantly better than that when making its predictions. And now that all of the features as well as the label are in the correct format, we can define the x and y variables for our dataset. So we define the x variables as all the columns in the vehicle data frame except the class column. So these will be all of our input features, and then we make use of the drop function for the data frame once more. Following that, we define our y variable as the class column. So we now have 9 input features which represent various details about the silhouettes of vehicles, and these will be used to predict one y value which represents the type of vehicle. Now that our dataset has been prepared and all of our input features are continuous numeric values, we can go ahead and scale all of these input features. For that, we make use of the preprocessing module in the scikit-learn library, and then we make use of its scale function in order to scale all of our input features. The scaler which will be used to perform this will be the standard scaler. You may recall that the standard scaler will have the effect of adjusting the values in each of the columns of the data frame independently, such that each distribution has a zero mean and unit variance and standard deviation. And once we have scaled all of the input features, we will split our dataset into train and test sets. For that, we make use of the train test split function available in the scikit-learn library, and the arguments which we pass to it include all of our scaled input features, the y variable, and we can also specify the size of our test set. Here we say that 20% of the dataset should be used for testing, and the remaining 80% will be used for training purposes. The train and test data will be available in the variables x underscore train, x underscore test, y underscore train, and y underscore test. And now with all the training and test data ready, we can go ahead and build our classification model. So we have previously prepared our vehicle silhouette dataset so that it contains 9 input features, which are all continuous numeric values. We then went on to perform a standard scaling in order to standardize those continuous variables. And we also label encoded the class column of our vehicle dataset. Following that, we split our dataset into train and test components, where the training data is 80% of the dataset and 20% will be used for testing. We can now use that data in order to build our classification model. So the specific classifier we will use is the linear SVC classifier. So this is the linear support vector classifier available in the scikit-learn library. And we will initialize this without specifying any parameters. That is, we will simply make use of the default values. So once we have initialized this, we will go ahead and begin training this classifier. And for that, we will pass in our training data, the variables x_train and y_train. This training data is passed to the fit method of the support vector classifier. Once we run this, the model should be ready within a few seconds, and you can see all the initialized parameters for it here as well. And now that this model is ready, we can begin evaluating it against the test data. For that, we can make use of the model's score function, to which we pass in the x variables, that is the input features of the test data, as well as the actual values for the labels in the test data. So the x_test variable, which contains all of the input features, will be used by the support vector classifier in order to make predictions. These predictions will then be compared to the y_test variable, which contains all of the actual values. The value returned by the score function will be the accuracy of the models. How many of the predictions actually matched against the actual values? So the accuracy which we get here is 0.64, or about 64%. When you consider that there were 4 different classes of vehicles, then blind guesses would have given us an accuracy of about 25%. So an accuracy of 64% in this case is in fact a very good performance. However, given that there were a number of different features available in our dataset, it is possible that a lot of them were in fact very strongly correlated with each other. Having highly correlated features could hurt the model's performance when making predictions on real data, which is why it is always good to trim down the features which are not necessary. To check if there are fields in our dataset which are very highly correlated, we can make use of a correlation matrix. Following that, we can also visualize the correlations using a heat map. For this purpose, we will be using the matplotlib and seaborn data visualization libraries. So we import the matplotlib pyplot object as well as the seaborn library into our notebook. Following that, in order to view the correlation values between all of the features in our data frame, we can make use of the cor function. This will return a correlation matrix where each of the features in our dataset will be paired against each of the others, and then the corresponding correlation values will be displayed. We can in fact run the cell to see exactly what this correlation matrix looks like, and we can see all of the correlation values over here. So you have all of the features represented along the columns as well as the rows, and each of the cells represents the correlation values for the corresponding pairs of features represented in the row and column. The correlation values range from -1 to +1. A negative value implies a negative correlation, where the increase in one value corresponds to a decrease in the other. A positive correlation value suggests that an increase in the value of one feature results in an increase in the other as well. One issue with this correlation matrix, however, is that it contains a lot of numbers, and it makes it difficult for us to judge which pair of features are highly correlated. For that reason, we will now generate a heat map. You can think of a heat map in this case as a correlation matrix with colors which are used to signify the degree of correlation. So to create this heat map, we generate a matplotlib figure, and then within that, we use the seaborn library's heat map function. The arguments to this include the correlation matrix itself, as well as a number of arguments to format the heat map. I won't get into the details of that over here. However, it is enough for you to know that this will represent our correlation matrix in a much more intuitive way. So once we execute this cell, we have our heat map ready. So the lighter colors here represent highly positively correlated values, whereas the darker colors represent negatively correlated values. We can also view the correlation numbers within each of the cells, and we can clearly see that there are a number of features in our dataset which are strongly correlated. For example, the scatter ratio and the scale variance fields have a correlation value of 0.95, and the columns for circularity and scale radius of gyration have correlation values of 0.94. So it seems clear that many of these features in fact convey the very same information, and it is not necessary for us to include all of them when building our machine learning model. One way to handle situations where you have highly correlated features is to manually drop some of the columns which are highly correlated to others. This technique, however, is not only painful because of the manual intervention, but when you have two strongly correlated features, it may not be entirely clear which of those features has a strong cause and effect relationship with the value you're trying to predict. In this case, there is a serious risk that you end up dropping the feature, which goes a long way towards explaining the underlying variance in your data. To avoid that, we can employ the technique of principal components analysis, which we will explore next. We have multiple features in our dataset which are strongly correlated with each other, and it is not clear which of these features, in fact, is the best predictor of the outcome we are trying to predict. Then we can employ the technique of principal component analysis. Principal component analysis, or PCA, can be defined as a mathematical procedure which can transform a number of correlated variables into a smaller number of uncorrelated variables, which are called principal components. When you go from a large number of features to a smaller number of principal components, what you have effected is in fact called dimensionality reduction. Let us now see exactly how this works using scikit-learn. So to apply principal component analysis, we can simply import the PCA class from the scikit-learn decomposition module. We can then initialize this PCA model by passing in a few parameters. First, we specify the number of principal components it needs to use. So our original input data contains 9 features, and we will reduce this to a total of 8 principal components. The whiten parameter is used to ensure uncorrelated outputs, and we set this to true. Following that, we will fit this PCA model with our training data. For that, we can make use of its fit transform method, and we will pass in all of the X data, which contains all of the scaled values for our input features. The value returned by this fit transform will include the 8 principal components for each of the data points in our dataset. So this variable will be referred to as x_reduced. So once our PCA model has been fitted to our input data, we can make use of its explained variance field in order to view the amount of variance which is explained by each of the principal components. So what we get here is an array, and we can see here that the first principal component explains a lot of the variance, and the last of these 8 principal components has an explained variance value of just 0.04, which is less than 1/100th of the first principal component. Rather than look at these raw variance numbers, we can also make use of the explained variance ratio field in the PCA model to view what proportion of the underlying variance is captured by each of the principal components. So once we run this, we get one more array, and we can see here that the first principal component in fact explains about 64% of the total variance, while the last principal component explains just half of 1% of the variance. Do note here that each of these principal components here are arranged in the order of explained variance. Once we have these explained variance numbers, we can generate something known as a scree plot. This is where we plot a line for each of the principal components and their explained variances. So we make use of the matplotlib plot function over here, and then we pass in the explained variance ratio array to it. If you wish, you can format the plot so that there are labels for the x and y axes. And then this is what the scree plot looks like. So you can now very clearly visualize the drop in the explained variance for each of the principal components. There is a significant drop from the first principal component to the second one, and the drop is a lot less dramatic moving along from the fourth principal component onwards. So now that the PCA model has reduced the size of our input data from a total of 9 features to 8 principal components, we can build a new classification model using these principal components. For that, we once again make use of the train test split function, and on this occasion, we pass in the x underscore reduce data frame, which contains these principal components. Everything else is exactly the same as it was previously, where we pass in our y variables and we specify a test set size of 20% of the data set. So once we run this, we have our train and test sets, and we once again initialize a support vector classifier. On this occasion as well, we do not specify any parameters for this classifier and simply go with the default values. And then following that, we will use the fit method of the classifier in order to train our model. And though we pass in the xtrain and ytrain variables like we did before, on this occasion, the xtrain will contain the 8 principal components rather than 9 features. Following that, our model training is complete, and it is now time for us to evaluate this model. So now that we have performed dimensionality reduction, what effect will it have on the accuracy of our classifier model? For that, we make use of the score function of the model once more, to which we pass in our test data, and this returns an accuracy of about 64%. Coincidentally, this is the exact same score which we obtained when we did not perform dimensionality reduction. So, in spite of reducing the dimensions in our input, we were still able to get the same accuracy as we did previously. This suggests that our new model will be more robust because it is less susceptible to issues caused by the correlated values. And now that we have seen an accuracy of about 64% when we went from 9 features to 8 principal components, what if we trim down the number of principal components even further? So for that, we create one more PCA object, and on this occasion, we specify the number of components to be 6. Following that, we will feed in the 9 input features from our dataset in order to get 6 principal components, which will be captured in the x underscore reduced variable. We will now need to redefine our train and test data, for which we once again make use of the train test split function. On this occasion, the x underscore reduced values will contain 6 principal components. Now that we have our training and test data, we can redefine our linear SVC model, and on this occasion, we fit it with the new training data with 6 principal components. So our SVC model has been created, and it is now time for us to test how accurate it is with predictions. So we make use of the model's score function once more, and we notice that even with 6 principal components, we still get an accuracy of about 55%. So though this is not as accurate as having 8 principal components or 9 input features, an accuracy of 55% is still very good when there are 4 possible values to predict. So we have now seen how we can reduce the number of dimensions in our input data and still get very accurate results from our model. Our data set only contained a few hundred rows, and if you were to have a lot more data points, then the accuracy should improve even further. We have previously used a standard scaler in order to scale all of the feature columns in the vehicle silhouette dataset. Following that, we also applied the technique of principal components analysis in order to reduce the number of dimensions in our input data. In this demo, we will use a normalizer rather than a standard scaler on our input features and see how that affects the accuracy of our model. So we begin by importing the normalizer class from the scikit-learn preprocessing library, and we also import the NumPy library. We will then remind ourselves what our vehicle silhouette dataset looks like. So here we see that this contains 9 features and 1 label, which is the class column. These are the 9 features we ended up with after performing some trimming of the columns, and then we performed a label encoding on the class column in order to convert the string data which was there previously into these numeric labels. The accuracy of the various models which we created in order to predict the class of vehicles from all of these details about the silhouette range from 55% to 65%. In order to apply the normalizer on our feature columns, we will now redefine our X and Y data. So the X data will include all of the columns in our vehicle data frame over here, except the class column. So we make use of the drop function to accomplish that. The Y data, of course, only includes this class column. We will now preview the X data just to ensure that it does not contain the class column. And yes, this only includes the 9 features. Now, before we apply the normalizer to our input data, we need to transform it into a NumPy array. In order to do that, we can make use of the values field of this data frame. So when we run this cell, we are left with an array of values, and then we can simply view its contents now. And you can see this has all the data in the cells of the data frame. Following that, we can apply the normalizer to this data. So we initialize the normalizer with the default values, and then following that, we make use of the fit method of the normalizer, to which we feed in the array containing all of the feature data of our vehicle silhouette dataset. Just as a reminder, the normalizer will work on each of the rows in our dataset independently. That is, it works on a cross-sectional basis rather than a longitudinal basis. So once we run this cell, we are left with a normalizer which has been fitted to all of our input data. We can view this normalizer now, and we see the parameters it has been initialized with. We can confirm these parameters by examining the get_params method. And then following that, we can transform the contents of the input array by making use of the transform method of the normalizer. So this will have the effect of normalizing all of the features in our dataset across each row individually. We can now take a look at what this normalized dataset looks like. And since all of the values will be between 0 and 1 and will extend to multiple digits beyond the decimal point, we will set a precision value of 3 using NumPy's setPrintOptions method. Following that, we will print the first 5 rows of our normalized array, and then we see exactly what this looks like. We can now use this normalized data in order to build our classification model. However, before that, we will need to load its contents into a pandas data frame. So here we initialize a new pandas data frame with the contents of our normalized array. And if you'd like to round the contents of the entire data frame to 2 decimal places, then we can make use of the round function over here, where the first argument is the entire data frame. Following that, we can set the column headers for this data frame which we have just created. So these are the same column headers as existed in the original data frame. Now, in order to assign these column headers to the data frame which we have already created, we can set the columns field of that data frame to this list of columns we have just created. Now that we have all of the normalized features within one data frame, you may consider combining the normalized features with the corresponding labels so that you have both the features and labels within the same data frame. You can make use of the pandas concat function for that. And once we have this, you can see all the normalized features and which label they correspond to. We will now move on to defining our training and test data, but we will first define separate variables for our X and Y data. So the X data will include all of the normalized features, whereas the Y data will only include the class column from our data frame. Following that, we will split the data into train and test sets using the train test split function once more. Following this, we can now redefine our linear support vector classifier. So once we initialize the classifier, once again using the default parameters, we will fit the classifier to our training data. So we pass in xtrain and ytrain to this fit method, and within a few seconds, the model should be ready. We can now begin evaluating this model, and for that we make use of the classifier's score method in order to check the accuracy of this model's predictions against the test data. And what we end up with is an accuracy of about 52%. So this is not particularly great, given that all of the previous models which we constructed in fact showed better accuracy. Given that the label to predict in our dataset includes 4 different classes of vehicles, an accuracy of 52% is not a bad outcome. However, a normalizer is a better option when you're performing clustering or text classification, and this is not necessarily a good fit for the classification model which you're trying to build here. However, let us see if applying the technique of principal components analysis improves the accuracy of this model in any way. So here we make use of the PCA object and we define it to have 7 principal components. This again involves dimensionality reduction because the original data contained 9 features. We transform our X data to get the principal components from it, and then following that, let us examine the explained variance for each of the principal components. So the raw values of the variance don't really help us too much. So we will instead take a look at the explained variance ratios, and this gives us a better output. We can see, for example, that half of the variance is explained by the first principal component, and the last one only explains a fraction of 1% of the total variance. We can visualize this explained variance by means of a scree plot once more, and we pass in these explained variance ratios to the plot function of matplotlib's pyplot, and the output confirms that it is the first 2 principal components which explain most of the variance. And now that our dataset has been reduced to its 7 principal components, we will use that data in order to split our dataset into train and test sets. Following that, we will rebuild our classification model, but on this occasion, we will pass in some parameters. I won't get into the details of each of these parameters here, but you will be aware that you can tune the parameters of your model in order to see if that improves its performance when making predictions. So with this SVC model initialized, we can train it by fitting it to the training data. And now our linear SVC model is ready. So it is time for us to examine its accuracy against the test data. But before we do that, let us revisit the 2 big changes which we made. For one, we made use of principal component analysis to reduce the number of dimensions in our input data from 9 features to 7 principal components. Following that, we also tuned some of the parameters in our model, including the tolerance levels, as well as the penalty to apply in the loss function, in order to see if this improves the accuracy. Previously, we had an accuracy of about 52%, and now with these changes, let us see how this model does on the test data. And in fact, the accuracy has improved significantly to about 60.5%. So we have now covered several ways in which you can implement scaling, principal component analysis, as well as parameter tuning in order to build better machine learning models. In this exercise, you will apply an encoding technique on the target column of your dataset, which contains the following values: red, white, rose, and sparkling. As you may have guessed, this includes various wine varieties, but given these are all in the form of strings, they cannot be fed into most machine learning algorithms. So you will need to encode this data into some numeric form. How exactly can you do that using the scikit-learn library? Also keep in mind that this is the target column of your dataset and not a feature column. Following that, you will identify some of the features of normalization. There are many different scalars available in scikit-learn, and each of them have their own unique set of characteristics. However, the normalizer is distinct from the remaining in one very significant way. What exactly is it, and how exactly does normalization work? For the next task, you list down multiple reasons for using the technique of principal component analysis on your dataset. During the course, we covered that rather than use the features of your dataset directly, you can extract the principal components from those features and then specify exactly how many of those principal components will be used in order to train your model. But why exactly would you do that? For the next task, you will use one of the tools available in the scikit-learn library in order to split your dataset into training and test sets. If your dataset is represented in a pandas data frame, and since a pandas data frame is in fact a NumPy array underneath, you can make use of an array slicing notation in order to split your dataset. However, this is often cumbersome, and there is a ready-made tool available in scikit-learn to speed up the process for you. What exactly is it? And finally, you'll identify a method for viewing the correlations in your dataset by making use of the pandas and seaborn libraries. When you're working with very large datasets with a number of different features, it is very likely that a lot of the features are in fact correlated with each other. In such cases, you may want to visualize the correlations so that you immediately know which of the columns are correlated and which of these features you may potentially drop. How do we visualize these correlations though? All of these topics were covered during this course, so please pause the video and take some time to perform this exercise on your own. For the first task in the exercise, you needed to encode the target column of your dataset, whose distinct values included 4 different wine varieties. So when you want to transform the string values in your target column into numeric labels, then you can make use of the label encoding feature available in scikit-learn. This encoder will assign numeric labels to each of the distinct values in your target column. The way to do this using scikit-learn is to make use of the label encoder, which is available in the sklearn.preprocessing module. Once you have initialized the label encoder, you can make use of its fit_transform method in order to label encode a particular column of your dataset. In our example containing the 4 different wine varieties, there will be 4 different labels 0, 1, 2, and 3, which will map to the original string labels in alphabetical order: red, rose, sparkling, and white. While you could also use one-hot encoding in this case, since you are encoding the target column, it is okay to use label encoding and is in fact more intuitive. For the next task, you needed to identify some of the features of the normalization process and specifically how it differs from most of the other scaling techniques which are available. Well, one important distinction between a normalizer and the other scalars is that normalization operates on each of the rows in your dataset independently, whereas the other scalars typically operate on each of the columns independently. And how exactly does normalization work? Well, consider that you have a dataset which includes 3 columns, and one of the rows in your dataset contains these values: x, y, and z. When you normalize this row using the L2 norm, then the scaled value of x will be represented by this formula. So in the numerator you have x, and in the denominator you have the square root of the sum of the squares of x, y, and z. On the other hand, if you make use of the L1 norm when you create your normalizer, then this is the scaled value of x. Here the numerator is x and the denominator is the sum of the modulus values of x, y, and z. For the next task, you needed to recall some of the use cases for principal component analysis. So why exactly would we use it? Well, consider that you have a dataset which contains a huge number of features. Think not just several dozen, but potentially several hundred. Well, in this case, you can imagine that many of the features will in fact be correlated, and in such cases, it will be very difficult for you to know exactly which of the features has a meaningful impact on the value you are trying to predict. For example, consider that you have 2 strongly correlated features, x and y, and that your target value is z. You are not sure which out of x and y actually have the most meaningful impact on z. It could be that x is a strong predictor of z and y simply happens to be correlated with x, or perhaps you're simply mixing up the influence of x and y. It is these kinds of situations where the technique of principal component analysis comes in handy. This is able to extract the most significant features, that is, the principal components in your dataset. And once all of the potentially hundreds of features in your dataset have been transformed using PCA, then you can extract those components which explain most of the variance in the underlying data. So you could potentially whittle down from hundreds of features to a few dozen principal components in this case. That is, you have performed dimensionality reduction. Employing this technique may potentially speed up the training of your model since there are just a few principal components to deal with rather than hundreds of features. For the next task, you needed to make use of one of the tools available in scikit-learn in order to split up your data set into training and test sets. There were a few occasions during this course where we made use of the train test split utility available in scikit-learn. The arguments which you pass to this include all of your X data, that is your features, your Y data, and then you can specify what proportion of your data set will be used for testing. This will return the X and Y values for your training and test data. For the final task, you needed to recall how we can visualize correlations in our data using pandas and Seaborn. Well, we can view the actual numeric values for the correlations by generating a correlation matrix in pandas. For that, we can make use of the pandas data frame cor function, which will give us all the numeric values for the correlations between every pair of columns in the data frame. So once we have this correlation matrix, we can feed it into a Seaborn heat map. The heat map will make it easier for us to spot correlations in our data set when compared to going through all of the numeric values in a correlation matrix.
In this video, we'll consider research that involves preventing neural networks from overfitting. Deep neural networks contain several nonlinear hidden layers. Deep neural networks produce very expressive models that can learn extremely complicated relationships between inputs and outputs. In the presence of limited training data, many of the complicated relationships actually are the result of sampling noise. They'll exist in the training set, but not in real test data, even though that training data may be drawn from the same distribution. This leads to overfitting, and although some methods have been developed for reducing it, less than ideal performance has resulted. Model combinations almost always improve the performance of machine learning, and combining several models is most productive and useful when the individual models themselves are different and have different architectures, or at least they are trained with different data. However, this presents a monumental task, since training each large network requires massive computation. It is prohibitively expensive in terms of computational costs. Large networks also require huge amounts of training data, and there may just not be enough data in order to train different neural networks on different subsets of data. Dropout is a technique that can address both of these issues. Dropout not only avoids overfitting, it provides a method for efficiently combining many neural network architectures. Dropout works by dropping out hidden and visible units along with their associated incoming and outgoing connections from the network. The choice of which units get dropped is random. And the idea here is to take a large model that has a propensity to overfit and repeatedly sample and train what are effectively sub-models. So research has shown that the dropout method improves performance of neural networks across a number of domains, and the level of the performance advantage varies with domain. But this suggests that dropout is a successful general technique, not specific to any one domain, and the idea behind dropout may also be extended to restricted Boltzmann machine as well as other graphical models. In this video, we'll consider research related to multi-label learning algorithms. Multi-label classification and the closely related multiple output classification are variants of the standard classification problem, with multiple labels possibly being assigned to each instance. Multi-label learning algorithms represent a generalization of multi-class classification where a single label categorizes instances into exactly one from multiple classes. But with multi-label classification, there is no restriction on how many of the classes the instance may be assigned to. Essentially, this means finding a model that can map a number of inputs to binary vectors. Multi-label data has some inherent challenges. For example, growth in this area has led to tremendous growth in labels, and hence exponential growth in the combination of labels. There is also a tremendous computational cost associated with building and querying models, and machine learning data also typically presents non-trivial feature properties like high dimensionality, unbalanced data, as well as interdependencies amongst labels. When evaluating multi-label learning algorithms, it's been found to be quite useful to use two types of metrics. Those are metrics used to evaluate bipartitions and metrics used to evaluate rankings. Metrics that are used to evaluate bipartitions consist of two groups, label-based and example-based metrics. Label-based metrics are calculated for each label and then averaged across all labels, while metrics for examples are calculated for each test example and then averaged across the entire test set. For evaluating rankings, several measures are used, including one error, which evaluates how many times the top-ranked label did not appear in the set of possible labels, hence the lower the better. Coverage, which measures the average depth in the ranking in order to cover all labels correlated with an instance. Ranking loss, which measures an average fraction of label pairs inappropriately ordered for the instance. Is-error, which measures whether a ranking is perfect or not, as well as average precision, margin loss, and ranking error. The research differentiates between two typical approaches to multi-label learning methods: problem transformation and algorithm adaptation. Problem transformation transforms the machine learning problem into one or more single label problems, while algorithm adaptation means extending a single label algorithm to handle multi-label data. Research has shown that the best performing overall methods were random forest of predictive clustering trees and hierarchical multi-label classification. These were followed by binary relevance and classifier chains. Overall, tree-based methods performed faster both in training and prediction. Deciding which approach to use, however, depends on the problem and which requirements are most pressing, whether that is efficiency, flexibility, predictive performance, or any number of other requirements. In this video, we'll consider some research related to deep residual learning for image recognition. Deep learning algorithms consist of many stacked layers of neurons, with the layers being fully connected. The depth of neural networks is key to performance. Deeper neural networks have been shown to be more adept at automatic feature extraction, which increases their ability to generalize to new problems, for example, classifying previously unseen images. Deep neural networks have also seen more optimization due to the availability of high-performance GPUs and better, larger databases. One major issue with deep learning is that the deeper you go, the more prevalent is the loss of information, and it becomes more pronounced as networks go very deep. To understand, consider decision-making as a function of event history. Events occur in sequence. Past events influence future events, and a decision maker that can only see the last past event makes decisions based on the assumption that this most recent past event is encoded with everything that's required to be known about all previous events. This assumption is fine for very short history of events, since there is typically a strong correlation between close sequential events. But with deep learning, information is gradually lost in the depth, and this results in decision-making that is quite short-sighted. To address this issue, which we call gradient vanishing, the notion of residual connections is proposed. These residual connections are connections that are made between non-sequential layers. In a network with normal connections, information is just passed from layer to layer. Information concerning the past state of an image, for example, is very limited, with all activations based only on the new features. With residual connections, we can take the future map from a layer that we'll call T and add it to the output of layer T plus 2, for example. Research results have proved very successful, with a trained 100-layer deep neural network exhibiting increased accuracy recognizing images. This led to additional follow-on work, which has also shown that the residual network can in fact improve performance not only for deep, but also for shallow networks. And this agrees with the expected improvement in accuracy, since residual functions provide important information about the original state of the data. In this video, we'll look at some of the research involved in transferable features in deep neural networks. Numerous deep neural networks have been trained on natural images, and the thing is that they share curious phenomena. On their respective first layers, they learn features that are very similar and resemble Gabor filters or color blobs. These first layer features are not specific to any particular dataset or task, so in that regard, they should be seen as general features that are applicable to many datasets and tasks. However, features must eventually move from general to specific by the time that the final layer of the network is reached. This feature transition, which is common with deep convolutional neural networks, has not been studied to any great extent. But we do understand that somewhere along the transition from general at the start to specific at the end, there must somehow occur from layer to layer or neuron to neuron that transition. Research objectives in this area include quantifying the degree to which layers are general or specific, and this considers neurons at each layer of a deep convolutional neural network. Research results has demonstrated that transferability between layers is negatively affected in two ways. First, there are optimization challenges due to splitting networks in the middle of fragile or tenuously co-adapted layers. And secondly, transferability is also negatively affected by the specialization of higher layer features associated with the target task at the expense of performance. Additional results include understanding the fact that either situation can and does dominate, and that dominance depends on where features are transferred from, that is, from the top, middle, or bottom of the network. It was also found that transferability decreases as the distance between tasks increases. So there's an inverse relationship there. And it was also seen that initializing a network with transferred features can significantly boost generalization performance, which could be a valuable general technique for improving the performance of deep neural networks. In this video, we'll have a look at some research associated with large-scale video classification. Convolutional neural networks represent a powerful model class for image recognition. Because of the prevalence of images and videos on the internet, many algorithms have been developed to analyze the semantic content of image and video for various applications, including for search and summary. Associated research objectives in this area include evaluating convolutional neural networks for large-scale video classification, against a new dataset of 1 million YouTube videos belonging to over 400 classes. Previous related work in this field involved a three-stage standard approach to video classification. In the first stage, local visual features describing a region of video are extracted. Then in the second stage, features are combined into a fixed-sized video-level description. And then finally, in the third stage, a classifier, for example, a support vector machine, is trained on the resulting bag of words to distinguish between the relevant visual classes. Convolutional neural networks are biologically inspired classes of deep learning models that replace the three stages with a single neural network. But there had been, to this point, relatively limited work on using convolutional neural networks for video classification. In consideration of the types of research models used for this research, each video is treated as a collection of short, fixed-sized clips. There exist a number of options for extended connectivity, and in particular, the research models use three general connectivity pattern groupings: early, late, and slow fusion of information. Multi-resolution convolutional neural networks are used and achieve a compromise between training time and performance by using two streams of processing: the fovea and context streams. The fovea generally for visual acuity and color discrimination, and the context stream for the context. This results in manageable learning optimization while taking advantage of data augmentation and pre-processing, which reduced the effect of overfitting. Results showed that convolutional neural network architectures can learn powerful features from data that is weakly labeled, and this greatly exceeds the performance of typical feature-based methods. It was also found that the slow fusion model consistently performed best, and in the end, the results demonstrate that mixed resolution architecture consisting of a low resolution context and a high resolution fovea stream effectively sped up convolutional neural networks without sacrificing accuracy. In this video, we'll consider research related to common objects in context. A primary goal of computer vision is to understand visual scenes. This incorporates numerous tasks, including understanding what objects are present and localizing those objects in 2 and 3 dimensions, determining object and scene attributes, and characterizing relationships between objects, thus giving them some semblance of context. The established object classification and detection datasets prior to this research are very good at assisting in the classification and detection problem, but there were none that were particularly adept for assisting in scene understanding, and this is what we call context. The chief research objective in this area is the establishment of a new large-scale dataset that addresses 3 main challenges involved in scene recognition. That's detecting non-canonical object perspectives, the precise two-dimensional localization of objects, as well as the contextual relationship amongst objects. For example, consider performing a web-based image search for a bicycle. Current trained systems perform well on canonical views, especially when the target object appears in profile, unobstructed, approximately in the center of a well-composed clean image, but struggles to recognize objects when they appear in some context in a non-canonical view. Characteristics of a proposed dataset include complex images of typical, everyday, ordinary scenes with common objects as they exist in their natural context. Object instances are labeled using per-instance segmentations, which assists in precisely localizing the target object. Research results include a dataset that is established with some 330,000 images. This dataset has several features that support object recognition in context, including stuff segmentation, where so-called stuff categories include materials and objects that don't have a clear boundary, like sky and grass, for example. There are also 1.5 million object instances in 80 object categories, along with 91 stuff categories, 5 captions per image, and 250,000 people complete with key points. The dataset, incidentally, is now published as COCO, Common Objects in Context, and sponsored by a number of organizations, including Microsoft and. In this video, we'll consider research involved in generative adversarial networks. Deep learning algorithms have been established as industry standards for producing rich, expressive, hierarchical models. They are proficient at representing probability distributions for typical artificial intelligence and machine learning applications. For example, audio waveforms that include speech. Deep learning has been deployed to great success in discriminative models. These are typically models involving high dimensionality input to a label class. These striking successes were primarily based on backpropagation and dropout algorithms using piecewise linear units with particularly well-behaved gradient traversals. Deep generative models have seen less success and impact, in part due to the difficulties inherent in approximating probabilistic computations and difficulty taking advantage of piecewise linear units in a generative context. In light of these challenges, research was proposed for new generative model estimation, which works by using a generative model and an opposing or adversarial one. A discriminative model evaluates samples and learns to recognize the origin of the samples, that is, whether from the data distribution or from the candidates produced by the generator. Competition drives improvement until such time that generative candidates are indistinguishable from genuine samples. In practice, generative adversarial networks work with a known dataset that is used to initially train the discriminator. The generator is typically seeded with a randomized input from some predefined space, and samples then produced by the generator are evaluated by the discriminator, with backpropagation being applied to both networks, resulting in the production of better images, while the discriminator also improves at recognizing synthetic images. Research has resulted in adversarial networks being successfully deployed that produce photorealistic images, visualizing, for example, industrial design clothing and digital gaming objects. They've also successfully modeled patterns of motion in video, reconstructed 3D objects from images, been used to adjust and improve astronomical images, and they've even created realistic original artwork. Several new areas of advanced research have also been identified for generative adversarial networks involving semi-supervised learning to improve performance of classifiers and efficiency improvements in training performance. In this video, we'll consider research associated with scalable nearest neighbor algorithms. For typical computer vision and machine learning problems, large training sets are critical for excellent performance. The most computationally expensive component in several computer vision and machine learning algorithms is finding nearest neighbor matches for highly dimensional vectors. Research objectives in this area include proposed new algorithms for approximate nearest neighbor matching. For matching high-dimensional features, the most efficient algorithms are the randomized KD tree and proposed new algorithm, the priority search k-means tree. These algorithms are compared with previous algorithms for nearest neighbor matching classified in 3 categories: partitioning trees, locality-sensitive hashing, and nearest neighbor graph methods. Considering research results, This is a comparison of the two algorithms that prove to be the best at finding fast approximate nearest neighbors, the multiple randomized k-trees and the priority search k-means tree, and they're compared with existing approaches, the approximate nearest neighbor and locality-sensitive hashing algorithms. The priority search k-means algorithm outperforms both the approximate nearest neighbor and the locality-sensitive hashing algorithms by almost an order of magnitude. In this figure, we see the performance obtained by employing a distributed processing framework. Here we're looking at the results of using 8 parallel processes on 1, 2, and 3 machines. Now, even though the same number of parallel processes are used, the performance markedly increases when these processes are distributed over multiple machines. And this can be easily explained by considering memory access overhead. When more machines are used, fewer processes are running on each machine, so fewer memory accesses are required. Overall, the proposed algorithms were compared against previous algorithms, and the results demonstrate improved performance with the ability to deploy over a distributed processing framework. The research was subsequently released as an open source library named FastLibrary for Approximate Nearest Neighbors, and it grew into one of the most popular libraries for nearest neighbor. In this video, we'll consider research associated with facial alignment and ensemble of regression trees. One of the keys to facial recognition problems is facial alignment. Using an ensemble of regression trees, facial landmark positions can be estimated directly from a sparse subset of pixel intensities to achieve real-time performance with high-quality predictions. Related research objectives involve the development and presentation of a general framework based on gradient boosting. The goal is to learn an ensemble of regression trees while optimizing the sum of square error loss and naturally dealing with missing or partially labeled data. In addition, research should demonstrate efficient feature selection resulting from the use of appropriate priors while exploiting image data structure. In this research, the proposed method uses a cascade of regressors. Each regressor in the cascade is learned, and the core of each regressor function is the tree-based regressors which are fit to residual targets during the gradient boosting algorithm. The method extends the functionality to handle situations where some of the facial landmarks are not labeled in some of the training images. The results of this research include a general framework based on gradient boosting that's capable of learning an ensemble of regression trees to optimize the sum of square error loss and naturally deal with missing or partially labeled data. The framework was shown to be faster at reducing error than previous methods and fully able to deal with missing or partially labeled data. In this video, we'll consider research related to learning deep features for scene recognition. One of the trademark tasks of computer vision is scene recognition, which essentially provides the definition of a context for object recognition. Recent progress in object recognition is partially due to the availability of large, relevant datasets like ImageNet, along with advances made in the effective and efficient use of convolutional neural networks for learning high-level features. Convolutional neural networks are inspired by the hierarchical organization found in the human brain, with layers of escalating processing complexity. This architecture, working in conjunction with large databases, have been able to achieve remarkable performance in object classification. Even though convolutional neural networks are very impressive for learning features for object recognition, their use in scene recognition hasn't been on the same pace. One possible reason for this difference is that current deep features training, for example, using ImageNet, is just not up to the task of scene recognition. The fact is, that higher-level features learned by object versus scene-centric convolutional neural networks are very different. It comes down to this. Iconic or canonical images of objects don't include the richness and variety of visual information that images of scenes and environments require for learning in order to be able to recognize them. Objectives of research in this area include demonstrating that higher-level features learning for object versus scene-centric convolutional neural networks is different, and that iconic images of objects have a lack of diverse visual information required for learning to recognize scene-centric images. And secondly, to generate and introduce a new scene-centric image dataset that does contain the diverse visual information required for scene-centric image recognition. Research in this area includes the proposed Places database, a scene-centric database containing more than 7 million images along with 476 place categories. This is a rich and diverse image dataset with detailed, complex images that can be used to train algorithms that require huge relevant datasets for effective training like those required by convolutional neural networks. Research results showed that deep convolutional neural networks require massive amounts of data for effective learning. The research resulted in the Places database, which includes millions of labeled images with sufficient detail and complexity to effectively train scene-based convolutional neural networks. And using this database, state-of-the-art performance was achieved using deep features against all current benchmarks. In this video, we'll look at research proposing Extreme Learning Machine, which is used for regression and multi-class classification. Because of the simplicity of their implementations, least square support vector machine and proximal support vector machine have seen wide adoption in binary classification applications. So why use Extreme Learning Machine? Well, the conventional least square support vector machine and proximal support vector machine can't be used directly in regression problems, nor can they be used directly in multi-class classification problems. Research objectives include demonstrating that both least square support vector machine and proximal support vector machine, as well as other algorithms, may be simplified to produce a unified learning framework known as Extreme Learning Machine, and to use Extreme Learning Machine directly to demonstrate its efficacy in regression and multi-class classification problems. Extreme Learning Machine is effective for generalized single hidden layer feed-forward networks. In this case, the hidden layer, or feature mapping, doesn't require tuning. These single hidden layer feed-forward networks include, but are not limited to, support vector machine, polynomial network, and the conventional feed-forward neural networks. Results of this research show that Extreme Learning Machine provides a unified learning framework with widespread feature mappings that can be applied to regression and multi-class classification directly. And from an optimization method point of view, Extreme Learning Machine has much milder optimization constraints versus least square support vector machine and proximal support vector machine. In addition, at least in theory, it appears that compared to Extreme Learning Machine, least square support vector machine and proximal support vector machine achieve suboptimal solutions and further require computational complexity far greater than that required by Extreme Learning Machine. In addition, simulation results demonstrated that Extreme Learning Machine shows better scalability and similar up to far better generalization performance with a much faster learning speed, up to thousands of times faster than traditional support vector machine and least square support vector machine. In this exercise, you'll practice what you learned about research topics in machine learning and deep learning. You will list the two types of leading-edge multi-label learning algorithms, describe how features transition, and discuss research results, including the listing of some advantages of using convolutional neural network models for image recognition, also discussing how KD-tree and K-mean tree algorithms perform, especially relative to previous nearest neighbor matching algorithms, and finally discuss scene-centric database research. For example, why would you use a scene-centric database, and what are some properties of the Places scene-centric database? Now pause the video and perform the exercise, and when you're finished, come back here for my solution. Okay, so the first task, list the two types of leading-edge multi-label learning algorithms. Research differentiates between two typical approaches to the multi-label learning methods, and this is problem transformation and algorithm adaptation. Problem transformation transforms the multi-label problem into one or more single-label problems, while algorithm adaptation means extending a single-label algorithm to handle multi-label data. Next, describe how features transition. Well, features, you should understand, must eventually move from general to specific by the time the final layer of the network is reached. This feature transition, which is common in deep convolutional neural networks, although it hasn't been studied to any great extent, we do know that somewhere along the line, the transition from general at the start to specific in the end, a transition must occur from layer to layer and neuron to neuron. Okay, next, discussing research results, and first, convolutional neural network models. Convolutional neural network architecture can learn powerful features from data that is weakly labeled, and convolutional neural networks have performance that greatly exceed the performance of typical feature-based methods. The slow fusion model consistently performs the best. You should understand also that using convolutional neural networks with mixed resolution architecture that consists of a low resolution context and a high resolution fovea stream effectively speeds up convolutional neural networks without sacrificing accuracy. Next, we'll discuss how KD-tree and K-mean tree algorithms perform. Research has showed that KD and K-mean tree algorithms demonstrate improved performance versus prior nearest neighbor algorithms. And further, they can be deployed over a distributed processing framework, a scalable platform that can use multiple servers for even better performance. And now, discussing scene-centric databases. So first, why use a scene-centric database? Well, with respect to scene recognition, you should understand that convolutional neural networks are inspired by the hierarchical organization found in the human brain, with layers of escalating processing complexity. And this architecture, in conjunction with large datasets, has been able to achieve some remarkable performance in object classification. However, even though convolutional neural networks are very impressive for learning features for object recognition, their use in scene recognition hasn't kept pace. And one possible reason for this difference is that current deep features training, for example using ImageNet, just isn't up to the task for scene recognition. The fact is that higher level features learned by object versus scene-centric convolutional neural networks are different. Iconic images of objects don't include the richness and variety of visual information that images of scenes and environments require for learning in order to recognize them. And now, some of the properties of the Places database. You should understand that the Places database is a scene-centric database containing more than 7 million images, or at least millions of labeled images. You should understand that this is a rich and diverse image dataset with detailed, complex images that can be used to train algorithms that require huge relevant datasets for effective training, like those required by convolutional neural networks.
Objective of this video is to define reinforcement learning and specify the essential elements used to depict reinforcement learning. Objective of machine learning is to ensure that we get continuous improvement in the performance of machines, or probably programs, over time. The simplified way of implementing a process that improves machine learning with time is using reinforcement learning. We can consider reinforcement learning as a machine learning approach through which intelligent programs that contains agents work in a known or unknown environment to adapt and learn based on given points. It's one of the important learning area where we can treat it as a science of decision making. Reinforcement learning cannot be classified as supervised or non-supervised because of its basic features. One of the primary usage of reinforcement learning is to ensure that softwares are capable of identifying the best behavior or the actions that need to be taken. And finally, reinforcement learning is oriented more towards goal. This is the reason why it is also called as goal-oriented algorithm. Now let's try understanding different elements of reinforcement learning. We have agent. We can consider agent as a component which takes actions. For example, if you want to make a product, in order to deliver elements, you need an algorithm. And that algorithm here is agent. Actions are set of all possible moves which agent can make. Action must be self-explanatory. Then third important element that we consider in reinforcement learning is the discount factor. Discount factor is multiplied by future rewards as discovered by the agents in order to eliminate these rewards' effect on the agent's choice of action. Then we have environment. Primary objective of environment is to take agent's current state, an action as input, and return as output the agent's reward and its probable next state. Then we have state itself, which is a concrete and immediate situation in which the agent finds itself. Then we have reward. Reward is the feedback by which we measure the success or failure of the action which was taken by the agent. Agents are guided by policy. In other words, policy is the strategy that agent employs to determine what should be the next action which is based on the current action. Policy maps states to action and the actions that promises the highest reward. Then we have value. Value is significantly long-term return with discount. Now let's try to understand the process which reinforcement learning follows. You have your observations. Your observations are read and it is passed on to agent. Depending on the observations, agent will decide what action it has to take and what is the reward which environment may provide to agent. Apart from reward, it also publishes the next possible state. Objective of this video is to recognize the key differences between the reinforcement learning and machine learning paradigm. In order to establish learning patterns, we can utilize two different schools of thoughts. One is machine learning and second is reinforcement learning. In order to establish learning patterns, we can utilize two different schools of thoughts. One is machine learning and second is reinforcement learning. Primary difference that classifies machine learning and reinforcement learning are: machine learning works on existing or given sample data from where it will derive the learning model. But when it comes to reinforcement learning interacts with the environment and collects the necessary information. Machine learning operates with interactive software system, but when we talk about reinforcement learning, it works better in artificial intelligence with human interaction. In machine learning, we will have various different algorithms which are available for use, which can be classified as supervised and unsupervised. But in case of reinforcement learning, we don't use supervised or unsupervised algorithms. Some of the critical algorithms that falls under machine learning are regression and classification, whereas when we talk about reinforcement learning, it can be built on various different parameters. For example, it can be based on exploration, it can adopt decision processes, it can also utilize policy-based learning, deep learning, and value learning. Finally, let's try to understand machine learning and reinforcement learning differences using some examples. Machine learning works well when it identifies a general formula from a given set of examples, whereas reinforcement learning facilitates as controlling mechanism. Machine learning takes responsibility of analyzing the given input and output of a function to learn. Reinforcement learning includes control theory, and you can also utilize reinforcement learning to implement gaming theory. Machine learning needs generalized models in order to ensure that it is able to implement classification, whereas reinforcement learning depends on learners' interaction with the environment to extract the desired outcome. Objective of this video is to depict the flow of reinforcement learning using agent, action, and environment. Functionality of reinforcement learning depends on various essential elements. Some of the elements which are involved in reinforcement learning mechanism are agent, which is the primary component and is also called as decision maker. Then you have environment, which contains values which need to be read by the agents in order to identify the right decision. In other words, environment represents the surrounding area. Then we have state. State is maintained by agent in order to learn the environment and also decide how state transition will occur. Then you have action. Action is the task which agent conducts within a given environment. Finally, you have rewards. Reward is used to train the agents. Now let's try understanding fundamental reinforcement learning flow. First thing that we need to understand is reinforcement learning works in interconnected manner where you will have different components communicating with each other. Reinforcement learning also need to ensure that you have distinct communication channel between agent and environment. And this communication is done in order to ensure that communication of rewards with objective can be established. Finally, we need to also ensure that reinforcement learning flow contains state transition, where you will have state transition from one state to other state, and this state transition occurs as a result of various actions. Now let's try understanding deep reinforcement learning mechanism. You'll have various components. For example, you have agent, which manages state. Then you have environment. Agents will take action on environment. You will have rewards and you will have observations. Apart from that, agent will also contain deep neural network, which can be driven by policies. When your reinforcement learning is integrated with deep neural network, it is called as deep reinforcement learning. Current example clearly indicates that your agent can have DNN, which can communicate with the environment. Now let's see how agent and environment will work from perspective of reinforcement learning. Agent's responsibility will be to receive scalar rewards, which primarily is represented by RT. It should receive observations and it should invoke execution of actions. Whereas when we talk about environment must receive actions. Instead of receiving, it will emit observations and it will also emit rewards, which in either case is scalar. Objective of this video is to illustrate the different scenarios of state changes and transition processes applied in reinforcement learning. Let's try to understand concept of state and actions first. State describes what is the current situation of an object or of an agent. Action is the task that takes responsibility of moving from one state to other state. In short, action is the task that is performed by the agents. Finally, action performed in a state may create a reward, and rewards can be either positive or negative depending on the outcome. Now let's take a scenario. First component here is agent. Assume that we are talking about reinforcement learning in terms of sales. Agent would be the salesperson because he is there to ensure that there is some activity. Sales channel becomes the environment which drives a medium of sales. Now, whenever a salesperson takes an action in order to complete a sales, it means that there is transition from one state to other state. Finally, salesperson may get some sales, which is considered as reward. In other words, whenever there are actions, there will be state change, and that state change may provide some reward which can be positive or negative. For example, if a sales state change does not conclude in sale, it means it's negative reward. But if it concludes in sales, it means it has given positive reward. Now let's try understanding state transition impact. Every transition will have different reward values. These reward values will involve gamma values, which are also called as discount factor. Assuming that gamma value is 0, it specifies that reward is associated with the current state, but when your gamma value is 1, it specifies long-term rewards. Now we have to go and identify how actually we can have state transition. There are various different reasons because of which there will be state transition. One is when an action is taken, and second is which is dependent on time. Representation 1 specifies that in current scenario, you have transition from one state to other state which changes with time, and T indicates that particular change. In representation 2, we can see that there is change in the state because of some action. Objective of this video is to recognize the concept and role of rewards in reinforcement learning. Reinforcement learning is primarily based on the idea of reward hypothesis. All goals can be described by maximization of the expected cumulative rewards. That's the reason why in reinforcement learning, to have the best behavior, we need to maximize the expected rewards. Another important element of reward is a scalar feedback signal, which need to be recorded. Then you have to understand that reward also indicates how well agents are working at a time step, which is represented by T. Finally, agent maximizes the expected sum of rewards in order to get the best possible outcome of reinforcement learning. There are different approaches on which your reinforcement learning can depend, primarily from perspective of agent and rewards. For example, you have policy-based agent reinforcement learning. It provides you capability of having better convergence properties. It is effective in high-dimensional or continuous action space. When the space is large, usage of memory and computation consumption grows rapidly. There comes the role of policy-based RL, which takes responsibility of avoiding this because the objective is to learn a set of parameters that is far less than the space count. Then second important approach is actor-critic agent, where actor-critic agent is not a single algorithm. It is collection of various related techniques. And all the techniques are based on policy gradient theorem, which trains some form of critic that computes some form of value estimate to ensure that it can be plugged into the update rule as a lower variance replacement for the returns at the end of an episode. The third important approach that you can take is model-free agent approach, where you don't have a model and it learns a policy or value function from experiences, but rather than explicit model of an environment. In case of model-free agent environment, you are learning it implicitly by learning which actions can provide you the best cumulative rewards. Fourth important approach is model-based agent approach. In case of model-based reinforcement learning, again you don't have a model, but it is based on experiences by performing various actions within the environment. You learn a policy or value function by also explicitly learning a model of the environment, which contains the transition function, reward function, and possibly starting state as well as terminal or terminating states. Now, one of the important factors that has impact over reinforcement learning is reward prediction errors. These are involved in most basic form of error-driven reinforcement learning. A reward prediction error can be calculated as the difference between a reward that is being received and the reward that is predicted to be received. In short, by applying the right learning, which depends on the action selection and the neuron which is involved as a function, you will have either expected reward or actual reward. Reward prediction error represents the difference between the expected reward and the actual reward. Reward prediction error can be quantified in any useful physical or subjective unit of reward. But you need to be careful when you are selecting neuron function. Objective of this video is to list the essential steps applied by agents in reinforcement learning to make decisions. Agent in reinforcement learning is the component that is responsible to make the decisions of what action need to be taken. And in order to make that decision, agent is allowed for use of any observation that can be made from the environment. In short, agent can be treated as a software program that makes decisions. These decisions are taken after perceiving information from the environment. In addition to this, in reinforcement learning, we usually care about handling a reward signal. Signal is nothing but something which is received from environment. Agents are autonomous and works correlated with other actions. Now let's try to understand what steps are taken by agents in order to take decisions. First step is it should perceive the environment. In other words, it should collect information from the environment to decide the action. Once it is done, it takes decisions, and decisions will result in corresponding action which that agent has to take. Let's take an example of robot, where objective of this human robot is to move the body. We'll have environment, which is the space where that robot has to do mechanical activity. Then robot becomes the agent. You will have observations which actually you have to record. And these observations could be angles of joints. Whenever there is a body movement per step, agent will receive the reward. Apart from receiving the reward, that action can in turn generate another action. For example, you may have body movement per step, which may enable agent to receive reward, and in conjunction with that, it may also invoke another action that may be turning direction of the joints. In short, you will have environment and agent which will collaborate with each other in order to generate actions and rewards which are required in reinforcement learning. Objective of this video is to recognize the prominent types of reinforcement learning environments. There are different types of reinforcement learning environments. Some of them are deterministic, you have observable, you have discrete or continuous, and then you have single agent or multi-agent. Now let's try to understand difference between deterministic finite automation and non-deterministic finite automation. In case of deterministic finite automation, it goes through finite number of steps and it performs one action for every state. But when we talk about non-deterministic finite automation, it is not at all possible to identify the next state with non-deterministic finite automation. And you will have more than one option available for the identified automation. Let's differentiate between single and multi-agent. In single agent, it's only one environment interaction. And if you have another environment, your single agent cannot interact with the previous environment. But when we go for multi-agent, It manages dynamic environments and can have changing environments as per the need. Current slide indicates representation of single and multi-agent. You will have single agent. In case of single agent, agent will have goals, action, and domain knowledge. But it will interact with only one environment. But when we go for multi-agent, as it is clearly indicated, your agent can interact with multiple different environments. For example, here we have two agents and each agent has its own goal, action, and domain knowledge. Apart from that, they have capability of dynamically interacting with more than one environment. Objective of this video is to demonstrate how to install OpenAI Gym and OpenAI Universe. OpenAI is a non-profit artificial intelligence research organization that provides various different tools in order to promote and benefit humanity as a whole from artificial intelligence initiatives. There are two important components that we are going to install, which is initiative of OpenAI. First one is Gym. It's a toolkit that is used for developing and comparing reinforcement learning algorithms. Then you have OpenAI Universe, which is a software platform that helps to measure and train AI, general intelligence across the world. Now let's try doing installation of OpenAI Gym. In order to install OpenAI Gym, you need to ensure that you have Python 3.5 plus installed. Let's go and install Gym by using pip command. To do that, we have taken up an Ubuntu instance which is created in AWS. You can use local Ubuntu or any other flavor of Linux or Mac systems. In order to do installation of Gym, we'll write pip followed by install followed by Gym and we'll press enter. This is the simplest approach in order to go and install Gym, which will be used for reinforcement learning. We'll wait for installation process to get over. Your installation is successful along with the warning that says that you are using older version of pip. You can go and you can upgrade it. Let's go and upgrade our pip, though Gym is already installed. To upgrade, we will write pip install upgrade pip and press enter. It will ensure that it has successfully installed now the new or latest version of pip. Once OpenAI Gym is installed, you can go and you can utilize packages which are provided by Gym in order to build your reinforcement learning applications. Now our objective is to install OpenAI Universe. To do that, you need to ensure that you have installed Conda. In order to check whether Conda is installed or not, you can go and you can write at the command prompt Conda followed by -v, press enter. Once you press enter, you get the version of Conda. In case if you are not getting, it indicates that either it is not installed successfully or you haven't done the proper setup. Follow the documentation in order to install Conda. Now our objective is to create an environment and name that environment as Universe. To do that, we'll be writing Conda followed by create followed by name and we'll give name as Universe. After specifying Universe, we'll go and we'll specify Python version and we'll specify Anaconda. So now we are creating a new isolated environment that will take responsibility of managing packages, versions, in order to ensure that you don't need to reinstall Anaconda every time. We'll press enter. Once we'll press enter, it will start fetching the packages, solving packages specifications, and move towards final creation of the universe. It will ask you to proceed. We'll say yes and press enter. Once you'll press enter, it will go and it will start installing all the packages which are needed in order to create your universe environment. Now, once your environment is created, you need to go and you need to activate it. To activate it, first we will clear and then we will write source followed by activate followed by universe and press enter. Now you'll find that you have moved to an environment called universe, where you can go and you can install various other packages that are needed in order to build your artificial intelligence programs. For example, for computer vision, you have to go and you have to install OpenCV. For GPU based applications, you can go and you can use TensorFlow framework. So depending on the need, you can go and you can install the required packages. Now it's time to test your knowledge and understanding of what we have learnt in this course. So in this exercise, you will list the essential elements of reinforcement learning, name the prominent agents involved in reinforcement learning, specify the steps that an agent takes in reinforcement learning, recall the types of reinforcement learning environments. Now I want you to pause this video and attempt all of the exercises and then come back to view the solutions so you understand how well you have attempted. Some of the important elements of reinforcement learning are agent, action, discount factor, environment, state, reward, policy, and value. There are different types of reinforcement learning agents. Some of them are value-based agents, policy-based agents, actor-critic agent, model-based agent, and model-free agent. Steps of agents in reinforcement learning are: agent perceives the environment, takes the decision, and converts decision into actions. There are different types of reinforcement learning environments. Some of them are deterministic, observable, discrete or continuous, and single agent or multi-agent. Objective of this video is to recognize different types of reinforcement learning that we can implement for decision making. As we already know that reinforcement learning in formal terms is also called as a method of machine learning wherein the software agents learns to perform certain actions in a given environment, which probably leads to maximum reward. It does so by exploring and exploiting knowledge it learns by repeated trials of maximizing the rewards. Some of the important terminology that are used in order to implement and understand reinforcement learning are based on agents and environment. Let's first try to understand what is agent and what is environment. Agent is an hypothetical entity which performs various actions in an environment to gain some reward. Then you have environment, which is the scenario which agent has to face. In order to understand various other components which uses agent and environment in order to implement reinforcement learning, we need to talk about state. State is the current situation which is returned by the environment. Then we have policy. Policy talks about the strategy that the agent applies to determine what should be the next action based on the current state. Then you have value of two types. One is Q value and second is value. Q value is similar to value, but there is a difference, and that difference is in terms of extra parameter which it takes, and that extra parameter is the current action. When we talk about value, it is the expected long-term return with important factor like discount. Then we have reward. Reward is considered as the immediate return which is sent back from the environment to evaluate the last action which was taken by the agent. Then finally, we need to understand what is action. Action is all the possible moves which an agent can take. Now let's try to understand how actually we can get a reusable model of reinforcement learning. Reinforcement learning types can be classified based on model. Model is simulation of the dynamics of the environment where your agent operates in order to give you different outcomes. Now let's try to understand two fundamental types of reinforcement learning. One is model-free and second is model-based. When we talk about model-free algorithms depends on trial and error to update their knowledge. Model free may not need space to store all of the combinations of state and actions. But when we talk about model-based reinforcement learning, model learns the transition probability from the existing pair of states and the action to the next state. It helps agent to understand the world and create a model that represents it. Model-based may need some extra space because model will store state and action, and that may lead to space growth. In case if you have a sophisticated algorithm where you need multiple state and action, your space need will grow. So in certain scenarios, you'll find that model-based implementation becomes impractical. Now let's try to understand reinforcement learning types based on the policy. You can have two different types of reinforcement learning when you apply policy as an important factor. One is on policy and second is off policy. In case of on policy, you'll find that agent learns values which is based on its current action, and this current action is derived from the current policy. Whereas when we talk about off policy, it learns values which are based on actions obtained from some other policy. So depending on the need, we can go and we can adopt appropriate type of reinforcement learning. Now let's try understanding various different types of reinforcement learning algorithm. You have Q-learning, which is considered as an off-policy algorithm used for temporal difference learning. It can be proven that given sufficient training under any policy, the algorithm may converge with probability 1 to the close approximation of action value function for an arbitrary target policy. Q-learning learns the optimum policy even when actions are selected according to a more exploratory or even random policy. Second important algorithm for reinforcement learning is state action reward state action. It's an algorithm which was derived from Markov decision process policy. It is used in reinforcement learning for machine learning. In certain books, you may find an alternate name also for that, which will be SARSA. This name simply reflects the fact that the main function for updating the Q value will depend on the current state of the agent, which is S, the action of the agent selected, that is A, the reward R, and the agent gets for choosing this action, the state that the agent enters after taking that particular action, and finally the next action, which is called as A2. Now let's try understanding deep Q learning. Deep Q learning is considered as combination of two different school of thoughts. One is it uses deep learning, and second it uses reinforcement learning. Deep learning may not have labels and reinforcement learning may not have tables. We have another method which is policy-based method. Deep Q learning is a value-based method, but when we talk about policy-based method, we have algorithm called as policy gradient. Policy gradient determines outcomes based on policy. There are certain advantages which you may get. For example, it can also learn from the outputs of the probability that is generated for every action. Objective of this video is to demonstrate how to implement reinforcement learning using Keras and Python. You need to go and you need to ensure that you are able to build a model that can be utilized for reinforcement learning in order to do score calculations. To do that, we have launched Ubuntu, and in that Ubuntu, we have launched VI Editor. We started with importing packages. For example, we have imported NumPy as MP in line number 1. In line number 2, we are using OpenAI Gem component that will provide us environment to build the model. Then we are using Keras, where we are using keras.model and we are importing sequential model. Then in order to ensure that we are able to have multi-layer, we are using from keras.layers and we are importing dense, activation and flatten. We are taking optimizer, and optimizer that we are going to use here is Adam. Then we can go and we can take agent that we want and also policy and memory that you want to apply on your reinforcement learning. First task is to go and define an environment name. We are using CartPole V0, which is part of Gem. Then we are getting details about the environment and we are trying to extract number of actions. To do that, we are using gem.make, np.randomSeed. Then we are calling seed of env. Then we have specified nb_actions, which is reading actions from your current environment, which is CartPole-v0. Now we are going to build a very simple model which can be used in reinforcement learning. Model is sequential. We are adding layers to it. So we have added a flatten layer where we are providing input shape and all the observations of your environment. Then we are adding dense layer, passing 16. An activation that we are attaching to it is ReLU. We have added multiple layers and last layer that we are adding is MB actions, which is dense, and activation is linear instead of ReLU. Finally, we are printing the model, which will be used by reinforcement algorithm in order to identify and get values like state and reward. In order to run this, we have to go to command prompt, and at command prompt, we'll be using Python test.py. Once you'll press enter, it will internally use TensorFlow backend and it will give you details of the layers which are built in order to apply reinforcement learning, where you have layers, output and shape of each layer along with the parameter. Final is summary of how many parameters are there, how many trainable parameters are being used and how many non-trainable parameters are being used. By using this model, now you can go and you can apply reinforcement learning and get the outcome. Objective of this video is to identify the role of Markov decision process in reinforcement learning. Markov decision process is the process of the agent observing the environment output consisting of a reward and the next state, and then act upon it. It is a process where agents will observe the environment, visualize the output which contains reward and the next step, and then take the decisions. This entire process is what is called as Markov decision process. Markov decision process is a classic approach which can be used in order to identify the problem of learning from the interactions to achieve the desired goals. Now, there are two important ingredients that we need to understand regarding Markov decision process. First is the mathematical term which is used, and second is the Markov process. Both combined together will provide decision-making capability. Mathematically, MDP is considered as a state which has property and it should meet a condition, that is P state plus 1 or ST equal to P ST plus 1 with a series. Primary objective of mathematical term is to capture all the relevant information from the history and make it available in the state. Whereas when we talk about applying Markov process, it is based on a random process which does not get stored in memory. It works with tuples where you'll have S and P based on the state space which is represented by S and transition function which is represented by P. Dynamics of entire system can be defined by using S and P values. Now, once we understand MDP, let's understand what is Markov reward process. Markov process provides you a value judgment. In other words, it is used for decision making. And it derives it from the accumulated reward by using certain sample sequences, where Markov reward process can be represented now by using a tuple which contains 4 important features. First one is S, which is a finite state space. Then you have P, which is considered as state transition probability function. Then you have R, which is the reward function in action. And then you have gamma, which is the discount factor. Objective of this video is to illustrate the concept of Q-learning rule, and deep Q-learning. Q-learning is considered as a model-free reinforcement learning technique. It can also be considered as an asynchronous dynamic programming approach. Primary objective of Q-learning is to provide you capability of providing an agent which has capability of learning to act in optimized way using Markovian domain. Apart from that, Q-learning works by using concept of estimation of the values depending on state action pair. Now let's try to understand the process which is used by Q-learning. Q-learning typically involves three important process elements. First one is Q-learning. Second is optimal action policy which need to be applied. And finally, you get the finite Markov decision process. Now let's try understanding Q mathematically. Q can have function which contains two essential parameters, S and A, where A can also be referred to a tuple or a table. Function represents the value that an action A can take with state S, and it is represented by using Q in square brackets S, A, which is equal to immediate reward achieved and the discounted reward. Immediate reward is considered as the point which is given when an agent moves from current state to another state while doing the action, whereas discounted reward is the point that is given for the future references. Now there are certain rules which need to be applied when we are using Q-learning approach. For example, you have a definition which is defined as QSA. It should equate with QSA plus A RY max of Q S caret A caret and eliminating Q followed by S and A, where you'll find that SAR and S invert is the experience tuple. Fundamentally, when we use this approach, Q value converges with the probability between 1 to n. Now let's try to take an example of the Q-learning, which is value-based method, and internally it uses artificial neural network principle, specifically used in CNN or convolutional neural network. You have some essential elements like state and action, which need to be made available in Q table, which was derived mathematically in the previous slide, and it gives you Q value. Another approach is you can pass on state, where you are now using deep Q neural network, which is combination of reinforcement learning and deep learning, and it gives you Q value 1 and Q value 2. Objective of this video is to demonstrate the steps involved in installing TensorFlow. There are different approaches which can be used in order to install TensorFlow. We can use pip in order to install it. There are various different packages of TensorFlow which are available. Depending on the need, you can select one of them. For example, you will have TensorFlow package, which is stable and it supports CPU only and works on Ubuntu and Windows. Then you have TensorFlow GPU, which comes with GPU support. You have TensorFlow Nightly, which is Preview Nightly built for CPU only. And you have TF Nightly GPU, which is with GPU support. You need to ensure that first step is to go and check the system requirement. You need to have Ubuntu 16.04 or later. You can also do installation on macOS 10.12 or above. You can install TensorFlow on Windows 7 and even on Raspberry Pi. Hardware requirement depends on the package that you are installing. In order to ensure that you are able to install TensorFlow, you do have certain software dependencies. So you need to ensure that you have installed Python. After installing Python, you will go and you will do certain checks. For example, we need to go and we need to check the system requirement. To do that, we'll check whether Python is installed or not. We'll specify Python 3 -- version and press enter. You'll find that you have Python installed. Then you need to check whether pip is installed or not. So we'll write pip 3 -- version. And it gives you outcome that which pip is installed. Then you will also go and check whether virtual environment is installed or not. For that, you need to go and check virtual env ---- version. So now you have all the prerequisites which are being met by your existing Ubuntu system. Now let's maximize it and write clear in order to clear the screen. Now you have to decide whether you will go for TensorFlow system install or you will go for TensorFlow virtual environment install. If you want to go for TensorFlow on virtual environment, you need to create a virtual environment. In the current installation, we are going to demonstrate how you will be doing system install of TensorFlow. So in order to install, we'll write pip followed by install, followed by ---- user, followed by ---- upgrade, followed by TensorFlow. And then you'll press enter. Once you'll press enter, it will start installation of TensorFlow. We have to wait till it collects all the information, downloads all the packages, and installs it. Now, once you get message that it has successfully installed, it indicates that now you have TensorFlow installed on your current system. Objective of this video is to demonstrate how we can start implementing reinforcement learning using TensorFlow. In order to ensure that we are able to use TensorFlow for reinforcement learning, we need to ensure that we have installed TensorFlow as well as framework which we have to use for reinforcement learning provided by OpenAI. In order to start building the model, we need to go and we need to ensure that we have taken the system with the right capabilities that helps you to write either GPU-based or CPU-based applications. Your first task is to go and import necessary packages. For example, we are importing GEM, which is one of the essential framework for reinforcement learning. And then we want to use backend as TensorFlow. So we have imported TensorFlow as TF. Then we have NumPy and random, which will be used in order to generate numbers and manipulate it. We are starting up with env equal to gem.make and we are passing again frozen lake environment which is provided by gem. We are resetting default graph and post resetting default graph we are going and we are declaring the input layer where we are saying tf.placeholder shape is 1,16 and d type is tf.float. Then we are using tf.variable. tf.variable in our case will be used for generating trainable variables. For example, we can use weight, we can use bias for our model. As of now, we are using random to generate uniform values. Then we are using tf.matmul and passing input 1 and w, which will ensure that it does matrix multiplication and it initializes qout, which will be another matrix. Finally, we are applying tf.argmax, which gives capability of evaluation in case of TensorFlow. We are passing qout, which is the matrix, which we got as a result of matrix multiplication applied in the previous statement. We are printing the prediction. Post-printing prediction, now we want to obtain the loss, which will be calculated by using sum of square difference between the target and the predictions of the Q values. So we are taking next Q equal to tf.placeholder, and if you see shape here is 1,4 because Frozen Lake is a grid-based environment which provides 4 grids. Loss tf.reduce sum, and we are passing tf.square next Q minus Q out, which will give us the square of the outcome. Finally, we are using trainer that will be used in order to train, and we are using gradient descent optimizer to optimize the existing model, specifying the learning rate to be 0.1. Our final step here is to ensure that our model is ready by using trainer.minimize loss, which will take responsibility of fitting the model. Once model is fit, we are ready to utilize Q learning phases to apply reinforcement learning. Now we'll save and we'll exit from our editor and we'll try to execute it to see the prediction. After writing name of the file, we'll press enter, and if you see, we'll get here tensor arg0 shape 1 d type in 64. So you are getting the predicted value. Objective of this video is to demonstrate how to implement Q-learning using Python. In order to ensure that we are able to understand concept of Q-learning, we are going to utilize capabilities of OpenAI Gym and Frozen Lake. First task is to go and import the required packages. For example, we are importing Gym and we are importing NumPy as NP. Then we are taking up an environment which comes along with OpenAI Gym, and name of that environment is Frozen Lake -v0. If you have created your own environment of OpenAI, you can go and you can specify that environment. Now let's initialize tables with all the zeros, and the way Frozen Lake environment will organize it will be in form of 4x4 grid of blocks, where each one either being the start block, the goal block, a safe frozen block, or a dangerous hole. After understanding these 4 different type of blocks, we need to go and set our learning parameters. So we have set our learning parameter LR, which is equal to 0.8, and Y, which is equal to 0.95. These 2 lines are present in line number 14 and 15. Then we are specifying number of episodes that we want to utilize in order to finally go and get the actual score. So we have specified in line number 16, number of episodes is equal to 2000. Then we are creating an empty array in line number 19. We are starting for I, n range, and we are passing the episode. We are starting this iteration where first task that we are doing is resetting the environment in order to get the new observation in line number 22. In line number 23, 24, 25, we are initializing some of the variables which will be needed in the program further. They are all, D, and J. In line number 27, we are trying to build the Q-table learning algorithm, where we are iterating using value of J, which was initially initialized to 0 in line number 25. We are taking it up and we are trying to build an iteration which will go from 0 to 99. In line number 28, we have given a control variable that will control iteration of the loop, that is J plus equal to 1, which will increment after every iteration. Then within each iteration, we are going and we are choosing an action from the Q table. Q table is already created in line number 12. So current code will get applied on line number 12, and objective will be to select an action. We are using numpy random.rand in order to select the action with the equated formula in line number 30. Once we have action, we need to get the state and the reward from the environment. In order to do that, we are using S1, R, and D, which is equal to env.step_a, which helps us to store different parameters of existing reinforcement learning using Q. In line number 34, we are updating the Q table with the new knowledge that we have gained as a result of line number 30 and 32. To do that, in line number 34, we are using Q, which is a function, and passing S and A, where S is the state and A is the action, which is getting equated using Q plus LR, that is learning rate, and equating it again by using NumPy package and max function of it within the given range. In line number 35, we are incrementing R all with the new value of R. Line number 36, we are initializing S with the value of S1. And then we are checking the condition that if D is equal to true, break. Else it will append R all to R list in line number 40. And this iteration helps us in getting score over time and final Q table value. Score over time is calculated using sum of R list divided by number of episodes. Now let's go and execute and see what is the value of score over time and final Q table value. To do that, we'll go to Spider and we'll click on Run button. Once you'll click on Run button, it will start execution, getting the environment, creating the initial table, applying the iterations and episodes, and giving you the final score over time and final Q table value. Under Variable Explorer, we can clearly see what is the score over time. It is 0.557, and what is the current value of Q table, which is specified in 2-dimensional array. Now it's time to test your knowledge and understanding of what we have learned in this course. So in this exercise, you will get an inbuilt environment using OpenAI Gym, extract the number of actions from the environment, and build a model using Keras and add layers to the model using ReLU activation. Now I want you to pause this video and attempt all of the exercises and then come back to view the solutions so you understand how well you have attempted. In order to ensure that you are able to get and build an environment using OpenAI Gym, you need to ensure that it is installed. After installing, you will launch an editor of your choice. After launching editor, you'll start writing the code. First line is import NumPy as NP, which provides number manipulation capabilities. Then you have import Gym. Then we are importing some of the important Keras packages in order to build the model. Our first task is to declare a variable called env_name and specify one of the inbuilt environment which is provided by OpenAI Gym. We have initialized env_name to cart pole v0. Our next objective is to go and extract the number of actions. In order to extract number of actions, we need to initialize env with the env name environment by using gym.make. Then we are using numpy np to generate random seed number, and we are placing that seed number in env. Finally, we are using env.action_space.n to generate number of actions. Our next objective is to build a model using Keras. In order to build a model using Keras, we are using sequential approach. For that, we have initialized model equal to sequential, and then we are adding certain layers to it. First layer is input layer. We are adding input layer by making call to a method called as flatten and passing the required arguments to it. We are also adding env.observation_space.shape, which adds features to the current model. Next, we are adding number of layers to it. First statement of adding layer is .add. We are specifying dense, and we are passing 16 as the layer density. Then we are using a method in order to add the activation. We are using model.add activation, and we are passing the activation function, which is ReLU. We can add as many number of layers as we want. Our final layer is add dense, where we are passing nb_actions, which is part of the environment. And then we are activating it using a different activation function called as linear. This helps us to build the model. Finally, we are printing model summary. Now, after getting the environment, extracting number of actions, and building the model, we'll go and we'll execute the program. To execute the program, we'll exit the editor by using :wq because we are using VI editor. Once we exit the editor, we need to go and run the program. To run the program, we'll write Python, followed by name of the file which contains the program, and that file is test.py. We'll run the program. Once we'll run the program, it will show the output where it will give you details of each and every layer that is added along with the output shape and the parameters.